よし。赤がさ、赤が切れると。青が今シャツが入ってます。
Yes, sir. Now you can live.
Okay. Good morning, everybody. It is a pleasure being with you this morning and share this session 2F on rehabilitation technology to enhance dam safety, underwater inspection, robotics, and repair methodology for dams. My name is George Dabre. I am from Switzerland, and I will chair this session. We have 6 speakers scheduled, so I would ask the speakers to stick to the allocated time and not go beyond 12 minutes so that we have a few moments for any questions and also to change speakers. Now, in order to start this session, let me say a few words on what we are going to talk about this morning and take a step back actually on this morning session. When we talk about underwater inspection and works to be undertaken underwater, actually we have to go back and see at what we want to do. And actually what we want to do is inspect parts that are usually underwater and possibly also perform some maintenance work or some repair work or even replace some components in this area. Now, inspection, I think we all agree that one key component of a dam safety framework is surveillance, and with this surveillance, it's visual inspections. When we talk about visual inspection, we tend to forget sometimes that there are not only parts that are easily accessible, that are above water, but we have also some parts that are underwater. And we also have to inspect them at a regular interval. It is actually also sometimes a regulatory requirement. For example, in France, for the highest category dams, it is required that every 10 years, those parts be inspected. And obviously, also you may have to do some work on these parts. Now, if we do inspect parts that are usually underwater, what do we have to pay attention to? What do we want to look at? At concrete dams, and this also applies in part to masonry dams, we obviously want to look at what is the general condition of the material itself, of the concrete or of the masonry material. We want to look at possible cracks. In concrete dam, this would occur very often at the level of the lift joints. We want to see if some of the vertical joints between the blocks are opening in concrete dams. So those are some areas we want to concentrate when we do inspect concrete masonry dams. If we look at embankment dams, we want to look at what is the condition of the upstream facing of the riprap. Facing asphalt, concrete, for example, what is the general condition? We want to look for possible settlements, for inception of sinkholes. And very important also, if you have some work, some conduits and some openings going through the dam itself, through the embankment, how does the contact zone look like? Do we have some openings? Do we have some cracks between the works and the inlets, the conduits, the intakes? Runoff river dams. Well, runoff river dams, what do we have any sign of displacements, of deformation of the dam and the foundation? Do we have any signs of water infiltrating into the dam material? And very important also at run-of-river dams are the steel components, electromechanical components. Do we have any sign of corrosion? Do we have erosion? Do we have abrasion? And for all types of dams in general, also sedimentation in front of intakes and inlets, what is the situation and what is the condition of the screens? Do we have any sign of clogging? Do we have any sign of corrosion, etc.? So those are the kind of things that we want to look at when we inspect parts that are usually underwater. So how to do that? Well, the easiest way or the more comfortable approach actually for inspection and maintaining parts that are usually underwater is to perform a drawdown. And you see on the right-hand side 2 pictures of drawdown that have taken place in Switzerland in the last few years. This is something which is done on a more or less regular basis, especially when it is connected with some maintenance work, some very heavy maintenance work. Now, there are some disadvantages when you perform a drawdown. First of all, it is actually not always possible, especially when you have large reservoirs and when the inflows are larger compared to the possible outflow that you can have without damaging the downstream areas. When you perform a drawdown, you will release sediments. This may mean that you will have issues, environmental issues. It takes time. If you are at a hydropower scheme, then you may have a loss of production. So all that makes it that it is not always possible or practical actually to do a drawdown. Just one comment, again, drawdowns are done on a regular basis all around the world. When you do perform a drawdown, for any reason, take the opportunity to perform a very comprehensive inspection, and do not forget to involve a geologist who will then inspect the reservoir banks. One word of caution at arch dam, and I know that in India you have only one large arch dams, but there are some in other parts of the world. Make sure that you verify the stability of the dam when the reservoir is empty, because obviously you don't have any arch effect if you don't have any water in the reservoir, and especially in winter at low temperature condition, then you may have some stability issues. And this is one thing that was checked at another dam, for example, here in Switzerland, which is the dam of Vallée d'Ilay, and we can see that the curvature is very high, and stability when the lake was empty had really to be looked at in a very precise manner. Now, this was if you perform a drawdown. Again, it is not always possible, and you may have to do some inspection and some work really underwater. Well, how can you do that? Well, you can use divers. One limitation is that you cannot go very deep with the divers. Depending upon how much sediments you have in the water, what is the water turbidity, observation will be impaired. And it takes time to perform a very comprehensive inspection with divers. Then you can use ROV, remotely operated vehicles. The advantage is that you can go much deeper, you are less affected by turbidity, and at hydropower schemes, you have essentially no or very little impact on the production, and last but not least, it is usually less costly. If you have to perform works underwater, again, usually you take divers, and in the last few years we have been using also saturated divings, and you see a picture here. It is of the dam of Punta Gala, again in Switzerland, Weather divers will stay for several days underwater in these chambers like the one you see here on the right. The advantage is, of course, that then you'll lose, it needs less time and you can also go deeper. Can we work in a remote fashion? Well, I personally don't know, and I will certainly hear what people have to say this morning. As a last picture, as a last slide, some example of what has been what you can get when you do some underwater inspection in particular. And you see first the case of the Madras intake. Where here the inspection did show that there is an accumulation of sediments in front of the intake. At the bottom left, you see an inlet of another dam, which is the dam of Puntalgal, and you see the accumulation of sediments in front of the inlet. From the dimension that we see here, we have a width of 9 meters, so the height of the accumulation of sediments was probably of the same order of magnitude, if not more. It reached the top of the screen, actually, of the inlet. But what we can see is that the inlet itself is free from sediments, and this comes from the fact that the gates are open, the bottom outlets are open at least once a year in a very regular interval. So this means that in case of an emergency, it would still be possible to open the gates and to release water. And what we see here on the right-hand side is the condition of steel lining also at an inlet here at another dam, which was the dam of Berenbroek. So those are some pictures of what we can see when we perform inspection in underwater. Okay, then let me switch now and go to the presentation again. Welcome everybody, and I think we will move to the first scheduled presentation on underwater diagnosis and repair and rehabilitation of dams. And this will be presented by Mrs. Sasikala. Please, can you start? On underwater diagnosis and repair and rehabilitation of dams.
Executive Engineer
And this will be presented by Mrs. Sasikala.
In this session,
please,
I'm going to share a few words about
can you start?
underwater diagnosis and repair and rehabilitation of dams. As we all know, existing gauging dams are always
underwater diagnosis and repair
so we need to protect the
dams.
executive how to protect.
And
We
this
have
will be
to
presented by
maintain
Mrs.
the dams, that is to increase the age of the dam. In this session,
please,
I'm going to share internal parts of
can
the
you
dam
start?
underwater diagnosis and repair and scans to our body dams. So the modern methodology we adopted, existing gauging dams are always non-destructible. So we need to geological dams to identify.
And
We
this
have
will
to
be
pass in
presented
all
by-
types.
Excuse me, excuse me. Can everybody mute the mic except for Mrs. Sasikala, please? Can you all close your mic?
Modern methodology we adopted, existing gauging dams are always non-destructible. So I'm going to talk about the case study of Sholaya Dam. We have to pass in all types.
Excuse
Here,
me.
we adopted
Excuse me.
as well as
Can everybody mute the mic except
What is
for
sonic
Mrs.
tomography?
Sasikala,
How
please?
it works?
Can you all
Sound waves travel
close your mic?
Modern methodology we adopted. So
Hello?
I request the host to share my recorded presentation.
Yeah.
good morning, one and all. I'm Sashikala, Executive Engineer in the design wing of Tamil Nadu Water Resources Department at Chennai. In this session, I'm going to share a few words about underwater diagnosis in repair and rehabilitation of dams. As we all know, existing aging dams are always a treasure to our country. So we need to protect those treasures. How to protect? We have to maintain the dams. That is, to increase the age of the dam, we have to diagnose the internal parts of the dam as we do ultrasound scans to our body. So the modern methodology we adopted is the non-destructive testing method. That is a geophysical testing methods to identify the leakage paths in all types of dams. It consists of ground penetration radar method, then electrical resistivity imaging. The next is sonic tomography. And the third one is underwater scanning using remotely operated vehicles. So I'm going to talk about the case study of Sholaya Dam in Tamil Nadu. Here, we adopted sonic tomography as well as underwater scanning using remotely operated vehicles. What is sonic tomography? How it works? Sound waves travel faster in the denser media. So when there is seepage in the concrete or mortar, the concrete or mortar becomes porous. Thus, the density is reduced. Thereby, the velocity of sound waves is very less. Thus, by identifying the low velocity zones, we can predict the seepage in those areas. This is the sonic tomography method. Now, let us see about the Sholaya Reservoir project. That is, it is under the Parambikullam Aliyar project scheme, which is a prestigious scheme of Tamil Nadu, located in the Vanemalai Hills. This scheme consists of 10 number of dams, 4 powerhouses, 6 main tunnels, and 7 irrigation canals. So this is how the line of dams. Here, the topmost is the Upper Neera Dam, and next is the Lower Neera Dam. The third one is the Sholaya Dam. Here, we have 2 powerhouses. In addition to diverting water to irrigation, we generate power. These are the 2 powerhouses located here, and the downstream of this is Parambikullam Dam, and again Tunnakadavu, Peruvaripallam, like that the system goes on. Next. Let me say about the salient features of Sholaya Dam. The Sholaya Dam is located in the Coimbatore city of Tamil Nadu. This was constructed during 1961 to 1971 across River Sholaya. And the storage capacity at MWL is 5,677 MCFT. And the debt storage capacity is 338.9 MCFT. This dam is a composite dam, consists of earthen as well as masonry dam. The masonry part has spillway and non-spillway portion. The spillway has 3 number of gates. And the height of the masonry dam from the rock level is 345 feet. I can say this is the highest dam in Tamil Nadu. And the special feature of this dam is it has 3-tier gallery. Then let me talk about this in this order. That is, first of all, diagnosis using non-destructive testing methods, then underwater inspection to identify the loss of water and using ROV, and then the rehabilitation. This is the cross-section of the non-spillway portion of Sholaya Dam. So we have 29 number of notches and 167 number of porous drains. The gallery, 3 galleries are situated at 3 different locations. The top gallery, this is the top gallery. This is at 3,156 feet. And the intermediate gallery is at 3,066 feet. And the foundation gallery is at 3,018 feet. The rocky bed is at 2,960 feet. So here, let me enlarge the section. Here, from the dead storage is from the river bed level, that is 3,040 feet, to the tunnel sill level, 3,130 feet. That is, the dead storage portion is about 90 feet. And the total height, as I said, is 345 feet. And the live storage portion alone is 160 feet. So we can see that is half of the storage is the dead storage portion only. So we need to diagnose by underwater scanning. Here you can see the pictures of the galleries. This is the topmost gallery. Here we don't find any leakage. There is seepage water. And here, this is the intermediate gallery where considerable amount of seepage is there. And this is the lowermost gallery. There is a foundation gallery. Here you can notice more seepage. This is the closer view of a leached portion in the drainage hole of the gallery. What is leaching? That is the water percolates and gets leached. Let me explain about leaching. The soluble matter coming out from the structure by the action of the percolating water is called the leaching. Thus, deterioration of saturated concrete takes place due to cycles of weathering. When the water with the dissolved salt splashes onto the structure, some of it migrates through the concrete through cracks or pores during wetting. As the concrete dries, the salt solution is concentrated and eventually it crystallizes as we see in this picture. This is what leaching. Here, the picture of leaching, it looks like a snow-like structure in the lowermost gallery. So this leaching, how it affects the structure, that is how the structure or mortar or concrete gets deteriorated due to leaching. Yeah, the cement or mortar deteriorates due to the reaction that takes place between the constituents of the concrete or mortar itself. Most common of these reactions is the alkali-silica reaction. The alkalis present in the cement react with the silica found in aggregates. This reaction gel expands when it is moistened, causing tensile stresses in the concrete. This reaction gets accelerated with alternate wetting and drying frequently associated with the aquatic splash zone. This wave action in the splash zone is susceptible to sulfate and magnesium ion attack. This action washes away soft outer layers of concrete or mortar and replenishes the supply of aggressive chemicals. Always, the reacted products occupy a greater volume than the original solid materials, thus resulting in the increased stresses in concrete. Thus, cracks are developed and the structure gets deteriorated. The basic science hidden here is when the solvent, that is the water, reacts with solutes present in the construction materials, it gives a solution. This solution contains some essential solutes which reduces the strength and the durability of our structure over years. So next we see how we did underwater scanning in Sholaya Dam. In the year 2018, we did a survey there by using the remotely operated vehicle. This is a picture of the remotely operated vehicle. We can operate it with joystick remote controller in the control room. This is how the ROV floats in water and captures the images. This ROV captures the entire, it scans the entire face of the dam underwater. Then here we can see the signals received, and these are the pictures we got from the ROV. There's a loss of water between masonry blocks at a height of 3,123 feet. Here, crack is observed at a height of 3,130 feet. So likewise, we get all images from the ROV and we compare. Not only photos or pictures, a high resolution video of the dam was also recorded using ROV mic. So what we observed is the loss of water in the submerged portion of the dam was very less compared to the live storage portion. That is, the portion of the dam which is exposed to alternate wetting and drying. See, the surface of the dam where alternate wetting and drying happened is more prone to loss in water than the portion immersed in water. This is what we observed in the Sholaya Dam. Next, coming to the point of we diagnosed the damages, then now the rehabilitation begins. How we rehabilitate? This is, as we know, this is a masonry dam. We need to repair the joints. First of all, the entire face of the dam, the joints are cleaned using, this is racking of joints is carried out. Then it's cleaned using water jets and then dried. You can see the existing and as well as raked joints here, we can compare. So after drying, the cavity filling is done. Cavity filling is done in two methods. That is, if the cavity is 5 centimeter to 30 centimeter deep, we can refill the cavity after cleaning by manual method. without any vibration. This is how they are doing. Next is, if the cavity is from 30 centimeter to 1 meter deep, we have to do injection pressure grouting. This is how the pressure grouting is carried. We are drilling holes of 25 mm dia and 300 mm deep in a triangular pattern. Then the PVC nozzle of 12 mm dia is inserted using quick setting cement. A mix of 43 grade cement with water as per the consistency required is applied, and on completion of grouting, PVC pipe shall be cut and sealed with cement putty. So this is how the injection grouting is done. Then coming to the last stage of rehabilitation, that is the pointing. Pointing work, filling with pointing mortar in horizontal and vertical joints. Average depth of filling is about 2 times the thickness of the joints, and it's finishing with T joints, that is alternate horizontal and vertical. And the primary coat with solvent-free epoxy bonding agent was applied with brush. Then it is filled with non-shrink, abrasion-resistant, UV-resistant, impermeable polymer modified cementitious mortar system. It has a compressive strength of about 45 Newton per mm square in 7 days and 70 Newton per mm square in 28 days. And the tensile strength is about 4 Newton per mm square in 28 days. And the permeability is less than 10 to 12 centimeter per second. So we can see the pointing, how it is being done on the upstream face of the dam. Here, this is what the arrangement made for rehabilitation of the upstream face of the dam. This is the masonry portion of the dam, and this is the non-spillway portion, and this is the spillway portion. So this is how the pointing was done. See, now coming to the post-rehabilitation. So after the upstream rehabilitation, the seepage has reduced to about 1/3. Even before rehabilitation, the seepage was within the limits only, but this type of diagnosis and rehabilitation has arrested the leaching to a greater extent, thereby contributing to the increase in the stability and lifespan of the dam. The seepage, here it is in this bar chart, it was observed from the year 2017 to 2018. It is clearly indicated. Then thus we conclude the lifespan of any hydraulic structure can be increased if it is periodically maintained in a good manner. So let's all protect these treasures for generations. Thank you.
Thank you, Mrs. Sikala. It was quite interesting to see how tediously the work was performed. As I look at the time, I would suggest that we go straight to the next speaker. And the next speaker will be Mr. Sota Ushida, who will talk about unmanned maintenance work with underwater remotely operated vehicle for discharge facilities of dams. Mr. Soto Ushida, please.
Can you see? Can you see the slide?
We can see the slide. I don't know if you can put it in full screen, but yes, we can see. You can start.
Oh, okay. Start.
Good morning, everybody. My name is Sota Uchida. In my presentation, I'm going to explain unmanned maintenance work with underwater remote operated vehicle, ROV, for discharge facilities of dam. In discharge facilities of a dam, 2 gates are usually installed in one discharge pipe, and one downstream is the main gate, and one upstream is the subgate. The subgate is only used when maintaining the main gate. The subgate is designed to open and close only when the upstream and downstream water pressures of the gate are balanced. It cannot be opened when the water pressure is applied only from the upstream side, as shown in this figure. Therefore, to open the subgate, we need to fill the discharge pipe with water and balance the upstream and downstream water pressures of the subgate. The role of the water filling system is to fill the discharge pipe with water. The water filling system is composed of a pipe, a main bulb, and a sub-bulb. The inlet of the water filling system is installed underwater of the reservoir. The pipes and valves of the system need regular maintenance for aging and corrosion. However, in order to maintain the sub-valve and the pipe between the valve and the reservoir, we need to install a water stop cover over the inlet of the water filling pipe to stop water flow into the pipe, because we do not have a system to stop water. The installation of the water stop cover has usually been performed by divers so far. However, the inlet of the water filling pipe is often installed in deep water depths of more than 40 meters, involving great danger to the divers. In addition, diving over a depth of 40 meters requires a lot of large facilities and significant cost, and it is also highly risky. So, we developed an unmanned maintenance technique to reduce the risk of accidents and the cost. The technical methods to stop water into the water filling pipe is another way will be skipped considering the limited time. In order to make the installation work of the water stop cover unmanned, the ROV main unit is required to have good operability, and the water stop cover is required to stop water leaking into the discharge pipe almost completely. In addition, a mechanism for attaching, detaching the ROV main unit and the water stop cover, and a water injection mechanism for the water filling pipe are also required. To satisfy these functions, many devices and parts are attached to the ROV main unit and the water stop cover. This slide shows the components of the ROV main unit. To save the cost, we adopted an underwater ROV already developed for the inspection of waterways in power plants. We did not have a ready-made water stop cover, so we newly developed one. Highly flexible material was used for the water stop rubber to be applied to various shapes of the surfaces of the inlet. A needle valve is equipped to the water injection device, enabling water injection to the water filling pipe. To realize the unmanned installation of the water stop cover by using the underwater ROV, we needed to ensure that the essential functions are normally performed under the actual conditions. Therefore, we decided to conduct field tests at Takayama Dam and Hiyoshi Dam. The test procedures are as shown on this slide. Through these procedures, we evaluated the functions of this water stop, cover touching, detaching, and water feeding systems. In the following slides, I will explain the test conditions and the results at each dam. Takayama Dam is an arch concrete gravity dam with a height of 67 meters. The underwater depth of the inlet of the water feeding pipe was 9.5 meters. The turbidity around the inlet was between 3.7 and 4.0 degrees. This slide shows the test results at Takayama Dam. The water stop and water injection systems operated satisfactorily. The cover attaching, detaching system worked properly with the water stop cover. However, during controlling the ROV, the cover hit the structure by accident and came off. To prevent easy loosening, we needed to strengthen the power of the electromagnet. The upper right figure shows the structure of the inlet of the water feeding pipe at Takayama Dam. We had to offset the water stop cover by 30 mm from the center of the inlet. It was performed without any problems. However, we found that we needed to install an additional camera and light to improve visibility in turbid water. In addition, we discovered that the buoyancy of the water stop cover depended on water depth increased the difficulty in controlling the ROV's attitude. Therefore, we needed to add a function to adjust the buoyancy of the ROV main unit. Kiyoshi Dam is a concrete gravity dam with a height of 67.4 meters. The underwater depth of the inlet of the water feeding pipe was 23.7 meters. The turbidity around the inlet was between 3.8 and 4.6 degrees. This slide shows the test results at Kiyoshi Dam. Kiyoshi Dam has a unique water feeding in pipe inlet. The inlet is installed in so small space that we had to operate ROV in the limited width of 4 meters. The length of the ROV is 2.45 meters. Actually, we successfully controlled it during the operation. We thought that the additional acoustic camera, which was installed after the experiments at Takayama Dam, helped this operation. However, since the camera and light were obstructed by other devices, we reconstructed their positions and angles. Also, since the direction of the light beam was changed, when it conducted to something by accident, we needed to add a protective cover on the light. Based on the test results at both dam sites, we confirmed that an underwater ROV was practical. In the meantime, we needed to reconsider the following points to improve the way of operation. To save cost, we used an underwater ROV originally developed for the inspection of waterways in power plants. But if this method becomes widely known and adopted, the cost of this service can be lowered, and we can develop a special ROV with each purpose. And we think we will need to make the size of the ROV main unit smaller, increase the propulsion power, and strengthen the attitude control functions. The cost and safety advantages of this system could have been recognized through this development. This system was patented in Japan jointly by the Japan Water Agency and Sato Teco Company Limited. We hope that the system will be widely used in various places in the future. Thank you for your attention.
Thank you, Mr. Sota Oshida. It was quite interesting to see this application, and I guess we are coming to situations where we can use ROV to perform underwater work. I forgot to say, if you have any question to the presenters, please do put your question in the chat room and also to Mrs. Sasikala so that we can share them at the end of the session. Again, thank you very much. And without any further delay, I would come to the next presentation. This is from Mr. Tian Jing preliminary analysis of underwater maintenance technology to the water caution pool of Xikuradu hydropower station.
Okay. Good morning, everybody. Can you hear me?
Mr. Sota Ushida, yes, okay. Can you close your video? Yes, please go ahead. Yeah, Mr. Tianjing Jie.
Okay. Okay. Can you see my screen sharing?
I can see that. Can you put that in full screen? But we can see that, yes.
Okay.
Can you put in presentation mode?
Okay. The title of my report is Preliminary Analysis on Water Maintenance Technology to the Water Cooling Pump of Shiradu Power Station. Okay, let's look at the report outline. First section, overview of Shiradu Power Station. The Shiradu Power Station is located at the lunar reaching of Jinsa River, which is a giant water conserving and power hub focusing on power generation and taking into account sun blocking, water country, and improving downstream chilling conditions. The power station is equipped with two underground powerhouses on left and right banks. The total capacity is 13,816 megawatts. The power station is a concrete double curved dam with a maximum height of 285.5 meters. Further discharge and anticipation facilities consist of 7 serve houses and the window house in the dam body. The water cooling pump behind the dam, which makes the further discharge with the characteristic of lead outflow, alkalinity, and energy dissipation in water cooling pump. The regulation capacity of Shiradu Reservoir is incomplete annual regulation, and the flood discharge time in flood season is more than 3 months each year. And the cross-section view of the water cooling pump is shown on red, and it's a duplex transversal section. Due to the long-term flood discharge every year, there is no other engineering experience to refer to. It is necessary to arrange the inspection and the maintenance of water cooling pump every year during the initial operation period to employ its operation rule and ensure its safety. Currently, there are mainly 3 types of common defects in the operation of the water cooling pump, including concrete abrasion, concrete cracks, and the structure-driven damage. Those three types of concrete defects should be treated at the initial stage of the occurrence to avoid opposition of the water coupon with defects, which would lead to accelerated deterioration of the defects and structural damage. Therefore, the Shilodu power plant will conduct a comprehensive inspection and maintenance of the water coupon after flood season every year. The post-flood maintenance can be divided into two stages. From 2013 to 2017, the water coupon was checked and repaired after being drained. And since 2018, and water inspection and repair have been carried out to build water coupon with the cooperation of underwater robot and divers, as shown in picture. Next, look at the second section. Introduction to the maintenance of the water coupon in drain. The specific drainage time is as follows. It can be said that in pumping time is about 1.5 months, and the filling time is about 1 month. And this is a photo of drained water coupon. And photos of inspection of the water coupon have been dragged. A look at typical defects and repair principle. Due to a time constraint, I won't go into detail. 1. Concrete wear and scour, as shown in the picture. 2. Concrete cracks and water seepage. 3. Concrete damage at structural joints. After drain and the concrete wear, piece and cracks were contained in time. The working condition of structure joint was improved and the leakage of water coupon was significantly reduced, as shown below. However, there are some shortcomings in draining the water coupon for maintenance as follows. Drainage is time-consuming and a large investment. The unloading, reboundment, deformation of the water coupon by draining is not conducive to struggle stability. The water coupon was overhauled during the low temperature season, which will aggravate the shocking and rebound deformation of being dragged. With the increasing maturity of underwater maintenance technology, it is recommended that the water coupon can be repaired underwater after the flood season. Then let's look at the third section. Introduction to underwater maintenance technology for the water coupon. Currently, underwater maintenance may include dive operation and underwater equipment operation. And this is diving job classification. And the unmanned diving equipment. The application principle of underwater maintenance robots, including limitation of diving operation, the rapid development of robotic and electronic information technology, the encouragement of national science and technology innovation, the mature application of underwater robots in offshore oil and underwater salvage search and rescue. And this is the main function of the underwater robots owned by Shilodu. Inspection scheme underwater. The cooperation of underwater robots and divers were used in the inspection of the flood and slopes of the water coupon. which has the characteristics of full coverage, point positioning, and high accuracy. The types of defects existed mainly as follows. The concrete of the floor and the slope is slightly abrated. A few cracks in the concrete on slope, some of which have water seepage. The polyurea on the structure joint surface is partially peeled off and damaged. Repair materials. The main properties are shown in the table below. After sufficient comparison and testing for different defects, Xiamen brand and water sealant, HKUW1, epoxy mortar and concrete, HK969 joint filling material are selected as water repair materials. And the main characteristics are conveyed and water contraction, high strength for curing, and good impact and wear resistant. Contraction process. For the pair of different types of defects, the contraction process is as follows. 1. Damage of concrete surface. Repair principle. Damage less than 1 centimeter in depth will not be repaired. Damage with a depth of 1 centimeter to 3 centimeter are repaired with epoxy mortar. Damage greater than 3 centimeter in depth are repaired with epoxy concrete. The defects such as concrete cracks, structural joint damage and leakage. Repair principle. Water seepage cracks should be repaired with a water sealant, which also has anti-seepage and structural reinforcement functions. If it's impervious cracks are repaired with a K99 joint filling material. If it's polyurea filling off and being broken, it to be trimmed first. This is a comparison before and after and water repair. And the water inspection and repair of the water pond only save construction period and cost, but also benefit the structural of the water pond. And after maintenance, the concrete damage and the cracks have been well improved. The repair effect is better, and the leakage of the water pond is also significantly reduced, as shown below. The inspection results provide the reliability of the underwater inspection and revealed the damage type and the distribution law of the water pond during flood discharge. It should be taken as the focus of attention in the future and also provide reference significance for related projects. Finally, we look at the fourth path, prospect for maintenance technology of hydraulic structures. I will give a brief outlook from two aspects. The first part is improvement of underwater robots as a function of clean water replacement, which can overcome the influence of cell coverage and mold environment on data collection and achieve high definition data acquisition on the water concrete surface. To strengthen the research of small and flexible underwater robots, which can inspect and repair in regular and narrow underwater area so as to achieve no dead spots. 3. Comprehensive robots that can integrate underwater inspection and multi-repair scale to achieve the goal of underwater unmanned inspection and repair. The same path is prospect for other maintenance technologies. Research of intelligent inspection system of special drones for different we can realize the intelligent inspection of areas such as high dam surface, overflow surface, and high slopes. To relying on new technologies such as big data, cloud computing, and artificial intelligence, the intelligent maintenance system for hydropower station that integrate intelligent inspection, intelligent technology, independent evaluation, decision marking support, and unmanned inspection and repair will be we can further improve the construction of intelligent water conservancy. Okay, my point is over. Thank you.
Thank you very much, Mr. Tianjun Che. It was quite interesting to see in which direction we are going. I just want to tell you already now that we have some questions, so don't go away at the end of the session, so that we can have a small discussion still afterwards. But for the time being, I want to switch and go ahead with Mr. Kanapa, who will talk about inspection of dam infrastructure using ROVs, an innovative approach. Please, Mr. Kanapa.
Thank you, George. I hope I'm audible.
You are indeed. Yes, go ahead.
Yes, okay, thank you. Just a second, just present my screen. So is my presentation visible now?
We can see the presentation. I don't know if you can put it in presentation mode.
Yes. Yeah.
Perfect. Thank you.
Okay. So very good morning to all, and thank you to all the speakers, particularly George and Shashikala Madam and others, Shota and Tianjin. So to set up the pace for the session. So I hope you are all aware of how the ROVs are trying to change the scenario of underwater inspections, particularly in the space of dam inspections. So we are IRO and we are based out of India, and we are into critical asset infrastructure inspections. And currently I'm presenting a topic on dam infrastructure inspections, particularly using ROVs and how they can effectively be employed in this scenario. So generally remote operated vehicles, just to give the definition, are tethered, or I would say cabled underwater vehicles or robots which are used to explore deep oceans, and they are in this industry of ocean exploration, I would say that for about 40-50 years now, particularly into oil and gas exploration. And now they are finding more and more application in inland assets like dams, because of the extensive deeper dams and having very deep water pockets, and particularly structures like shell shaft, which always carry some water levels above 50 meters, 60 meters, which is quite difficult and constrained environment for divers to actually effectively execute. So rather than, as George and others have already mentioned, draining a dam, it's better to always have a informed decision making using ROVs. So they are already in this field of inspection, particularly into oil and gas industry, shipping industries, and they have penetrated into many other industries, and they are finding quite a lot of application in dam inspection too. So just to set up with how the general layout like for the people who having used to this. So generally they are easily deployable. They are come in the technical class, what we call as observation class ROVs. So they are generally 1 or 2 person deployable, coming in the range of like 50 to 60 kg or lesser than that. Systems up to 20 kgs are effectively being used, like the one you are seeing here. So they are deployed from the water level to the dam, and they can be deployed based on the conditions. We have employed it from the dam, I would say dam approach road, and also we have executed in certain dams using boats when the level of water is way too low from the deployment point. And they are easily controlled using a basic systems like this with innovative algorithms and control station. You don't need any hefty systems. Yeah. Yes. So dam assessments, so periodic assessment and maintenance of dam is necessary to maintain the structural integrity of such infrastructures, as rightly said by other speakers also. And conventional divers were employed for dam inspections, but ROVs have proved to be safer, economical, and much effective method of inspection, and it's being highly used in these present days. And the key advantages I already described is, one is about the safety, as more and more dams are getting aged. They might be developing various kind of I would say seepages and defects and kind of sections, which might be riskier when you firstly employ a diver. Though diver have their own effective advantages on tactile capabilities and quick repairing capacities, but it's always safer to first employ a ROV to execute a first level of inspection to understand the criticality or the nature of defects. Then we will present various ways in which this has been done before by us, and others are also in this industry are doing such expert works in this area. So basically, as set up in this, they are mostly a visual inspection tool, and they have a limited level of, I would say, the next level of inspection. But this itself is very critical when it comes to planning for the next level of inspection. So they are surfacial structural assessment tools, and they can be used to get the whole visual assessment of a dam structure, as most of the dams situated, particularly if I take the case of India, North India, and many of the other rivers are perennial, so the debt storage level is quite high, and most of the dams owners wouldn't have had a chance to actually see what is beneath, I would say, like some 15-20 meters to even 70-80 meters. It varies with many other dams based on their debt storage level. So because we cannot deep draw it or drain it fully, many cases are there where the dam wall has never been exposed. So there, these tools are very effective. And to understand the structural, or I would say the visual part of deterioration, we employ generally the common methods are, one is the visual imaging methods. They are basically high-end cameras with optimized lighting and also specific algorithms to make the image better for the end user. And on the other side, it's the sonar imaging methods. Most of the waters you cannot get them in very, I would say, appreciable visual means, because of the extreme turbidities, or maybe a post monsoon scenario will create a lot of turbidity, and if it is an algae bloom, then again the visibility is quite constrained. Then sonars would come very effective, and we have employed those also in many of these scenarios. So generally, to find the structural deterioration, you can see how the system employs. So they are deployed on the upstream side, and the ROVs are made to dive vertically downwards in, I would say, what we call as lawnmower pattern, parallelly to the wall to capture. And structural deterioration refers to the damage that occurs to the dam over a period of time, mainly due to internal external factors. And internal factors mostly is due to formal design, poor design, or poor construction. Many things can cause these defects, and in the external factors, it could be embankment sliding, many other seismic activities. There are like multiple scenarios which can cause this kind of structural deterioration. And what you are seeing is some of the methods which we employ. I would quickly take you through sonar first. So sonar are particularly sound imaging methods, and there are various sound imaging techniques. One is called the side scan sonar, and another method we employ actively is the imaging sonar. So what they do is, imaging sonar is mostly like an acoustic camera which you can use forward looking to see what is in front of you, if the dam walls are, or just to get a tactile information of the how the whole structure is deteriorated. That can be effectively seen using a imaging sonar. Here you can see a tire lying down at the bottom of the river bed, and you can arrange the visual ranges, but it needs a certain level of used to or expertise to understand or interpret the image. Whereas side scan imaging again are another effective tool, but they are used mostly by us for bottom mapping. Mostly post monsoon or extreme flood scenario, there are quite a lot of debris being collected, particularly near this Louis Gate mouth and many of the dam wall, I would say, riverbed joining points, the junction areas or the zones where these large boulders and all this can come rolling down to, and this could be a dangerous situation when we try to operate or like open the sluice gates or any of the other critical gates, or even the I would say trash rack are all getting damaged by this. So a side scan, bottom scanning would help us to get an idea of what is lying right beneath the dam structure, to get a feel of what to survey or what to expect before even sending a diver or an ROV into the scenario. And when you send in this imaging sonar, it will give you a close-up view of the situation. And post that, we can employ camera methods, and visual methods have been well explored by many ROV players in the industry. But addition to that, specific to the dam community, some of the key areas are particularly with the seepage or leakage assessment. So this is one of the dams in South India where we actively employed these two methods. So one is the feeler method and other one is the dye injection method. So how we employ is, feeler methods are generally the suction created by the cracks or the ingress of water through some of the joints which you cannot visually see. These feelers are generally sucked into that small crevices or gaps. This will give you a logical understanding of what or where you can suspect a seepage. So the general method is that while we are scanning, we also visually check with the additional camera. It's a second camera which keeps on looking at the feeler to have an understanding about, is the feeler getting sucked into these cracks or crevices. And once we confirm a suspected area, we inject dye. These are all common industry proven dye. This is a fluorescein dye, sodium fluorescein, which is also considered safe medical grade also. So they can be used in even drinking water sources. And we actually did this survey in one of the major dams across South India. It is also a source of drinking water for many important city downstream. So this, when employed with UV lighting, will give you a very good perception of the seepages, because mostly the gallery flooding will happen, but we don't know where to actually inject. So there and all, this kind of leakage detection methods, particularly the injections, are very helpful, and which are actively being employed along with the ROV. Additionally, on the imaging technique, what we do better is that you can see most of the images on underwater structures have this haziness, and they are bound to have this because of the suspended particles in the water causing the haziness. But you can see that with advanced algorithms and image enhancement methods, we can actually cleanse the image and remove the haziness to give you absolute clarity into the kind of defects. You can see a serious concrete erosion has been visualized here with a lot of material loss, and you can even see the aggregates being exposed into this scenario. So these are some of the best methods into additionally with the imaging, which will help you. And next upon is with these structures being so large and enormous, like 1 kilometer wide, or I would say that like 500 meters, 600-meter wide dams being inspected with multiple strips of images. A larger perspective is very important, and there this 3D reconstruction methods are very effective. We are working on this stage and developing such methods effectively for dam clients. So here you can see an off-the-shelf imaging method where a volcanic vent has been mapped like this. So multiple strips can be stitched together to give a I would say a larger panorama or perspective of how big the defect is or what is the condition of the whole dam in a single shot, rather than going through multiple videos. These are all emerging methods which we are effectively trying to employ into this dam inspection scenario. So to conclude we have visual inspections of dam is becoming more and more practical with the advent of ROVs, as they can go to deeper depths, even up to 200, 300 meters is now very much possible. And we are opening up possibilities for search shaft inspections also, as they are also a critical infrastructure, always holding waters well above 50, 60 meters to 100, 200 meters based on the head at which the generators are operating. And secondly, obtaining visual records of underwater structural damage of the dam face inlet structures using visual and acoustic tools like ROVs, key use cases with dam safety inspections. So they nowadays, particularly Icold and all these dam safety authorities are very keen to understand the structural condition, and ROVs can be effectively used. ROVs can be configured with multiple cameras, lighting methods, sonar methods, and other navigational and value-added tools. I think already Sota and Tiachi and others have already shown that how they are customizing the ROV platform to specific use cases for dams. So ROVs are capable. Only thing is that we have to understand the requirements in the dam. So preliminary inspection with the basic ROV methodologies, and then improving them and customizing them to next level of inspections or even maintenance methods are quite possible. Underwater communication and positioning capabilities are growing, and as rightly said, once this most often some of the limitations with ROV is related to the capability of tether, limitations of tether, or the cable being a cause for entanglement, or could be a cause for difficulty in piloting. But with the advent of better communication methods and autonomy, which we are already working on and improving, ROVs could be a very effective tool to be used in dam inspection methodologies. So that's most of the concluding remarks. Thank you all. Thank you for giving us a question.
Thank you very much, Mr. Kanapa. It was quite interesting also the part on post-processing, and this is something that sometimes we forget. I mean, we get the data and the images, but then we still have to interpret that. So thank you very much. Quite appreciate. We go then to the next presentation. I believe there is a video which has been sent. I see that Alberto Squero is there, but he tells me that he has a video. Alberto, do you want to say a few words first?
Okay, thank you very much. I have prepared a video, so the presentation should be go on smooth. It's quite long presentation, so better I recorded it in advance, so should be able to cover all the subject of the title. Thank you very much for starting the video yourself. Thank you, George.
Okay. Can the organizing committee start the video?
This presentation is focused on the underwater repair of dams with flexible geomembrane, recent cases. Research and development for underwater geomembrane systems started at CAPI at the beginning of the 1990s. In 1994, it happened the first underwater repair of a small area over the upstream face of Dix Dam in the United States. In the years 1995 and 96, CAPI performed a 2-year research contract with the US Army Corps of Engineers in the United States. In 1996, the system was validated, and in 1997, it happened the first large installation at Lost Creek Dam in the United States. The test campaign entailed the construction of a spatial wall with protrusion, corners, recesses, cavities, smooth and rough surface. And the wall is also a spatial vacuum system which allows to create differential pressure between the membrane and the concrete. The wall was placed in a tank full of water. The underwater installation entails several options, from the full phase just to partial phase repair, including cracks and joints, or installation in flowing water in canals. The first full phase repair was at Lost Creek Arch Gravity Dam in the United States in 1997. The dam is 36 meters high, and at the time of the repair, the concrete downstream was so wet and damaged that could be removed by hand. The CAPI geomembrane system is drained. The drainage layer is continuous behind the geomembrane. It has a peripheral collector and transverse discharge conduits. The presence of the drainage avoids buildup of back pressure. The drainage layer allows monitoring the geomembrane behavior by measurement of drained water. The piezometers installed between the concrete and the geomembrane indicate the height of the water which cannot be discharged, if any. For the installation, all equipment was mounted on barge. The drainage hole is drilled from downstream to upstream. The drainage discharge pipe is placed from downstream after the drainage box has been drained out. Installation was made also partially in the dry. In the picture, we can see the surface preparation, the installation of the drainage geonet, and the carpet dry pretensioning profiles used above the fluctuation water level. The picture shows the dry and underwater installation of vertical tensioning profiles and the perimeter seal. Near the dam, rolls of Sibelon geocomposites are welded together to form 8-meter wide prefabricated panels. The carpet pretensioning profiles used below the fluctuation water level do not require a cover strip. For the installation, the rolled Sibelon geocomposites panel are resting on the barge and are lifted at the top and then deployed underwater. In this picture, we can see how the end part of the roll is lowered at the heel of the dam. The geocomposite panels were fastened concurrently in the dry and underwater. At Lost Creek Dam, the works were completed in 1997. 10 years after installation, the seepage flows remained at less than 0.02 liter per second, well below the acceptance criteria. When California DSOD, the Division of Safety of Dams, inspected the dam, the comment was that the downstream of the dam was the driest it has ever been. In 2018, spillway remediation works require removing the top portion of the geomembrane system. Once the spillway remediation works were completed, the geomembrane system was extended onto the new concrete and the new top seal was installed. This extension covered the horizontal joint between old and new concrete. Another case is the partial phase repair of Studena Buttress Dam in Bulgaria, completed in 2018. The dam is 55 meters high and is for potable water storage. The harsh climate required covering the deteriorated concrete by shotcrete, but then the shotcrete detached. Therefore, there was the need for rehabilitation of the top 29 meters of the upstream face. That's why it's called partial phase repair. The client is the Bulgarian Ministry of Regional Development and Public Works with funds from the World Bank. The main requirement is that there is no impact on operation. And the scope of the works entails waterproofing of more than 5,000 square meters of the upstream face, mostly underwater, the rehabilitation of appurtenant structures and grout curtain, upgrade of control and hydromechanical equipment. The total contract amount was in the range of 16 million euros. The requirement of no impact on operation required the underwater installation, and successful underwater references were required. The complex geometry requires high flexibility of the geomembrane. The seismic risk of the area requires that the geomembrane is capable to bridge cracks, existing and future. The harsh climate requires the installation is done in cold weather, even in presence of ice. The installation was performed for 5 meters in the dry and 24 meters underwater. The waterproofing system consists of 2,000 grams per square meter anti-puncture geotic style and the Sibelon CNT 3750 geocomposite. The geocomposite is made of 2.5 millimeter geomembrane associated to a 500 grams per square meter geotic style. The system has mechanical anchorage lines and a full phase drainage system. The first operation consisted in removing the unstable shotcrete facing, both in the dry and underwater. The following operation was a surface cleaning by hydroblasting, both in the dry and underwater. Several different types of profile were used as a fastening system at the face. for instance, at the convex corners, which allows pretensioning of the geomembrane. At triangular recesses, point anchors were used, and flat profiles were installed at concave corners. Flat batten strips were installed as watertight peripheral seal. Carpi performed continuous monitoring of the diving operations. Some smoothing with mortar was required at location of anchorage lines, and also some patching with thick geotextile in the more aggressive areas. The very harsh climates require diving through ice. Geomembrane panels were first anchored at the top and then deployed into the water. The same operation carried out in the dry were performed underwater. Here we see the installation of the stainless steel profiles underwater, installation of the watertight perimeter seals underwater. In this picture, we can see how was the surface before the installation and after the installation of the geocomposite. The picture shows the works above the water level already completed. After the works were completed, scarcity of water required the use of the water in the reservoir, so exposing the portion of the geomembrane installed underwater. The quality of the work underwater is the same of that installed in the dry. Requirement of the contractor impose a maximum leakage through two drainage pipes less than 0.9 liter per second for the full waterproof surface. And the currently measured leakage is 0.2 liter per second, a very successful installation. Another possible application is the repair of joints or local defects. We show here the repair of the Nakai RCC dam in Laos, a project completed in 2015. The RCC dam, 43-meter high, has a CVC facing and joins every 22 meters. The leakage since the first impoundment reached almost 2,000 liters per minute, and local repairs failed. As first activity, an underwater survey was conducted to detect the sources of the leakage. A map with the location of the main leakage sources was prepared. A test installation was conducted in the dry to validate the components and the procedures, mainly for the connection to the internal water stop and the installation of the perimeter seal. The various activities consisted in lowering a sacrificial geocomposite, grinding the surface at the location of the perimeter seals, grouting the connection to the internal water stop, then drilling holes and placing the anchors for the perimeter seal, placing the underwater epoxy resin, and final fastening and check with the torque wrench. Here we can see the system installed, and the system behaves to full satisfaction of the owner. The last example I want to show is the repair in flowing water with the Ciberon mat. Why the Ciberon mat? Preservation of water is more and more important with increasing population and climate change. As canals age, their lining deteriorates and loses water tightness. Safety can be jeopardized. Local repairs are generally short-term. Long-term repair requires dewatering, and many canals cannot be dewatered. Need for a long-term waterproofing liner that can be installed underwater and in flowing water, with no stop of operation. The Ciberon mat is a wide mattress composed by two synthetic geomembranes connected by flexible strips of geomembrane. Adjacent rolls of Ciberon mat are connected underwater by means of a special heavy-duty watertight zip. The Ciberon mat is filled with the cement grout, provide ballast, and avoid dragging by the flowing water. The lower geomembrane provides water tightness The upper geomembrane confines the grout. The grout will also provide extreme long durability to the system, protection against vandalism, so that no maintenance is required over the years. The components of the Sibylon mat are illustrated in this picture with the upper and lower geomembranes and double Sibylon C perforated strips as interlayer connection. The fabrication of the Sibylon mat occurs in a factory by providing 2-meter wide Sibylon CNT as lower layer and an upper layer of Sibylon C geomembrane. The Sibylon mat is fabricated in a factory. 2 meters wide roll of geomembranes are welded together, forming a 10-meter wide panel of Sibylon mat. As already mentioned, the adjacent rolls of Sibylon mat are connected underwater by means of a special heavy-duty watertight zip. Here we can see a roll ready for shipment at the factory. After underwater placement on the canal existing lining, adjacent connected Sibylon mat panels are filled with the cement grout to provide ballast and avoid dragging by the flowing water. On the left, we see the watertight zip, and on the right, the Sibylon mat panels are filled with grout. This video shows the installation of the Sibylon mat at Ismailia Canal in Egypt. This is Ismailia Canal in Egypt. The rolls taken to the site, prepare for deployment, insertion of the zip, the special machine deploying the rolls in the water, all activities controlled by remote with the camera. The roll has crossed the canal and reached the opposite berth. The zip is checked. Grout is prepared and pumped into the mattress. And this is the work complete. Thank you very much for your attention.
Thank you, Alberto. It was quite interesting to have this complete overview.
Thank you very much.
So now we come to the last presentation of this morning, of this session, by Mr. Xie Wandong, who is going to talk about a case study on underwater inspection method for tail race area in hydropower station. Please, Mr. Xie Wandong. Can you unmute yourself, Mr. Xie Wandong? We cannot hear you. You have to unmute your mic.
Can you see my screen?
Yes, we can see your screen and we can hear you. Can you put that in presentation mode? Yeah, perfect. Thank you.
Yes,
Go ahead.
yes. Okay. Now I begin my speech. So, Mr. Chairman, dear colleagues, ladies and gentlemen, good morning. I'm Xie Huaidong from the Three Gorges Corporation. And first of all, it is my great pleasure to have the opportunity to attend this annual meeting, especially during this corona time of COVID-19. And I hope that all of you be well and safe every day. The theme we will discuss today is case study on underwater inspection method for terrestrial area in hydropower stations. And 4 parts will be shared in my speech. Part 1 is the background. Part 2 shows us a brief introduction of some common underwater inspection methods. Part 3 covers relevant field cases, and finally, a simple conclusion and prospect is given in Part 4. First, and I will show you some background information. Nowadays in China, there are nearly 100,000 hydropower stations, which of course gives a great promotion to the economy. However, more than half of them have been operated for over 20 years, and no systematic information inspection about the hydraulic structures has been carried out, especially the underwater parts. So given all consideration, it is urgent and necessary to inspect the underwater parts and make corresponding maintenance plans based on the results. Okay, the part 2, so far, the commonly used underwater inspection methods are underwater TV, air diving, remotely operated vehicle, and multi-beam sonar. The working depth of underwater TV can reach 150 meters, while air diving can only reach 60 meters. And the remotely operated vehicle can reach 300 meters. The three methods are all suitable for clean water area. Underwater TV and air diving are used when the flow velocity is no more than 0.5 meters per second. And ROV can be used on the 2 meters per second. And also we can see some difference in the working way that you can see in this table. Mountain beam sonar has a wide range about the water depths, and it can reach as deep as 11,000 meters. This method can be used in various water environments, and it is suitable when the flow velocity is no more than 5 meters per second. This method usually works with a moving carrier like a boat or a robot. In part 3, and I will introduce the underwater inspection cases. In 2014, an underwater inspection was carried out in Three Gorges hydropower station, and a new method suitable for terrestrial area was proposed after this inspection. So guided by this method, the underwater inspection in Gezhouba hydropower station was carried out in 2016. And in the right of this page, you can see that the first picture is the terrestrial area in Three Gorges hydropower station, and the second one is the terrestrial area in Gezhouba hydropower station. Part 3.1, underwater inspection in Three Gorges hydropower station, and in this subpart, you will see three phases of this underwater inspection: the overview, the process, and the results. In the overview phase is that it has been more than 10 years since the operation of the Three Gorges hydropower station, and no detailed underwater inspection has been carried out in the terrestrial area. And in order to ensure the hydraulic structure's safety, find out defects in time, and provide basic data for later inspection, an underwater inspection was conducted in 2014. The process of this inspection is that, in general, the units cannot be fully stopped for an underwater inspection, and in this area, the water inspection is in turbulent condition. And at the beginning of the inspection, remotely operated vehicle was put into operation, but that couldn't be carried out because of the water regime, which meant the ROV could hardly be controlled and couldn't ensure the quality of the underwater inspection. So as the underwater TV, and after many field tests, it was ideal to use the multi-beam sonar with the aid of air diving. The results of the inspection showed that the shape and scope of Terrier's area were consistent with the design drawings. The concrete surface in this area was basically intact without obvious uplift and collapse. The overall condition was good, and the three-dimensional image of number 7 and number 16 unit was shown in this page. The inspection results and basic data were easy to see. So part 3.2, the underwater inspection in Gazhaba hydropower station. And of course, in this subpart, you will see three phrases. The first is the overview. The Gazhaba hydropower station was built in 1988, and no comprehensive inspection was carried out in the terrace area from the beginning of its operation to 2016. From January to April in 2016, referring to the previous underwater inspection, multi-beam sonar was mainly used and relevant equipment were fixed on a working sheet. The results of this inspection that from the pictures in this page, you can see that the terrace area of Gazhaba hydropower station was in good condition. Due to long-term scouring, the maximum scoured pit had formed in some area with a diameters of 6 to 10 meters and a depth of 2 meters. And this it can be seen in the left picture of this page. The phenomenon of scouring did exist in some area of terrace area, but the overall topography in terrace area didn't fluctuate much. And finally, we come to the last part of the conclusion. The results of the two inspections show that the shape and scope of terrace area were consistent with the design drawings. The concrete surface of terrace area was basically intact, and the overall condition was good. With air diving, multi-beam sonar can clearly show the underwater situation in terrace area and meet the requirements of regular inspection. And also, through some improvement, this method can also be used in other areas where have similar flow conditions with terrace area. And that's all my speech, and I hope you enjoy it. Thanks for listening.
Thank you very much for this presentation. I know that we are 10 minutes late, but still there are some interesting questions in the chat. So if everybody can stay on, and we can maybe take some of the questions that we have in the chat. And the first question I would like to take is for Mrs. Sasikala. Are you still there? Mrs. Sasikala?
Yes, sir.
Okay, there is a first question for you. I don't know if you have seen it, but this is a question from Mr. Zakir Hussain. And he asked if there are some vertical joints in the dam, in the Solaya Dam. And if yes, if you have done some treatment for this vertical joint, for this between the blocks. Can you take that up?
Yeah, vertical joints. We have the construction joints between two blocks. No?
Okay. And the question is what kind of treatment you have done, if you have done such in a particular way of these vertical joints. or you treated those joints like you treated also the other ones that you had, right? Are you still there?
Block between two blocks, that is transverse as well as vertical joints were identified, and we conducted the sonic tomogram study.
Okay. Thank you. Pardon, yeah, je vous en prie. Madame Aubry? Hello. Okay. Maybe we can come back to this question if there is still a comment to be made. The other questions that we have are maybe more for Mr. Kanapa and Mr. Soto Ushida, and there are a few of them. One relates to the limitation that we have on applicability of ROV, depth, turbidity, and so on. So who wants to answer first, Mr. Sota Ushida and then Mr. Kanapa?
Yeah.
Yeah, go ahead, Mr. Kanapa.
Yeah, so so I think I have gone through most of the questions. I have typed in some of the answers also. So generally about the limitations, what we see is mostly about the human brain, I would say, or the tactile capability of man that he can decide upon when he's actually going through some of the, I would say, vertical or this kind of cracks or joints, mostly when there is some dust filling happening, but there is actually loss of material in behind it. Human divers can actually send their hands or like clean them, and like that he can decide upon what is at least the next level of inspections to be done along with the dive. But that's one of the key limitations we find when we execute that. But once we repetitively execute this kind of inspections for the dams, we understand that what is the kind of problems that can happen, and we can accordingly improvise the ROV system specifically for that situation. That's one thing. And secondly, on the depth, we don't expect it to be a major problem. So we have executed up to 300 meters. So that's naturally possible. And yes, tether, that is the cable, is one serious limitation. But I said that over the period of time, with improvements in communication methods, we may be able to. But as of now, they are a key element in the ROV industry, and cables are mandatory when you want to get the live feed of the video and want to control it lively to get the best images of your areas of interest. But yeah, we have actively employed our piloting methods in very I would say experienced way, that we don't get them into that entanglement situations. There are very strategic ways to place the systems, where to place and how to manage the cables or the tether so that you don't get entangled. So that's on the ROV system. And I think I have seen another question also on the reptiles infestation. Yeah, very true. India has many dams where crocodiles are very common, but we have actively employed our ROVs in those systems, and we haven't got any, I would say, attack from reptiles immediately. And also we can employ, I think, in shark infested water, such methods are employed, wherein you send in some small electric pulses around the systems to deter them. So that can also be employed if needed. But as of now, we haven't had any issues with crocodiles, and also in snakes in most of the waters we have. Yeah, that's from my side.
Thank you. Mr. Sota Ushida, there are also some other questions. For example, if you can operate around the intake areas. Do you want to comment on that, Mr. Ushida?
And the limit is 100 underwater.
100 meter. 100 meter underwater.
Yeah, okay. And there was a question if you can operate the ROV in the area of intakes where there are some suction forces. Mr. Kanapa, do you want to comment on that?
Yeah, surely I will add up to that. So we have been actively working in that intake zones, particularly think what they are trying to share is about the stop of production particularly. So, but yeah, it's a real challenge to operate in intake areas when it's actively flowing. So, we always advise a fully closed gates to operate the systems, because the sections are quite high to operate in fully opened and intake zones. So we always operate at fully closed gates only, but we can very well plan the operation that we just limit it to like very limited hours. We have executed very large trash gates, also intake gates areas inspection within like 2 to 3 hours with a proper planning. So we can reduce the time of closure, but it has to be closed. That's the present situation of our systems, at least for the ROVs, because there is a very high chance, a definite chance of getting sucked totally into the tunnel or into the penstock.
Okay, thank you very much. There is still another question, which question if you have to plan in advance exactly what path the ROV is going to take, or if it is an online conduct of the ROV, and obviously we can do both. Does anybody still want to add something, to bring a comment on today's session? Please go ahead. It seems like it is not the case. Then I want to thank everybody. I want to thank also the organizers who have managed the session. And I wish you a good day. And I think the next session will start in 10 minutes. Thank you very much and have a good day. Bye-bye.
Thanks, George. Bye-bye. Thank you all.
So the organizer, is that okay?
Yes, sir, it's okay.
Good morning. My name is Ed Thompson, and I'll be presenting live. I'm the fifth.
Good morning.
Good morning.
Yes, sir. Now we are ready, sir. Please proceed.
Let us start the session.
Yeah, sir. We are go live.
Okay. At the outset, I am thankful to the Icold for giving me this opportunity to be the chairman of the session. It is my pleasure to welcome all the participants for today's session of this Icold Symposium on Sustainable Development of Dams and River Basins. I also welcome all the eminent speakers and guests from all over the world from different walks of life who have come here to share their knowledge and vast experiences. The session is dedicated to rehabilitation technologies to enhance dam safety, focusing mainly on modernization, optimization, and rehabilitation of aging dams. In view of climate change, dams and reservoirs will have to play an even more important role as mitigation and adaptation infrastructure by way of creation of adequate storage in order to satisfy the vital needs of water, energy, and food. In the present time, constructing a new dam is very challenging given the population density and intensive land use, as also a host of other factors. The sustainable dam safety management, therefore, is very essential to ensure water and food security. The safe operation of dams and reservoirs through latest dam safety concept is the need of the hours to comprehensively address the dam safety management. I think everyone can imagine the devastation that might happen if the dam gives away in absence of much required rehabilitation and improvements. There are thousands of large dams in India which play an important role in ensuring the water security of the country and constitute a major responsibility in terms of asset management and safety. More than three-fourths of these dams are at least 2 decades old. Rehabilitation of the dam aims at restoring and distressed dam not only to its original state but also aims at improvement to meet added requirements caused by changes in the safety criteria from time to time. Now, since the time is limited, let us start this session. First of all, I welcome Mr. Cyril Godex on this topic of deployment of a fiber optic leaks and seepage detection system below a waterproofing geomembrane on Upper Bhavani Dam. Welcome. First speaker, please.
Yes, thank you. Good morning. I think the pre-recorded presentation. Good morning, ladies and gentlemen. I am Cyril Guido, and on behalf of EDF, CARPI, and Geofi Consult, I will tell you a few words about an ongoing deployment of a fiber optic leaks and seepages detection system below waterproofing geomembrane on Upper Bhavani Dam. I will start with a little bit of context, then I'll move to the experimental demonstration of the system efficiency, and I'll then focus on the design and installation of such a system on the Upper Bhavani Dam. So what's the context? As it is well known, waterproofing using geomembranes is an efficient and cost-effective alternative to repairing and reinforcing old dams. However, uncovered geomembranes are vulnerable to mechanical impacts and hence potentially subject to leaks. It is therefore of great interest to equip geomembrane with low-cost systems capable of detecting and locating leaks. Fiber optics are good candidates for this application because they are a key component of high-performance distributed thermal and strain sensing system, allowing to measure temperature every 20 centimeters with a 0.1 degree accuracy. So, how can such sensors be used to detect leaks behind geomembranes? Well, this is simple, by locating thermal variations induced by leaks. In the case of geomembrane, there is usually only little thermal contrast between the water and the inner face of the geomembrane. Fortunately, it's possible to induce an artificial temperature contrast by heating the measurement cable. If a leakage would cross the cable, it will cool it locally and will be detected. This measurement principle was experimentally demonstrated in 2018 on a test dike in France. The setup was funded by EDF and consisted in first an existing experimental dike equipped with a geomembrane provided by CARPI, and secondly a heat pulse method fiber optic monitoring system installed behind the geomembrane by Geofi Consult. The measurements cable are made of copper wire for heating and fiber optics for measurements. They were fixed to the geogrid with plastic collars between 2 layers of geogrid, then covered with the geomembrane. You can see here the top view of the dike. The crest is at the bottom. You can see that there are 2 entry points for water. First, a simple cut in the geomembrane approximately 10 centimeters long, and a pipe for injection of water under the geomembrane at controlled flow rates. Of course, there's the pump to dry the inner surface of the geomembrane between tests. So the system measures temperature variations called DT. The DT profiles may vary spatially. So a reference DT, let's call it DT ref, has to be measured before and is systematically removed from the measurement. Furthermore, some technical parameters may vary from one measurement to another. To overcome this small variation, the calculated DT profile are systematically corrected by adjusting their average and their standard deviation to those of the reference measurements considered. The DT value of a given heat-up are then subtracted from the DT ref recorded at the same position during the reference heating. We then have the measurement called delta DT, that is DT ref minus DT, and it's computed for every point along the cable. This is, strictly speaking, the detection parameter of the active method. We apply a detection threshold to focus on specific points. At last, an additional parameter called detection intensity is computed from delta DT in order to quantify the leakage. You can see here the detection parameters evolution during 4 consecutive tests at different flow rates. All the leakages greater or equal to 1 liter by minute were detected, as you can see. You can notice that the greater the flow rate, the higher the detection parameter. This is obviously the same for the detection intensity, as you can see here. I would like to draw your attention on the relatively small flow rates tested here, only 0.5 to 10 liters by minute. As we saw, leak through geomembranes inducing water flow greater than or equal to 1 liter by minute can be detected, localized, and quantified with this system. This result can directly be applied to operating structure because first, the detectable leaks are smaller than the leaks that are commonly tolerated on real dimes, and secondly, the cost of such a system remains affordable, especially when compared to its benefits and to the other costs of waterproofing operations. That's why Carpi decided to deploy this system on the Upper Bavani Dam. A few words about this dam now. It's a masonry dam located in the Nilgiris district. It was considered as a distressed dam in 2005, with typical leakage of 8,000 liters per minute, with water level 8 meters below the full reservoir level. Several repair attempts were made, but none could provide a long-lasting permanent solution. So the lining of the upstream face was foreseen with the Carpi Sibilan geomembrane. For the record, the same lining was installed on Kadamparai Dam in 2004 and 5, and the leakage was brought down to nearly 35,000 liters per minute to nearly 100 liters per minute, and it is still in service. You can see here on the picture that the optical fiber measuring system was designed with 4 fiber optic cable loops located above the geomembrane. The lower measurement line are located above the drainage gallery. Because the works have been planned on 3 years, the cable will have to be cut into pieces before the installation of each work area. Then they have to be spliced in order to restore the optical continuity of each measurement line. As a consequence, 8 waterproof optical connection boxes will be installed under the geomembrane. At last, 4 optical connection boxes and 1 heat command rack will be installed in the crest of the dam, housed in 4 concrete shelters. And finally, the monitoring system will include 1 measurement device and 1 power supply for the device, for the measurement device itself, and for the heat command rack. The cables will be heated at approximately 6 watt per meter, and the measurements will be performed first before the impoundment of the dam, that is the reference, And then each year, or in case of increasing leakage, is measured in the drainage gallery. So you can see here several pictures of some steps of the installation of the ongoing installation. After the surface preparation, the cables are laid along the surface, then the protection joint is installed and extra lengths of cable are preserved at the top of the and at the bottom of the installation area. After that, the cables are fixed every 2 meters and the metric inscription are read on the cables in order to precisely know after covering where exactly are the leaks that should be detected. After the cable installation, the geomembrane is deployed and the integrity of the cable is checked from the upper end of each cable. Then the lower end is protected until the next work phase. Installation for the first phase started in May for the first year and carried out until mid-June 2019. Then monsoon started. The second phase of installation started next year in March, continued till May, in spite of the COVID-18 pandemic. The entire installation is now programmed for the third phase, scheduled to begin from middle of February this year and complete by mid of June this year. The entire dam has been divided into 4 segments, while the top left, that is 20%, has been completed in the year in the first year. The top right was completed in the second year. The
request for wrap up, please. Be fast. Request
is planned for installation between middle March and mid-June this year. The optical fiber cables will be positioned in the vertical section between the crests and the position where the cables takes a horizontal path. Wherever there is a break in between 2 seasons of work, a special connection box will be provided to ensure connectivity between the 2 sections of the cable. From the contractor point of view, the entire scope of work is designed and getting installed well within the contracted price as stated in the agreement. The ongoing success of this project in Upper Valley Dam is largely attributed to the meticulous design and planning of the fiber optic system in such large dams. As a conclusion, we can say that fiber optics equipped with heating units are accurate and cost-effective, and cost-effective systems capable of detecting, locating, and quantifying leakages and slippages below geomembranes. I thank you for your attention.
Very interesting topic. Fiber optics are generally known as excellent telecom cables, but they can be used as competitive thermal or strain sensor when properly instrumented. One of their extremities, they enable to measure the temperature, strain all along their path with a very high precision. This ability of fiber optics to actually detect and locate leaks below geomembrane, a very new experiment. I hope it will go a long way in the seepage detection. Very extremely, new and wonderful topic for all of us. Any questions, please? Other speakers, listener, they won't have any question. Okay, now may I request the next speaker, Mr. Andre, for the topic application of a granular filter for the rehabilitation of the primary food defense at Gamden.
Yes, I have a pre-recorded video. So
I request this presentation may be contained in 10 minutes.
And thank you for watching.
Thank you.
Solution is on a granular filter for the rehabilitation of an existing flood defense at Gameren in the Netherlands. First, I'll present something on flood safety and the role of dikes and levees. Next, a short reminder of what backward erosion piping is. And then the main is a innovative solution against backward erosion piping problems, the core sand barrier, which is basically a filter with spontaneous drainage formation. It is to be applied later this year at Gameren, a village along a branch of the Rhine River. I'll illustrate the safety problem and discuss some alternative solutions. Material selection for the core sand barrier and the modeling and safety approach. And I'll end with some conclusions. Flood safety, for example, for the Netherlands is of significant importance, at least in a low-lying country like the Netherlands. More than half the country is protected by levees. Some protect against the sea, some against rivers, and some both. And in the future, we are expecting sea level rise, climate change giving more flow on the rivers, especially in winter, and land subsidence, which also doesn't help, of course. Some examples of levees in the Netherlands, they're always on a sandy foundation. Sometimes they're built long ago, like the example to the right, at the village in Arnhem-Muiden in Zeeland, where the levee was originally quite small, but later on it has been heightened and at present is of significant heights and well protected against overflow and overtopping. But the backside of it is that of that higher head, which can be sustained, that failure mechanisms like the backward erosion piping problem come into place, which is a problem for about 1/3 of the levees in the Netherlands. Backward erosion piping is illustrated in 6 steps with pictures on the sides. It starts with some seepage, and as the water level rises on one side, a pipe will form visible by sand boils. And then invisible will be the retrograde erosion, the pipe extending towards the water sides, followed by widening of the pipe once it's connected to the outside water. And then at some point you'll get failure of the levee, followed by breakthrough and a big problem. And excuse me, the Icold has produced a bulletin to address this type of issues in a way by using a filter accompanied by drainage. And we derived a new solution especially to be applied at existing levees where the situation has become problematic because of the heightening of the levee, and where the existing situation is you get piping at some water level outside, and the pipe will easily extend towards the water sides as long as the head is further increasing. You have a significant gradient right at the head of the pipe, and this line will only move to the riversides until you have a problem. The coarse sand barrier, you place a barrier made of coarse sand, which is extremely highly permeable, and you put it on top of the near the top of the aquifer, slightly inside the blanket layer, and then you get a situation that a pipe arrives. It will split in both ways because the background sand will be eroded more easily. You get a rather small gradient inside the highly permeable coarse sand barrier, and the upstream parts you get the most part of the head difference, and as a result the total head can increase significantly. If you make your levee out of soil, it will only fail in most cases when the water level is already higher than the crest of the levee. So piping will not longer be an issue then. How do we model a coarse sand barrier? Basically, the final problem occurring in a barrier is heave. First, the pipe arrives at the coarse sand barrier from the downstream sides. The upper parts, which is originally filled by coarse sands, will be transported away. You get some pavement on the bottom of the channel, which causes some extra resistance, but that is only of minor importance. The most important thing is that you get a slope in the sand, which will flatten a bit because of the outflow inside the slope. And at some point, this will liquefy, and then your barrier fails, and after that, the whole apparently the video has stopped.
Hello. क्या हुआ क्या?
Can you please continue playing the video?
Yes, please continue. Yes, please continue. There was some internet problem, technical problem. Please continue.
The host has to restart. Yes, over there. Please restart.
Please continue. We are listening. Please continue. It's a very interesting topic.
Corner, you can press on play again.
There was some technical problem. Please continue.
The video was at 7 minutes, 10 seconds. With erosion piping problems, sand barrier, which is basically a filtering flood defense at Gameren in the Netherlands. Okay, please move forward. I'll present something on flood safety and the role of dikes and levees. Next, a short reminder of what backwards erosion piping is. And then the main piece, a innovative solution against Post, can you please put it at 7 minutes? The coarse sand barrier, which is basically a filter with spontaneous drainage formation. It is to be applied later this year at Gameren, a village along a branch of the Rhine River. I'll illustrate the safety problem and discuss some alternative solutions. Material selection for the coarse sand barrier and the modeling and safety approach. And I'll end with some conclusions. Flood safety, for example, for the Netherlands is of significant importance. At least in a low-lying country like the Netherlands, more than half the country is protected by levees. Some protect against the sea, some against rivers, some both. Mr. Bansal, we've already had this. Shall I try to share my screen and climb to the point where it was interrupted? Rivers, especially in winter.
Please continue.
And landslides, which also doesn't help, of course. Some examples of levees in the Netherlands. Can you see my presentation there, Mr. Bansal?
Yes, please. I'm listening, and it's very interesting topic.
Yes, I'm trying to get to the. I don't see what is. No. Trying to get to the right sheet. Yeah. So we model it as heave, and then we apply it at the village of Gameren. There's a very old levee, about 6 centuries old, which was not good anymore, and it could not be raised or improved anymore because of the presence of the village. So a new levee was built, but unfortunately they made some mistakes and they have improved it. And looking at the current seepage deficits, using the traditional method of applying a berm, at some places you need a berm over 100 meters. A sheet pile wall could be an alternative, or a coarse sand barrier. Here, the innovative solution of a coarse sand barrier has been applied. A berm, as you can see, takes too much space and volume of sand. Here you see the sieve curves of the background sand, and of course, to achieve a good filter, you have to fit within some constraints given by the filter rules. We apply the traditional filter rules of Terzaghi to remain on the safe side. This is not a place to use geometrical open filters. And then we have a safety approach. The coarse sand barrier heave occurs with the applied density at a maximum gradient slightly over 1. Then we apply a partial safety factor for heave at rigid structures with densified sand. there might be unfavorable three-dimensional flow when close to the barrier there's a obstruction in the underground by which the lateral growth of the pipes at the background downstream side of the barrier is impossible, then that could be a factor of 3. We usually apply a safety factor for potential difference between model and reality. We have a lot of information on reality here, so we can apply a rather low factor of 1.1. And then the permissible calculated gradient becomes, well, 0.19. And calculated at 10 different sections, we get a lower value of what is actually to be expected. So concludes it is safe. And then it provides a solution. It is economic because only little material is required. Material can be obtained by sieving natural sand, so not using any plastics or whatever, or steel. Construction depth is limited. The required equipment is readily available. Recently, we performed construction tests. Drains need not be constructed because the initial piping process will provide the drainage which we need. And in the laboratory, we've done tests on different scales with a maximum head of close to 8 meters. And yeah, it functions, so it works. And thank you for your attention. Here are all my co-workers who worked on this development.
Thank you, Mr. Henry. Very interesting, very informative. And this is a pilot application of core sand barriers, promises to solve the significant flood safety gap related to backward erosion piping. The presentation was very informative and indeed very interesting. So we felt as if we are sitting in the Netherlands, and we have been enlightened by your paper. Any questions, please, from other listeners or the speakers? Thank you very much. Now let's invite the next speaker, Dr. Jurget, on the topic of Mosul Dam. Next speaker, please.
Hello, I'm Dr. Georgette Kleppes, and I will be presenting on behalf of myself and co-authors, Mr. Bill Empson and Ms. Vanessa Bateman from the U.S. Army Corps of Engineers, as well as Mr. Mohammed Samadi of the Ministry of Water Resources in Iraq. Now, many papers and presentations have been produced concerning Mosul Dam, but none, to my knowledge, address the final outcomes of the project after 3 years of emergency drilling and grouting work, and that is the focus of this presentation. I will start with a brief overview and background of the project, and then talk about the work performed, what we learned during our time on site, and how our understanding of the project changed over time. Mosul Dam is located on the Tigris River, 50 kilometers upstream of Mosul and 350 kilometers upstream of Baghdad. The dam is the largest dam in Iraq and the 4th largest in the Middle East. The goals of the project are to provide significant water and irrigation supply, flood control management, hydropower generation, and environmental benefits to Iraq. The full storage capacity is 11.1 billion cubic meters, and the dam's main features are shown in the aerial image. Near the right abutment, there's a hydropower facility as well as the outlet works, and in the left abutment are a service spillway, saddle dam, and a fuse plug emergency spillway. The embankment dam was completed in 1985. It is considered a well-designed earthen embankment dam with relatively modern design features. The 2.21 kilometer long and 113 meter tall structure was originally designed by Swiss Consultants Group and was constructed by the German-Italian Mosul Dam joint venture. The dam is currently owned and operated by the Government of Iraq Ministry of Water Resources. This slide shows a generalized cross-section of the dam. It includes a relatively wide impervious core along with the chimney filter and drain, as well as a downstream towway. But one very unique feature that I want to draw your attention to is the grouting gallery located along the center of the dam at the base of the core. The designers included this feature to address the dam's very problematic foundation. This grouting gallery begins under the surface spillway in the east abutment and extends to the west abutment. It is meant to facilitate continuous foundation grouting. This is because the bedrock that makes up the dam foundation consists of a very complex geology and includes layers of gypsum and anhydrite. The gypsum and anhydrite are especially susceptible to solutioning over time and have the potential to form solution cavities. The bottom right image on this slide is an illustration of what could potentially form if the foundation were to go untreated for an extended period of time. As the cavity features form and grow larger, there's potential for the materials above to collapse in and material to be able to flow in. This raises a concern of the potential for internal erosion of the embankment materials through the foundation. The top left image is an illustration of the potential failure mode leading to an uncontrolled release of the reservoir. Continuous maintenance grouting was incorporated into the original design of the project to protect the dam from this particular failure mode. Over the past decade, armed conflict in the region resulted in shortages of equipment, materials, and manpower at the project site. This resulted in periods of decreased levels of maintenance grouting and periods where no grouting was performed. In addition, there were identified signs of distresses such as surface depressions and sinkholes near the footprint of the project. To further complicate matters, one of the two bottom outlets was inoperable due to a damaged gate position indicator rod, which greatly reduced the capability to quickly lower the reservoir in case of an emergency. Now, the two images on this slide are of cave features on the right abutment of the dam. They're outside the dam footprint. While this cave does not pose a threat to the dam as it is too far in the west abutment, it does represent what the foundation could look like without intervention by grouting. Features even a portion of the size could readily convey substantial flow of materials. Were interconnected solution features to exist that connected to the embankment, especially with relatively high reservoir levels, there could result a catastrophic event. A breach could occur with relatively little warning and with a large population on the downstream. There could be substantial life loss and economic impacts, especially since the dam provides a significant portion of the country's drinking and irrigation water supply. The foundation conditions, distress indicators, reduction in maintenance grouting activities, reduced capacity of the outlet works, and potential consequences all raise concerns of an increased risk of dam failure. In 2006, the media had publicized the conditions at the dam and referred to the dam as the most dangerous dam in the world. In 2015, the U.S. Army Corps of Engineers evaluated the project in accordance with international and U.S. dam safety standards. It was determined that the dam would be assigned a U.S. Army Corps of Engineers Dam Safety Action Classification of 1, very high urgency. This classification is assigned to those dams where progression towards failure is confirmed to be taking place under normal operations. At that time, the risks were driven not only by the potential performance of the foundation, but also by the exceptionally large downstream population at risk. In 2016, the government of Iraq contracted with the Italian firm Trevi to address the concerns of the project. The U.S. Army Corps of Engineers was requested by the Ministry of Water Resources to be the engineer of record and oversee the contract, and we were on site until April 2019. The multi-party team aggressively worked to complete as much work as possible to provide a robust foundation grout curtain across the dam foundation and restore the bottom outlets to full capacity. With the work came a vast amount of state-of-the-art equipment for not only grouting, but also for performance monitoring. A vast instrumentation program was completed to ensure a skilled workforce and engineering team was prepared and fully capable of leading Mosul Dam and the Ministry of Water Resources into the future. The 3-year effort on site resulted in over 4,800 holes drilled and grouted across the dam. That's nearly 350,000 meters of drilling. Over 39,000 cubic meters of grout was placed into the foundation. That is more than the last 13 years combined and equal to about 1.3 times the size of the Washington Monument. This was primarily used for the application of staged pressure grouting technology at depths, as opposed to the surface grouting that was previously performed. By the end of the project, we reestablished 2 continuous grout lines across the project and added additional lines at critical locations. In addition, the outlet works were restored to full operational condition. The result also included an understanding by the U.S. Army Corps of Engineers that although the foundation conditions are complex and problematic, the Mosul Dam should no longer be referred to as the most dangerous dam in the world. As active operation, rehabilitation, drilling and grouting, subsurface exploration, and monitoring of the dam was ongoing, the U.S. Army Corps of Engineers worked to better characterize and understand the project design, condition, and current associated risk. An improved understanding of the quality of the original design and construction, foundation conditions along the dam and on the downstream, and the effectiveness of the emergency grouting efforts and on-site work at the bottom outlets led to a better evaluation of the risk at the dam. At the start of the project, minimal information was available, and the earliest assessment assumed that there was little to no effective treatment of the foundation. After time spent on site, additional historic records were obtained and thoroughly reviewed. It was learned that the project was very well designed and constructed to address internal erosion concerns. Not only were appropriate materials used for embankment zones and filters, but there was an extensive foundation treatment and an aggressive initial grouting program. The foundation rock under the core was completely exposed during original construction, and extensive treatment, including dental concrete, slush grouting, blanket grouting, and the initial grout curtain were all performed. The original designers were located, and they were able to confirm the design and the construction of these features. This additional information was a key factor that influenced the latest risk assessment of the dam. Also early in the project, there was understanding that there was a higher risk of internal erosion through undissolved gypsum layers at or near the base of the embankment, or where there was significant brecciation of gypsum. The drawing on this slide is a profile view of the dam looking downstream along the center line. The primary areas of concern are near the embankment contact and are identified as GB1, GB2, and GB3. The original designers tried to capture the difficulty of explaining the heterogeneous condition of these GB layers by drawing a karst line. This karst line was a 2D dividing line between what was judged to be the more intact materials below the karst line versus altered, more brecciated layers above the line. Higher grout takes were expected near the karst line and where it was drawn. Exploration, as well as drilling and grouting during the 3-year emergency drilling and grouting program, provided a much better appreciation for foundation materials, historic grouting efforts, and the nature of void spaces. The recent work performed revealed that the foundation condition had been changing over time. The karst line has been redefined and is now evidenced to have moved westward, indicating that dissolution was ongoing. Repeated historic episodes of grouting have interrupted the karst network development. However, the emergency grouting program showed that the ground was still accepting grout despite the amount that had been put in previous programs. Modern understanding of karst development in gypsum supports the hypothesis that this karst development will continue until the gypsum anhydrite is completely solutioned or removed. The emergency grouting efforts yielded significant grout takes and identified variable-sized openings in the foundation. However, the results of the verification program indicated that the foundation along the center line of the dam was of low permeability and satisfactory performance. This was verified by water pressure tests, coring, borehole televiewer results, and upstream and downstream piezometer readings. The image on this slide shows that the results of the verification hole before and after grouting. It clearly shows the presence of grout post-grouting activities in the bottom image, in the cavities that were present prior to grouting in the above image. Now that I spoke on the foundation conditions along the center line of the dam, I want to discuss the foundation conditions on the downstream side of the dam. Little information outside the dam alignment was available at the early stages of the emergency grouting program. Given the heterogeneous nature of the foundation layers, this resulted in significant uncertainties as to the condition both upstream and downstream of the center line. Additionally, the extensive foundation treatment under the core footprint was not applied across the rest of the dam. Further, there were known depression features of the downstream left abutment shown in the picture and near the bottom outlet alignment downstream. During our 3 years on site, 52 exploratory holes were drilled. Many of the holes were drilled near the known left abutment feature, while others were concentrated along the bottom outlet works. Both these areas revealed voids up to 6 meters in height during operations. Drilling and grouting efforts were concentrated in these areas to determine the extent of the void features and indicated a complex and hydraulically interconnected network of voids on the downstream side of the dam. These areas were extensively drilled and grouted. Grout takes in the left abutment area were in excess of 900 cubic meters of grout, and near the bottom outlets in excess of 185 cubic meters of grout. Although these areas were treated with grout while we were on site, it was recommended that additional drilling and grouting be performed post-emergency drilling and grouting. because it's uncertain how far and how many more cavernous types of voids may exist. In addition, instrumentation indicates that the downstream foundation is nearly instantaneously responsive to tailwater fluctuations. This is indicative of a very permeable downstream foundation. However, there are multiple mitigations for internal erosion in place, including the foundation treatment beneath the dam core, a satisfactorily performing grout curtain, a robust instrumentation and monitoring system, and the downstream tow weight features, which all mitigate the potential for internal erosion. During the time that the engineer was on site, the record low lake level occurred and a 15-year record high lake level was experienced. The spillway was operated for the first time in 15 years and twice in the 3 spring seasons. In addition, the bottom outlets were both tested to full capacity. The dam performed satisfactorily to up to lake levels that were 4.8 meters below full storage. As of the final evaluation of the dam performance completed in April 2019, the Corps of Engineers determined that the dam was in full operational condition and the foundation was stabilized. Original design and construction features, in combination with the extensive foundation treatment and other construction recently completed, contributed to the current stability of Mosel Dam. The future stability of the dam is dependent on continued grouting and dam safety monitoring by the Ministry of Water Resources. The ministry has all the skills and state-of-the-art tools necessary to be fully effective at both grouting and monitoring of the project. Appropriate budgeting and effective procurement and management will also be critical to the project's future. Currently, the dam presents a much lower risk to the downstream community than it did in 2015, and the label of the most dangerous dam in the world is not applicable. Thank you.
Excellent. I hope this Mosel Dam is no longer the most dangerous dam in the world. I have just 1 or 2 questions for you. Excuse me. 1 or 2 questions for you, please.
Okay.
My first question is, when it was known that the geology of this area is most complex geology, having this limestone and all these things, then why this place was chosen for this dam construction originally? What were the compelling reasons?
Not exactly why they chose this particular location. There was an alternate location they started with initially, and they moved to this final decision in the 1980s. But I don't know why exactly they said it has to be exactly here. But they decided.
And second question is, anyway, it's okay. The second question is, what is the water cement ratio and pressure used for this grout in this soft clay and soft limestone? What was the water cement ratio?
The water and cement.
Water cement ratio.
There was a variety of grout mixes used throughout the project, starting with a very easy to flow light mix, and it increased over the 6 or 7 different grout mixes. I'd have to go back to get the exact grout mix used in the particular soft clay areas.
Okay, any question from the other speakers and participants, please? Thank you so much. It's a well-known to Mosel Dam. I mean, it has remained in great controversies in the country. It was known as most dangerous dam in the world. I hope now with this huge drilling, grouting, exploration of this huge number of holes and this creation of this comprehensive 3-dimensional foundation model, and you have already stated, and I hope this is no longer a world's dangerous dam in the world. Now it is safe. Thank you so much for such a nice presentation. Thank you. Now I request the next speaker, Mr. S.R. Patnaik.
I would, good afternoon, sir.
Good afternoon.
I would request virtual MNC to please run my video. It is there with them. Good morning, everyone. I'm Sangeeta Patnaik, working as Scientist C in Central Water and Power Research Station, Pune. I'm associated with the hydraulic model studies for optimization in the design and layout of spillway and energy dissipators. Today, the topic of my presentation is hydraulic model studies for additional spillway of Hirakud Dam, Odisha, wherein I will discuss about the contribution of CWPRS in evolving the efficient and economical design of spillway and energy dissipator. Hirakud Dam is a multi-purpose project built across river Mahanadi, about 15 kilometers upstream of Sambalpur district in Odisha. It was commissioned in the year 1957.
It's a technical problem.
Dam in Asia having a total length of dam and dike 25.8 kilometers. It is a composite dam of earth, concrete and masonry with the main dam having an overall length of about 4.8 kilometers. There are two spillways, left bank spillway and the right bank spillway. The left bank spillway consists of 40 sluices and 21 overflow, and the right bank spillway has 24 sluices and 13 overflow to pass the design discharge of 42,450. Dam 2 powerhouse is on the right flank of the main dam with an installed capacity of 347 megawatt. Now, the design flood of Hirakud Dam has been revised from 42,450 cubic to 69,632 cubic. So, in order to pass the additional discharge of 27,182 cubic, CWC advised to provide two additional spillways.
Technical
First,
team may please
with 5 spans of size 15 meter by 15
start the presentation. Technical team, please.
Design discharge of 9122 cubic. And the second additional spillway at the right dike with the 10 spans of size 15 meter by 12 meter to pass the design discharge of 13,000 cubic. Now this is the left bank spillway. This is the Gandhi Minar, also known as the Gandhi Hillock. This is the left dike, and this is the left bank additional spillway which has been proposed with 1900 meter long spill channel with a varying width of 120 meter to 200 meter. This is the drop structure at RD 857. The change in the width takes place. Now the project that left additional spillway envisaged the construction of a 33 meter high concrete gravity dam with a length of 203 meter. The spillway consists of 5 spans with a gate size of 15 meter by 15 meter, and the energy dissipator is in the form of a stilling basin. This is the stilling basin with length of 71 meter with chute blocks and dentated end sill. A 1 in 40 scale 2D sectional model was constructed in a glass-sided flume. 1 full and 2 half spans with 2 full piers along the stilling basin were incorporated in the model. The spillway and the stilling basin were constructed in big masonry. The surface was smooth cement plastered and painted with enamel paint. The pier, chute blocks and dentated end sills were fabricated in PVC foam sheet, whereas the radial gates in MS sheet. The piezometers were provided along the center of the span and side of pier for hydrostatic pressure measurement. So this is the tailwater rating curve which was provided at 250 meter downstream of dam access by project authorities, which was used for conducting the model studies. Now the studies for the discharging capacity for the ungated operation of the spillway for entire range of discharges was conducted, and it was observed that the discharging capacity was adequate as a discharge of 10,000 could be passed at MWL as against the design discharge of 9122 cubic, whereas the design discharge could be passed at EL 191.45 meter as against the FRL, which is 192.024. Now, it was observed that the performance of the stilling basin was unsatisfactory for the entire range of discharges, as the hydraulic jump was not contained in the stilling basin due to inadequate length of the basin. It was also observed that the Trunnion elevation of the radial gate was above the water profile, and therefore the Trunnion elevation was found to be adequate. It was also observed that the pressure profile for the entire range of discharges were satisfactory. Thus, the results were the performance of the stilling basin was unsatisfactory as the length of the stilling basin provided was insufficient to contain the hydraulic jump. Velocities were also observed downstream of dam axis, and it was observed that the velocities were very high, and therefore it was felt necessary to increase the length of the stilling basin from 71 meter to 90 meter. It was also recommended to either increase the length of the stilling basin or to adopt optimum combination of increasing the length as well as lowering the stilling basin after witnessing the performance of the modified length of the stilling basin of 90 meter. So both the alternatives were incorporated in the model as alternative 1 and alternative 2. In alternative 1, the stilling basin length was increased from 71 meter to 90 meter with a floor level of 151 meter. And the studies were conducted, and it was observed that the hydraulic jump was forming in the stilling basin for gated and ungated operation of the spillway. The performance of the stilling basin was improved marginally as compared to the original design. Therefore, the length of the stilling basin of 90 meter with floor level of 151 meter was found to be satisfactory. In alternative 2, the stilling basin floor level was lowered by 2 meters, that is EL 149 meter, with length of 90 meter. It was observed that the hydraulic jump was forming in the stilling basin for gated and ungated operation of the spillway, but no significant improvement was observed as compared to the alternative 1. So the lowering of the stilling basin floor level by 2 meter, that is EL 149 meter, was not recommended as it would also be uneconomical. Therefore, it was recommended to adopt the stilling basin of the length of 90 meter and floor level 151 meter, and the same was considered for 3D model studies. 3D comprehensive model was constructed to a geometrically similar scale of 1 in 100, incorporating the existing main dam complex. This is the existing main dam complex with left bank spillway, reservoir portion of 1500 meter, and river portion of 3 kilometer downstream of dam axis. The model also incorporates the proposed additional spillway with a part of the reservoir with 1900 meter long spill channel and river Mahanadi at 300 meter downstream of the dam axis of confluence of left and right limb. This is the varying width of spill channel from 120 to 200 meter. This is the drop structure where there is a fall of 5 meter at RD 857, where the change in width takes place. The energy dissipator is in the form of, that is the stilling basin, which was finalized from 2D sectional model studies were adopted for 3D model studies. This is the closer view of the model. This is the upstream view. This is the left dike. This is the downstream view of the model. These are the chute blocks and dentated end sill. The spill channel with 120 and 200 meter width. And this is the existing left spillway of main dam. This is the tailwater rating curve, which was provided by project authorities. The blue curve shows the rating curve at 200 meter downstream of confluence of additional spillway of and river Mahanadi. The red curve shows the rating curve at 200 meter downstream, and the magenta curve shows the rating curve after drop structure at RD 857. And these rating curves were utilized while conducting the model studies. Now, the studies were conducted for the discharging capacity, and it was observed that the discharging capacity was adequate for the entire range of discharges for ungated operation of the spillway. The photograph shows the performance of the stilling basin for gated and ungated operation of the spillway for 100% and 50% discharge respectively, and it was observed that the performance of the stilling basin was satisfactory as the hydraulic jump was forming in the basin. The approach flow condition near the left and the right draining wall
Request to
spillway, that is
wrap up.
the first and the previous span, were abrupt, causing sudden drawdown condition for the higher discharges.
May I request for speed up?
Observed that the flow conditions at the confluence of the spill channel and the left limb of river Mahanadi were not satisfactory. The flow was spreading at 90 degree at the confluence point and pushing the flow released from the left bank spillway towards the, this is the island, towards the island formed between the two limbs of river Mahanadi downstream of main dam during the combined operation. was also observed that the flow conditions at RD 857 to RD 936.25, this is RD 857 and this is 936.26. The flow conditions were abrupt due to the change, as the change in the width from 120 to 200 meter was abrupt. So the results were that the flow conditions near the left and the right training wall of additional spillway in front of the first and the fifth span were abrupt, causing sudden drawdown condition. Therefore, it is suggested to provide curved guide wall to improve the approach flow conditions in front of end spans. Performance of stilling basin was satisfactory. It was suggested to modify the design of the spill channel by providing a smooth transition of the channel from 120 to 200 meter width so as to guide the flow smoothly from RD 857 to RD 936.26. Flow from the spill channel was hitting the left limb of river Mahanadi in the downstream at 90 degree and pushing the flow towards the island during the combined operation of the existing left spillway of main dam and additional spillway. Therefore, a curved spill channel towards the left near the confluence would facilitate to guide the supercritical flow smoothly at the confluence of river Mahanadi. The design engineers requested to provide drawing for the suggested recommendation, and therefore CWPRS provided study sketches for the proposed upstream guide wall, smooth transition of the structure and alignment of the spill channel at the confluence to divert the flow towards the downstream side. CWPRS also suggested to examine the sketches based on the feasibility of the prevailing site conditions and structural considerations and provide the detailed drawing for the same so that these modifications could be incorporated in the existing 3D model for further studies to ascertain the performance. So it can be concluded that the hydraulic model studies play a significant role in optimizing the design of spillway and energy dissipator. 2D model studies on original design indicated the requirement of increasing the length of the stilling basin from 71 meter to 90 meter to optimize the hydraulic performance of the energy dissipator. With the optimized design of energy dissipator, 3D model studies were conducted for assessing the overall performance of spillway and energy dissipator for additional spillway along the left bank, existing left bank spillway on main dam. Modification for the upstream left and right training wall were suggested to guide the flow approaching spillway smoothly. Combined operation of additional spillway and left bank spillway of main dam indicated the necessity of modification in the design of spill channel at the exit. This combined operation would help in assessing the discharging capacity, effect of flood inundation on the island located between the left and the right bank spillway, downstream of main dam, and flow conditions in the vicinity of the confluence required for adopting the downstream protection works. Thus, it could be concluded that the model studies play a crucial role in enhancing the overall performance of spillway, energy dissipator, and other appurtenant structure based on techno-economic feasibility. Thank you.
Thank you very much. What I understand is the Hirakud Dam is one of the major and oldest dams which became operational in 1957. After reassessment of the design flood by Central Water Commission, the model studies were conducted on 2D sectional and 3D comprehensive models of additional spillways for the additional flood on left dikes of the Hirakud Dam. To assess this discharging capacity of spillway, it was very captivating. A simple two questions if you have on information. One thing is Manning coefficient used for developing the tailwater rating curves.
So it is 0.025. Actually, we see the because the surface is smooth cement plastered, so it the Manning's coefficient is get related with the proto site conditions.
The second thing, what was the criteria used for calculation of the stilling basin length? Whether it was USBR or IS?
USBR.
It was USBR. Okay, yes. Thank you. Any other questions from the speakers or participants, please? Okay, thank you very much. Very nice presentation. Very good, informative. And now may I request next speaker, Mr. E.A. Toms, for his topic on innovative seepage and spillway remedial design of a Puddle clay core dam.
Yes, good morning. This is a live presentation, so I probably could speed it up a little bit to make up some time. But yes, my name's Ed Toms. I'm presenting from Denver, Colorado, so thank you very much for having me today. I looked at several different projects that we could present on, and I selected I believe the most appropriate one that India is facing today, and that's puddle clay core dams, but also related to the innovation seepage and spillway improvements. The project is Continental Dam. It's located in Colorado, about 3,300 meters, so it's a high elevation structure. It was built back in two stages in 1925 and 1928. It's a puddle clay core dam, and obviously back in the 1870s, it was a standard practice between 1870 and 1930s. The issue of puddle clay core dams is the consistency of the placement of the materials. The quality control at that time wasn't very good, and that was the case for Continental Dam. There's no internal drainage system, as you can see. There's a slight one in right by the core, but pretty much not an internal drainage system. They didn't clean off the foundation very well. They didn't get down to bedrock. This material in here is a tough material, so it's volcanic with a glacier till on top of it. So the embankment structure is basically founded on glacial till. The reservoir back in 1994 was restricted by the Colorado State Engineer's Office. The reason they restricted that is because the embankment seepage, there was seepage about halfway up, discharging, and so they restricted the reservoir by 7 meters, which is about 50% of the storage capacity. Plus, they didn't know the actual spillway capacity of the project, plus also the related stability of the structure too, they didn't know about. So then they actually restricted the reservoir. Let's take a walk around the site. In the upper left here, the reservoir seepage. Again, it was founded on founded on tuff and glacial till. The glacial till has different interbedded lenses of clays and so forth. So the other issue up at the top is the slide area. Left abutment slide area is very concerning to the state engineer. And then they had previous consultants look at the project over the last 10 or so years. They had some ideas of how to repair it. They were looking at deep-seated grout curtains, cut-off walls. They were actually talking about liners of the reservoir. What we decided to do is actually try to control the seepage instead of try to reduce it. But the end-around effect through the slide area, through the glacial till was coming in through the embankment, coming out at the downstream of the embankment face. This picture is looking downstream of the embankment face. You can see some of the grass right here. Again, this is high altitude in Colorado, so the growing season is very limited. But the seepage would be coming out right around this area of the embankment. It's interesting, the site access. This is actually, they've placed a road across the spillway. This is a side channel spillway that was heavily damaged by freeze-thaw action, but actually just road traffic. So the owner needed to get to the crest, and so he built the road across it. Obviously, that would be restricting the flow capacity. Looking downstream, it was interesting too, is that when I was out there for an inspection, I took my rock hammer and tapped the wall, and part of the wall fell in. It's just the representative of the condition of the wall due to freeze thaw and just the lack of care. This is another picture. This is the Stilling Basin. The Stilling Basin was just a gravel pit, basically, with some sidewalls. So if it did discharge through here, it would erode this pretty quickly and then possibly back cut into the embankment. This is another picture of the right abutment looking upstream. This is another slide area. This is the other, the spillway chute is very damaged to freeze thaw. And you could imagine if a flood came through here, it would remove these walls pretty quickly, remove the, to remove the slide material, plus also cutting into the embankment. We, the client was is an irrigator, and they're very hardworking people, very practical people, but the technical aspects they weren't too familiar with. And so we had to use a different method at that time. It's standard practice, but it's a risk-based alternatives development approach. We wanted to inform the client on the different aspects technically, bring them along through the discussion and identifying the different possible alternatives, plus also funding availability. We had to come up for the regulators, for the funding people to be able to identify what is the most appropriate repair first. So is it the spillway or the embankment? So we had to deal with the funding availability and the phasing of that. We looked at the different alternatives, reducing again or control seepage. The water is very high value. They preferred to keep the reservoir full through construction. At the end result, we couldn't do that, but we actually went through the process, looked at the risk for each one of those items. The process just quickly, we looked at we gathered available data. The data is very limited. They had a lot of photos, historical photos back in for the 1925-29 construction, but actual drawings, they only had about 6 drawings. So we had to extrapolate a lot. The budget was tight, so we had to sit back again, and we used the SQRA process to identify where the weak data gaps were, and then we focused on those data gaps. We developed the seismic analysis. We also did the stability analysis of seepage and the flood hydrology. We looked at that information, we filled the gaps, and determined that through the different workshops, we dealt with the spillway improvements for the first bid package, and then the second bid package was the embankment improvements. Again, the first package for the spillway was because we felt it was the most critical. If it did discharge water, we felt it would fail pretty quickly. Again, the geology, just in general, it's glacial till over a tough volcanic bedrock. The structure is pretty much founded on about 30 feet of glacial till. There's 3 field investigations that previous consultants did back in 87, 94, and the one that AECOM did was in 2011. So through that, it was identified that the clay core was a silt or a silted clay with layers of fines and coarse gravels. So it wasn't very consistent, very homogeneous, and so that was a concern for us for actual seepage. The flood hydrology that we looked at, it was amazing that once we performed the flood hydrology, that there was adequate freeboard. So it's about 1.3 meters of freeboard on the dam. We had to obviously rehab or replace almost the spillway chute. And so that gave us some leeway of sizing it appropriately. And we'll talk about that in a few minutes. The seepage analysis, we actually looked at different parametrics on the material types. I won't get into all those details, but the existing seepage was 475 liters per minute, about mid height of the dam. So what we did, we looked at the parametrics on the core materials, the shell materials, the foundation. We did different studies, and our end conclusion is that the core was not affected. And that's, for puddle clays, you got to keep them pretty wet, moist, because otherwise they'll dry and crack. So our end result that we just modeled the dam as a homogeneous dam to be conservative. The stability analysis, again, we looked at the different loading conditions. In this case, we just looked at steady state and post-earthquake. We didn't look at a construction, during construction stability, because we reduced the reservoir all the way down to the intake. But based on the analysis, we assumed several filter sizing configurations, abutment sizes, and what we came up with is that we had to add pretty much a filter system all the way up to the high water line, and then also an abutment with a rock filter toe, and we'll talk about that in a little more detail. The spillway was pretty interesting. We wanted to use the existing spillway walls as forms. So we looked at the concrete. We assumed for structural stability, the concrete walls were native soil, so they're just pretty much non-effective. So we looked at the underdrain system and the chute wall heights and the stilling basin. Process we went through is that we saw cut the bottom of the spillway, removed that concrete, excavated down through a trapezoidal shape. We added sand, filter sand, a drain stone, and then a perforated pipe backfilled with the stone again. Put in rock anchors and also soil anchors on the sides to anchor it, and then put the concrete secondary, and then filled in the walls. So we could actually use the existing structure as a form, and it really saved time. This first construction window went as scheduled, and then we wintered over and dealt with the actual embankment the next season. So the drain pipe and then the filter size, is the two-stage filter up above. We did compatibility analysis. We could have passed just with a single stage, but because the inconsistencies of the fill material, the shell material, and the core material, we settled on a two-stage. It's a C33 sand, and then a gravel, pretty much the stone that we've used for concrete. And then with the toe drain, the actual computed discharge or the seepage that we anticipated down through the filters was around 2,700 liters per minute. So it was a lot of flow. We designed the pipe as a 1.5 meter pipe, perforated pipe, about a quarter full, for a safety factor of about 4. And then once we got down for the toe, we looked, if you remember, down in this area, it was a glacial till. And so the compatibility didn't work, so we used a 3-stage filter to just ensure that we didn't remove any fines from the foundation and plug plug the filters and so forth. The rock face, we just added about a 1 meter thick rock face with bedding rock just for erosion control. And then the seepage. This is the 1.5 meter pipe going into pretty much a well, a wet well type setup. And what we didn't use any electronic measuring equipment. The client, the dam owner actually climbs down the pipe and takes the measurements. This is the finished product. So you can see the, excuse me, the side channel spillway, the new constructed spillway, the stilling basin, and this is a type 2 USBR type stilling basin. It was designed for a 100-year flood, assuming that for the size and the cost, and anything greater than the 100-year would wash out, but it wouldn't attack the toe of the dam. So in conclusion, the risk-based decision approach, again, we had to use that to inform the client, to get the funding agencies behind us so they had some buy-in, and in actual alternatives evaluations, how we selected the alternative. The risk-based approach should be used with pretty much any dam, and I use them for all the dams that we have now, varying different complexities. Through that construction phasing, we probably saved, it was more than 10%. It was about 30% after we back calculated it. And so that justified the construction sequencing of the spillway and the embankment. And that's it. Thank you very much.
Thank you. Thank you, Mr. Tom. It was a very comprehensive presentation. A risk-based approach used to develop innovative designs related to embankments and abutment seepage control and spillway repairs for the high altitude continental dam located in USA. I agree with you. This risk-based design approach should be used for all project size to mitigate design, construction, and safety related issues. It's a wonderful idea. Just one question. In India, we are using the probable PMF for the dams which are more than 30-meter high, and SPF which are less than 30-meter high. What is the approach in USA for this design floods?
So the design flood for this is a high hazard dam. So we use the full PMP, or that developed the full PMF, but we did a site specific PMP. So instead of published data, we had a meteorologist come in and we developed the rainfall over the watershed, and it's about 50 square miles at high altitude. And so we could use that to reduce the PMP, the precipitation that resulted into the flood. But at the end result is 100% of the PMF.
Thank you.
Yep.
Thank you. May I speak? Next speaker, Mr. Ronald. This is a
Yes, I'm here.
Levees with large trees by equivalent static systems.
Yeah, thank you very much. We prepared a video for that, so maybe you can just start the video. Unfortunately, I cannot accelerate as Mr. Tom accelerated because it's a video. Thank you very much.
Okay, you are the second last speaker.
Okay.
Please.
Dear ladies and gentlemen, welcome to my presentation with the title The Rehabilitation of Levees with Large Trees by Equivalent Static Systems. Before we go to the topic, I would like to make a little quiz with you, or more a simple question. How old is the oldest tree of the world? Is it 1,200 years, 80,000 years, 4,850 years, or 9,550 years? You are thinking now, but I cannot see it and you can also not respond. So I will tell you the correct answer. It is 80,000 years. And it is the quaking Aspen of the USA. Now, the outline of my presentation shows an introduction, then some short information about design basics and codes for levees of Germany and international on an international basis, experiences with trees in Germany, and the equivalent static systems and case studies where we also talk a little bit about the design. The presentation will end with a short conclusion. Introduction. Since decades, starting from the 1980s, we had a lot of flood incidents, severe flood incidents in Germany. As you can see from the pictures, it was really sometimes really critical. See here, some people were sitting on the wall from a house which was already gone. And fortunately, these people were rescued by a helicopter and nothing happened. But shortly after this picture, although this wall failed. Here you see this picture, a famous monastery on the river Danube, which was also regularly flooded. Here, 1999, but it was also flooded 2005. And nowadays, there is a mobile flood protection system, which is protecting from the floods now. And here you see also a quite famous picture where some people tried to close a dike breach in 2013 with some ships. And at the end it was successful, but it was really very new and very difficult approach. When we talk about trees and levees, this is all there you have to consider storm events and flood events. So the storm event is endangering the tree, and this flood event is endangering the levee, inclusive the hinterland, by flooding. Since up to 2018, we were quite confident that these two events are not coinciding. Means that the storm event is an independent event and the flood event is an independent event, and normally storms are not occurring simultaneously with the flood events. But 2018 it was different. 2018 in January we had this storm event Buglind, the 2nd and 3rd January, and then 1 week later, or simultaneously, almost simultaneously, we had a flood in Germany, in Western Germany, on the Neckar, Lahn, Mosel, and the Rhine River, with a recurrence period of 5. So in advance, we had a very heavy storm which brought many trees to fail, and then we had a flood event, and also trees on levees failed. So from this experience, we are a little bit more concerned about trees failing on levees. But later I will show you some more pictures about that. As many other countries, we have a lot of books, guidelines, codes, which you need to read when you are busy with this topic. First, we have our DIN code, flood protection structures, as I mentioned here. But we have a row of guidelines, technical guidelines, which were first, which was published in 2011. Now we are working on part 2 and part 3, and especially part 2, the ecological aspects on or at levees, is dealing with this topic, trees on and nearby levees. Okay, there are some other guidelines, but also international standards and guidelines are available from the US or even the Netherlands, our neighbors, which are very experienced with levee constructions. And we have also this international levee handbook, where are also some topics related to trees on and nearby levees included. This is a section, a typical levee section, which is dictated by the German codes, which shows the basic requirements and regulations, such as the slope inclination, which should be 1 to 3 for both slopes, upstream and downstream. There should be a freeboard of minimum 0.5 meters or even 1 meter for large levees, and there should be a crest width and a defense berm on the land side, on the downstream side, and there should be a vegetation layer which is protecting the surface against erosion, and. But of course, when we have the topic with trees, you will ask, where shall we place the trees? So for this typical section, there is no tree. And then the question is, do we need to remove the trees when there are trees? Yeah, and when you look at this section, it is the case. You have to remove all the trees. Because also we have this protection zone here, which is, according to our federal system, 5 to 10 years different for the federal states. And then when there are trees, also not nearby, but a little bit far away from the trees, who is paying for the maintenance? Does it create more costs? And generally, are trees dangerous? And of course, trees are dangerous. Otherwise, we would already place some potential trees or tree areas where you can place trees in this section. But there are also some regulations concerning trees in the codes, in the up-to-date codes, which looks like this. You have this, again, this typical section of a levee, and you have this dike protection zones, which are, as I told you already, 5 or 10 meters for bushes and small trees, and even for large trees like poplars. Here it should be 30 meters away from the dike foot, both sides. And on the dike itself, you can place small bushes in the upper area of the downstream slope if you place a little bit thicker section, a thicker layer below it. This is the standard case, and because this is not the only case what we have, we are working on this part 2 of these guidelines, as I told you, dike guidelines, where we are introducing more cases, like you see here in this matrix. Again, you have here the normal case, where there is nothing on or nearby the tree. I mean, trees, of course there is something, but not trees. And there are now 3 exceptional cases, like you have an oversize on one side, you have an oversize on 2 sides of the minimum dike section, or you have a static system placed into the dike, which is taking over the flood protection function. This is what is the main topic, this exceptional case 4, this is the main topic. And as the dike gets stronger, the risks are lower for failure, and also you can place some kind of selected vegetation, woody vegetation, trees in the areas where you cannot place it in the normal case. So this matrix shall be included in this part 2 guidelines, but it is not published yet. Why do we need regulations? Because our dikes in Germany look like that. You see here, this is a topic, or this is a case study or situation in Munich. A dike in Munich, you see a lot of trees, but you don't see a dike. This is the same for me. I don't see a dike, but believe me, this is the dike road. The same here. This is a dike hidden in the forest, which is also a nature protection area. Okay, here's another dike at the River Iller, where you see just a small pathway on the crest, but a complete forest on the water and on the land side of the crest. But not only forest-like vegetation we have in our levees, but we have also single trees on the upstream slope, We have single trees. Here you see the river, which are placed as kind of alleys. Again, here on the upstream slope, or we have also single trees left after rehabilitation, which are enclosing quite a huge risk for the dam once a flood occurs. This is, again, even after the rehabilitation, you should not do it like that. You should really strengthen the dike that it can sustain over the decades of operation without any risks. And of course, you know, there is no possibility to surveillance or to supervise the dam during floods. You have also limited access, and all these negative effects which comes with trees. And of course, it's not only that the trees are hindering your work, but they also have a very high risk. You see here some failures on dikes, at dikes here in Düsseldorf. Okay, this child was not, is coming later, it was not endangered, but it was in the course of this storm event Ella 2014, I think a few thousand trees were failing in the vicinity of dikes. You see here a tree failure, which was critically damaging the crest of the dike. So, but there was no flood. And you see here some broken dikes where the roots of the trees were completely infiltrating the dike body. So the question is always, is this the reason, or was this negative, or didn't it work as a kind of natural reinforcement? But at the end, the dike failed there, though it was not enough reinforcement. And as we cannot really understand the failure behavior in these special cases, we generally assume that there would be kind of overtopping and erosion along the roots, so that rooting of the dike body is generally causing danger. So what can we do to avoid this danger, or to make our dikes as safe as we want to be them for trees close or nearby the levee? We in Germany frequently use this equivalent static systems. I mean, equivalent static systems, the complete flood protection function is taken over by this kind of ceilings with a static function. Here I've added the types of ceiling what we are implementing in Germany. That is, you see this mixed in place wall, where you put also some steel bars inside to get this static function, or a cut-off wall, a milled cut-off wall here. The mill is limited to about 10-11 meters, but this is also sufficient for some dikes, where you also put some steel bars in a distance of a few meters, that you can have this function. Or you can easily put a sheet pile, a steel sheet pile inside of the dam, which is also taking over a static function. Nowadays also PVC sheet piles are on the market, and also these sheet piles can take over a static function, but of course quite limited in comparison to the other ones. You place it somewhere in the dike body, and you have to consider some design considerations which show, or which consider a failure of the slope where the tree is placed, which looks like that. The tree can be upstream, on the upstream slope, or somewhere at the upstream slope, on the downstream slope, and then you assume there is a cantilever function, a cantilever effect, that the static system has to take over the complete loads if one of the slope fails. And you always have to think about potential erosion or scoring effects. So you have to set the level to which the complete slope is failing or eroding. That is in case or in a single case not always so easy. Starting with the year 2000, some projects were already realized, which is again here, a levee at the river Isar in Munich, close to the zoo. So after behind this fence there is a zoo. So once you visit the zoo in Munich, you can go also to have some nice sightseeing of flood protection dikes, flood protection structures. You see here there was a mixed in place wall placed in the middle of the dike, where you put steel bars in a distance of 4 meters to activate the static function. And by this you could leave all these trees in place, and the dike was also a little bit heightened so that the environmental impact was really minimized in this area. It is not only the environmental impact, but also the people, for leisure, for going jogging on the dike. They really put political pressure on the project that this solution was realized. Another similar question, similar topic, another project in Bavaria, close to the river Saarlach here. There was no dike, so that it was a new construction where a lot of trees has to be removed before the construction. Then you place the levee, the dike, and the dike was strengthened with a sheet pile wall in combination with a MIP wall, the mixed in place wall, which was also reinforced in order to allow trees close to the dam, to the dike in the future. Not on the slope, but it was designed also for complete slope failure, so that the dike is just, or the dam body, the dike body is just covering our flood protection wall, what it is at the end, and can fail completely. You see starting of the works and ongoing works. Now it is already completed. Another project which is now still in design phase. You see here a levee at the Neckar Rhine, at the Neckar River, which is completely covered also with woods, with trees, large trees, also trees with a height of 40 meters, where we designed a sheet pile wall close to the upstream dam shoulder, or in the upstream dam shoulder. The special thing is that the environmental restrictions are so strict that we could also not apply heavy machinery, so that we choose a pressing method, which is walking on the sheet piles themselves. So we have really no or very limited impact, very limited effect during the construction. So we did not remove a lot of, or we did not create or remove all these upstream and downstream vegetation and trees. Coming to the conclusion, there are risks of trees, and when the dike is not designed for accepting or for covering these risks, there should be no trees on dikes with a limit, with a small geometry, or without any additional safety measures. The conservation of woody vegetation is frequently required due to environmental restrictions, which is getting more and more important for these works in Germany or even in Europe. The European environmental law is really very strict. But there are measures, robust measures, in order to guarantee the stability and durability of levees. And these measures are combined with high costs for the investment during construction and also for maintenance during operation. And the equivalent static systems, as we explained in this presentation, are one of these robust measures which are frequently applied nowadays in Germany. Coming to the end, you see I have added a quote of a famous physician, Albert Einstein, who said, "People love chopping wood since in this activity one immediately sees the results." So chopping the trees or cutting down the trees in a levee project, it's the easiest way, but you also have to remove the complete roots, which makes it again quite expensive. But you see the result. The other thing is a little bit more complicated, although from the design approach. And here you see a picture where the police had to protect tree removal works from people who tried to save the trees. Yeah, this is also the other side. There are also some green activists who are against all of these kind of works. So thank you very much. Hope you have a good day. And I don't know how, but I think you can ask me questions after or whatever by email. You're welcome for that. Thank you very much.
Seems that our director is a little bit off.
Yeah, it seems so. Can I pose a question? Did you also consider the influence of animal burrows? Animals attracted more to levees if there are trees in it?
Yes, that's true. That is always the same when you have trees or whatever, this very dense vegetation, animals love to dig in. So this is always coming with the trees. You have also these holes, these weaknesses, and this is also a reason why you put this very strong measures inside the dam. Yep. Foxes, for example.
Yeah, foxes. In the past months, at the cross-boundary sites near Antwerp, we performed several overflow experiments with foxholes, just with trees. And well, if there's a foxhole, it's if there's a tree, close to the tree, and not that much happens. Clay is slowly being eroded. There are animal burrows which are not protected by the roots anymore, and then you get pretty quick failure because of those animal burrows. And further away, far away from the trees, there are no animal burrows. So, yeah, the most dangerous zone is a bit away from the tree, not far away from the tree.
We have already dikes that are called rabbit dikes because they're 40 years old, and the people and everybody, also the owner, calls them rabbit dikes. Okay, that shows the situation. Yeah. Thank you.
Thank you. Thank you. May I request the next speaker, Mr. Richard? Mr. Richard? He's here? Hello? There's no other speaker?
The last one is missing.
Last one is missing. Then let's conclude. Hello. Hello. क्या हुआ क्या?
चलो चलो
कोई जवाब नहीं दे रहा.
उड़ा रहे
Okay, we can conclude. It was a very good session in the topic rehabilitation technologies to enhance dam safety, focusing mainly on modernization, optimization, and rehabilitation of aging dams. The topics: optical fibers for CPS detection, granule filler for flood protection of levees were eye-opener. The topics like emergency drilling and grouting of हेलो मेरे वीडियो क्लोज हो गया बंद कर दें
Now we hear you again.
hello
Yes, we hear you. We hear you.
the session is to be concluded now.
Yes, sir. Please conclude.
It was a very good session and this topic
Video, sir.
Okay.
Yeah, you may please play that. Thank you, sir.
Now we are right, sir.
Okay, I think the session is live now.
Yes,
Should
sir.
we start it?
Started, sir, please.
Okay. Okay, I'm Kushvinder Vohra. I am member Water Planning and Projects in Central Water Commission, India, and I am chairing this session. I welcome you all in this session on modernization, optimization, and rehabilitation of aging dams. The topic is very relevant as a lot of water storage infrastructure worldwide is having challenge of aging, impacting its life and services. Now, India itself has more than 5,000 large dams. However, Indian dams are quite young as compared to dams owned by various leading countries of the world. However, still, there are challenges in their maintenance, especially related to efficiency and safety. There is additional stress due to climate change in addition to conventional challenges. Our assets are actually facing exposure to more intense and more extreme flood, drought, and earthquake events. Now, therefore, we need more investment to address safety and health of our existing assets to minimize the possibility of their failure and consequent economic loss and loss of life. Government of India is presently working in this direction through various dam rehabilitation programs such as dam rehabilitation and improvement project. I am happy to say that phase 1 of this project, which was taken up in 2012 onwards, is getting completed during March 2021. We have undertaken about two works related to 223 dams which were located in 7 states in India, and we have incurred a cost of about $315 million. Now we are ready with the phase 2 and phase 3 of the program, which will be for next 10 years beyond March 21. Then the outlay we have covered is around 10,000 crores, which is roughly say equal to, maybe I will be telling you in dollar terms also. So about 736 dams of 19 states are being covered now. In addition to that, 3 central agencies are also participating. This we are getting it done with the assistance of World Bank and the Asian Infrastructure Investment Bank. They each would be providing $250 million. And rest of the funds are being provided by the central agencies and the state government. And we hope that we will be covering most of the dams during this phase, which we feel that requires urgent attention. So in addition to that, India is also in the process of enactment of dam safety legislation. Proposed legislation is considered the foundation of dam safety assurance program in India, with adequate legal, technical, institutional provisions to deal with the dam safety. Actually, over the years, a number of developments in dam safety has taken place in India. So I'm able to tell you about India, but we will be listening from the speaker having the international experience today also. So keeping in view of all that, it becomes this topic becomes all the more relevant for deliberations, and I think that we will learn a lot from the deliberations which are held. There are 7 speakers. As I am told that there are 7 speakers in this particular session, and session is up to from 2 to 3:30. And therefore, roughly, I will request each of the speaker to utilize, say, about 10 or at the most, say, 11, 12 minutes, so that we can have, say, 1 to 2 minutes for question answer, if any, from the listeners, from the participants, to make it more fruitful. So with that, I think the first topic today is storm analysis and quasi-distributed hydrological modeling for design flood review of Icold Dam. Icold Dam is in Gujarat, and the presenter is Director, Central Water Commission, Mr. Nityananda Rai. Mr. Nityananda, are you able to see, able to hear? Are you there?
So actually, I am his deputy director. I'll be presenting.
You will be presenting on his behalf.
Yes, sir.
Okay, fine. So please introduce yourself and let us get going.
Yes. Is the PowerPoint visible, sir?
Yes, you are. Please go ahead.
Yeah. Respected chair and distinguished members of the delegate, very warm good afternoon to one and all. I'm Deputy Director, Central Water Commission, New Delhi, and I, along with my director, N.N. Rai, would be presenting the paper on the quasi-distributed model for Ukai Dam of Gujarat. Tapi is the second largest west-flowing river draining into the Arabian Sea, and Ukai Dam, commissioned in the year 1972, forms the terminal reservoir on the river Tapi. The catchment area up to the dam site is approximately 62,000 square kilometer, and this dam caters to the needs of irrigation, hydropower, and other facilities. It is a composite earthen and masonry dam with a maximum height of 80 meters and a gross storage capacity of 7,400 MCM. Therefore, as per the BIS criteria, this dam qualifies for probable maximum flood as its design flood. Ukai Dam was taken up as a part of our DRIP 2 exercise, and let me give a brief introduction about design flood. Design flood is nothing but a flood hydrograph which is adopted for a dam after accounting for the hydrological and the economic factors. It corresponds to the maximum risk, a tolerable risk the project can sustain without substantial damage to its components and the downstream people and its properties. The hydrometeorological approach that we are going to adopt for this particular catchment depends upon two components. One is a catchment excitation, which is nothing but the rainfall or the storm. And the second is the basin response, that we call it as a unit hydrograph. The physiographic parameters of Ukai catchment are delineated in the ArcGIS, and this catchment being of a catchment area of 62,000 square kilometers, and our unit hydrograph theory says the maximum allowable area is only 5,000 square kilometer per catchment. Therefore, we have divided this into a series of 20 subcatchments. And the catchment parameters, which are the catchment area, the longest flow path, the centroidal longest flow path, and the slope, are derived using the ArcGIS software. And these are the parameters that we have got for the 20 subcatchments. When we analyze these, we see that the slope is of a range of 1 to 3 meter per kilometer, which means that the entire catchment is of a very mild slope, or you can say a rolling terrain. And the unit hydrograph that is being developed is the Clark's unit, in which the time of concentration and the storage coefficient is taken into effect. A unit hydrograph is nothing but the hydrograph that results from a 1 centimeter of excess precipitation, which is spread uniformly in space and time over a watershed for a given duration. So according to the Clark's unit hydrograph, these are the 20 unit hydrographs that have been developed. And here we see that this particular subbasin, that is the SB7, gives the maximum unit hydrograph coordinate. Now, the important aspects of design flood estimation are, for a catchment area which is as big as Ukai Dam, that is 62,000 square kilometer, the selection of storm is of utmost importance. While we select the storm, we have seen that the time base of the unit hydrograph is extending more than 52 hours, which means that we have to select a 3-day storm. While selection of a 3-day storm, we have to be careful that the 1-day, 2-day, and the 3-day storm may have I very close to each other. So when we transpose these different storms individually, it makes the storm almost stationary. So in order to avoid that, in this present paper, we are going to discuss about the bodily movement of the storms and how the natural storm pattern is not disturbed. And this methodology that we have adopted for Ukai, we are comparing it with the depth duration analysis, which gives you a very good check that we are going on the right direction. Now, when we see this particular catchment, we have analyzed that a storm occurring in a place called Golkund, that is on the date of 4 to 6 August 1968, has a maximum I of 977 millimeter. This is the most critical storm for this particular catchment, and the respective 2-day and the 1-day storms have occurred in places called Jawahar and Ukai Dam itself. And these are the values of the storm high, the 445 millimeter, 752 and 977. These are the most critical storms that have occurred in the 1-day, 2-day and the 3-day duration in the year 1968. So our methodology would be to transpose this 3-day storm into the storm catchment and maximize the storm in such a way. We have to reorient it in such a way that it is maximized. Once the 3-day storm is maximized, we would shift the 1-day and the 2-day storm into the project catchment in consonance with the movement of the 3-day storm. I will just explain it to you in this figure. This is the original location of the 3-day storm of Golkund. I am transposing this to a new location, which gives you the maximum depth for the entire catchment. Likewise, this is the in situ location of the 2-day storm. I am going to transpose it into a new location, which is exactly parallel to the movement of the 3-day maximized location. Likewise, in this 1-day in situ location, I'm transposing it to a location parallel to the 3-day transpose location. So in this manner, once both the 1-day and the 2-day storms are transposed, this will be the figure that is there. This is the 3-day storm. This is the 3-day storm, this is the 2-day, and this is the 1-day storm after being transposed. This methodology of transposition of storms is called as the bodily movement of storms, in which we are not disrupting the actual pattern, we are keeping it in tune with the 3-day maximized location. Now, when I compare it with the depth duration study, the depth duration is nothing but the in situ location of the storm, where it had actually occurred without moving that storm to another location. I would analyze what is the depth which is occurred in the entire catchment. Now, when I am comparing the bodily moved storm with that of the depth duration, it is coming to the tune of 50 to 52%. I mean, the change is only 2%, and the 2-day to 3-day depth ratio is varying from 80 to 84%, which means that the bodily move transposition also captures the 1-day and the 2-day storm depth patterns, which has actually physically occurred in the catchment. So this is a comparative check that we are not going in the wrong direction. Now, once you get the storm depth for each of the 20 subcatchments that we have delineated in our GIS, we would multiply it with the transposition adjustment factor of 0.85 and the moisture maximization factor of 1.42 to get the PMP depth, that is a probable maximum precipitation that can occur on the catchment. Now, since I have taken a 3-day storm, how do we calculate the individual 1-day, 2-day and 3-day? The 3rd day PMP will be nothing but the 3-day PMP minus the 2-day PMP, and the 2nd day PMP will be 2-day PMP minus 1-day PMP. Thus, we get individually the 1st day, 2nd day and the 3rd day storms. Now we have to critically sequence this with respect to the distribution coefficients. Since Ukai Dam is lying in the Narmada and Tapi Basin Atlas of the PMP Atlas, which is developed by CWC and IMD jointly in the year 2015, I would get the time distribution coefficients from them. And it being a 3-day storm, we have going for the bell distribution. So each bell comprises of 12 hours. So our 3-day storm will comprise of 6 bells, and we are going to place it in the sequence B1, B2, B3, B4, B5 and B6. Since this particular catchment of Ukai is lying in two FER. FER is our flood estimation report. And for this particular catchment, we are using the upper Narmada and lower Narmada. Hatnur Dam, which is exactly in the mid of this catchment, is dividing this catchment into the upper portion of Narmada and the lower portion of Narmada. This is the location of Ukai Dam. So up to this particular portion, we have our subbasins 1 to 10, and lower downstream, we have subbasins 11 to 20. So we have to use the loss rate, which is given in our flood estimation reports, again made by CWC. We have it as 0.1 centimeter per hour and 0.5 centimeter per hour for the respective PMP grids, and we get our effective rainfall. Now, after getting the effective rainfall, we convolute these unit hydrographs, and now this is made as the input for the hydrological modeling that we are going to use with in our HEC HMS tool. This picture shows the actual Ukai Dam on the right, and this convolution is done with regard to the which gives us the maximum ordinate. And in our case, we are seeing that this particular unit hydrograph, which is of subbasin 7, gives you the maximum ordinate. So my critical sequencing will be with regard to the ordinates of this particular subbasin. Now, this will be the HEC HMS model that we have generated for this particular catchment. In this hydrological modeling, what we are using is we are making a series of subbasins, its junctions and reaches. What happens is that the lumped response of every subbasin is coming over to a junction, and the routed response of every reach will also reach the junction. So a junction is nothing but the culmination of, or the addition of, the lumped responses as well as the routed responses. Thus, the river would flow in this direction, and finally we would reach the final outlet at Ukai, and Ukai Dam will have the addition of all the lumped responses as well as the routed responses. We are using a Muskingum model of channel routing. So in order to make, now we have 20 subbasins and 20 junctions as well as 20 subreaches. In order to make it stable for Muskingum routing, we are going for the stability criteria. Delta T should be greater than 2kx. And we are subdividing for this, again, for this making the stability criteria, we are subdividing it into a number of sub-reaches. Here you can see in some particular reaches, we have as much as 6 sub-reaches, so that our stability criteria is taken care of. Again, the velocity that we actually physically get in these particular channels, that we have checked it with our CWC HO sites, and again the data of Hatnur Dam was analyzed for the backwater effects of these catchments. And thus, the actual velocity was used for this model, and we have arrived at the PMF for Ukai Dam. We are getting a value. This is the revised PMF I'm talking about that we have done in our DRIP 2 study. We are getting a value of 59,470 cubic, and this is comfortably lying between our envelope curves. The average envelope is coming to the tune of 43,000, and the upper envelope is giving a value of 75,000. So we can say a 60,000 is well in between these two upper average and upper limits. And as a conclusion, I would like to say that for such big catchments as Ukai, due care should be taken to have the proper storm selection and the proper reorientation. And this method of bodily movement of storms is a very new methodology, and it should be effectively utilized so that and compared with the depth duration study that we have done. Now, to obtain a reliable depth of PMP over all the subcatchments, the influencing factors of storm centering and reorientation need to be carefully decided. This is one hitch that we all face, because this has to come after 3 or 4 levels of filtration. I mean, we had a series of experts with us to give us more inputs as to how to go about this. And the biggest safety of any structure is the safety of the dam. So a reservoir should always have a spilling arrangement to pass the specified design floods safely without failure. and which results in an uncontrolled water release. So yeah, this is the conclusion, and thank you so much.
Explaining methodology so quickly, and we are grateful that you have actually done it in time. Now, if there are certain questions, if somebody has a question, can he put in the chat box also? He can put in chat box also. We can ask the question on your behalf with your name and question. Is there any question? So I'm not able to see any question in chat box. So what? Just one or two questions from my side, Isaac.
Yes, sir.
So this basically study we have done for considering this dam under DRIP 2 probably phase 2. That's what you told.
Yes, sir.
Now you have told that PMF has actually come as 59470 QMAC.
Yes, sir.
So what was the design flood? What is the present design flood?
56,000, sir.
56,000. 56,000 is around the present, and you have now come up with PMF of about 59,470, right?
Yes, sir.
So now there are two ways of doing it. So under DRIP 2, what you are proposing means how we are going to take care of this slight increase in flood?
So actually, this is totally taken care of by the design department too. I mean, they have to come up. This is just a hydrological observation. So now, yes.
Okay, so you have no idea whether the spillway is going to other measure is to be taken, right?
Yes.
Okay, fine, thank you. So, but in your study somewhere in your paper, it is written that it will be passing at MWL. This 59470 is passing at MWL itself. Is it correct or?
It can, sir, but some reservoir operations has to be done.
Okay, so we have to do certain reservoir operation in construction so that we can manage it within that. So you mean to say probably one of the measure which may be taking is reservoir operation manual for this project, which may not require any additional kind of structure arrangement. Okay. Okay, thank you very much, Isaac. And then the next speaker today is the topic is heightening of Dhanikari Dam. I think it is in Port Blair. This is a drinking water project, if I am correct. And but the topic they have given is the hydraulic design of spillway and energy dissipator in this particular project. So the presenter is Mr. V.S. Ramarao, and I think that he has requested for video for the presentation. Is that right? Host, can you play the video? Mute kar do.
Hello, everybody. Myself, V.S. Ramarao,
Yes, sir,
96, Maharashtra, and my paper titled Heightening of Dhanikari Dam, Hydraulic Design of Spillway and Energy Dissipator. Maharashtra, and my paper titled Heightening of
issue host की तरफ से
of Dhanikari Dam, Hydraulic Design of Spillway and Energy Dissipator. Outline of presentation is heightening of existing dams, heightening of Dhanikari gravity dam, modification of spillway and energy dissipator, assessing performance of spillway and energy dissipator of modified Dhanikari dam by physical hydraulic model studies. Heightening of dams. Number of dams were heightened or being heightened worldwide. The purpose of heightening includes augmentation of water supply, irrigation, industrial use, enhancing spillway capacity and flood control capacity, enhancing power generation. And as Icold felt in its 2016 conference, heightening of existing dams was considered as the most effective and economic way of increasing the storage capacity of existing reservoir and has been given top priority. Some heightened dams earlier, Rosris Dam in Sudan, it was heightened by 10 meters, swelling its hydroelectric production capacity by 50% and more than doubling the reservoir volume, 3000 MCM to 7400 MCM. Spullersi dams in Austria, Macaronis Dam in Italy, Lesufran Dam in UK, Mullardo Dam in North Scotland, Shin Muriyama in Japan are a few of dams that were heightened for various purposes. There are so many dams that were heightened. As far as India is concerned, dam heightening took place there. Barvi Dam in Maharashtra heightened to meet the water supply demands of MIDC in Mumbai. Dhanikari Dam in Port Blair was heightened by 5 meters. And in DRIP program, Dam Rehabilitation Improvement Project, it envisages the rehabilitation and improvement of dam projects in India, which includes design flood reviews. Dhanikari Dam heightening, the necessity. Dhanikari is a storage dam in Port Blair city in Andaman and Nicobar Island, India. It was built in 1973 to cater for the drinking water needs of Port Blair city. Storage capacity of 4.61 MCM was there. It was increasing demand of water to the city of Port Blair. It was proposed to raise its height by 5 meters to create an additional storage of 3.23 MCM, that's about 70%. The features of Dhanikari Dam before heightening includes length and height of the dam 132 meter and 32.25 meters respectively. Storage capacity was 4.61 MCM. Design flood was 145 meter per second. Spillway comprised of two spans of 7.9 meter wide by 2.2 meter height. Crest of the spillway was at elevation 58.5 meters. Full reservoir level was at 61 meter elevation. The dam top was at 62.5 meter elevation, and the original energy dissipator was in the form of stilling basin with inverted 31.2 meters, and the end sill was a dentated one. This is the photograph of original Dhanikari Dam before heightening. And the features of modified Dhanikari Dam after heightening. Height of the dam is increased to 37.25 meters. Storage capacity enhanced to 7.86 MCM, about 70% augmentation was there. Design flood is 225 meters per second. The spillway at present comprises of three spans of 3.6 by 3.6 meters. The crest of the spillway is at elevation 59 meters. Full reservoir level is at 66 meter elevation. The dam top is now at 67.5 meters elevation. And the energy dissipator modified with solid end sill, though stilling basin is kept same. This is the photograph of Dhanikari Dam after heightening. The design aspects of hydraulic model studies includes discharging capacity of spillway, that is design flood passing capacity of spillway. The reservoir water levels for various operating conditions is to be seen. Suitability of crest profile for passing various discharges upon it. Adequacy of length of the spillway, that is the number of spans and size, whether sufficient or not to pass the design flood. Adequacy of training walls, whether the flood or flow is contained within the top elevation of training walls. And efficiency of energy dissipator, whether the energy dissipator, that is stilling basin in this case, is performing efficiently to reduce the flow, to reduce the velocities of the flow coming over the spillway. This is 1:25 scale model of Dhanikari Dam. It's a geometrically similar scale model. 3 spans of 3.6 by 3.6 meters is reproduced here, and stilling basin at the EL 31.2 meters elevation, and solid end sill also provided. Hydraulic model studies with regards to spillway capacity was carried out. The design discharge of 225 meter cube per second could be passed through the spillway at a reservoir water level 63.7 meters with all gates fully open, which is less than the full reservoir level. 153 meter cube per second can be passed at reservoir level 62.8 meters, and 75 meter cube per second can be passed at reservoir water level 61.3 meters. A maximum of discharge 331 meter cube per second could be passed at FRL with all gates fully open condition. Also, with one gate in operative condition at FRL, the discharge of 225 meter cube per second could be passed. That is with 2 gates fully open condition, as per the BIS code 11223 1985, which recommends to analyze this capacity of spillway for one gate in operative condition. And this is the plot of discharging capacity of spillway with gates fully open condition and partially open condition. Here we can see 331 meter cube per second can be passed through this spillway with all gates, 3 gates fully open condition for full reservoir level. Hydraulic model studies in respect of spillway profile to see the profile of this modified profile of the spillway suited to the particular discharge conditions. Piezometric pressures were observed over the crest and the glacis of the spillway were found positive for various flow conditions. With the observed positive pressures over the profile of the spillway, it is corresponding to equation x square is equal to 20y, which is found to be acceptable for the modified dam. In this figure, we can see the pressure profile all along the crest up to stilling basin and end sill top. The pressures are positive over the spillway surface. Hydraulic model studies with regards to energy dissipator. Original energy dissipator for Dhanikari Dam was in the form of stilling basin of length 25 meters and inverted 31.2 meters. The end sill was a dentated one then. The intensity of the flow over the spillway is increased now with the modified dam from 9 meter cube per second per meter to 15 meter cube per second per meter due to the increased design flood from 145 meter cube per second to 225 meter cube per second. The length of the stilling basin was therefore increased to 30 meters to cope up with the enhanced intensity of flow along the stilling basin. Initially, provision of ski jump bucket was also considered as energy dissipator by the designers, but CWPRs recommended the stilling basin as energy dissipator since there was possibility of impingement of ski jump on the hill nearly downstream. Also, the pre-formed plunge pool downstream would involve huge amount of excavation. Hydraulic model studies with respect to energy dissipator continues. The performance of stilling basin was assessed for the discharges 75 meter cube per second, 150 meter cube per second, and a design discharge of 225 meter cube per second. Steady to strong hydraulic jump was forming in the stilling basin. The hydraulic jump was fully contained within the stilling basin for entire range of discharges. The velocity of flow entering the stilling basin was between 19 to 23 meters per second, while the velocity of the flow over the end sill and the downstream stilling basin was merely 3 to 4 meters per second. As such, there is about 80% reduction of velocity of flow in the stilling basin. Hence, the performance of stilling basin was found to be satisfactory. Water surface profiles for design discharge, and we can see here that the hydrology formation in the stilling basin.
Just host, can you please check up what is the balance time of this? Because we are only running 11 minutes.
150 meter cube per second.
Host is there?
Or full is available.
Yeah, fine.
It's a very important dam, heightened project of Andaman Nicobar Islands. DPR prepared considering the water demand for 20 years. Heightening project was completed in 2013. Modified spillway of performing satisfactorily as per hydraulic model studies conducted in CWPRS for discharging capacity of spillway, suitability of spillway crust profile, energy dissipation arrangement in the form of stilling basin with solid NSL. We can see from this importance of Dhanikari Dam heightening. Honorable Lieutenant General Shri A.K. Singh, he mentioned about the heightening of Dhanikari Dam by 5 meters, which eventually increased the capacity by 70%, solving the problem of water scarcity in Port Blair and surrounding areas in the next 20 years. This was clipping on August 14, 2014. This is the photograph of Dhanikari Dam spillway in operation during flood season. And top view of Dhanikari Dam.
Yeah, I think we can stop here this video.
Director CWPRS, Pune, India. Andaman Public Works Department, Port Blair, all my colleagues and friends.
Yeah, host, may kindly see that I think if some presentations are in the form of video, you may like to come to the conclusion or fast forward little bit up to the end if this is passing 11 minutes or so. So host may kindly control that, otherwise we will overshoot this session. Thank you, Mr. Ravarao, for a nice presentation and the benefits which you achieved because of increase in height of that thing. So do we have any questions? Anybody having question may give his name and a question in chat box. Host, can you also see, is there any question at any other forum there with you?
Nothing, sir.
Okay, fine. So just a small question from my side, Mr. Ravarao. When we were increasing this height by about 5 meter or so, whether there was any additional land acquisition or rehabilitation involved in it, or the entire additional submergence was in the government land? Mr. Ramarao, your mic is off. Your mic is still off. Yeah, now it's okay.
Sir, there was a bit of means increased submergence and land acquisition. It was there.
Okay, it was there. Right. Fine. I think next we can move on to the next presenter today. The topic is long-term structural performance monitoring of gravity dams through analysis and interpretation of instrumentation data. So they have done some study related to the instrumentation data with respect to Indra Sagar Dam in MP. And I think we have with us Mr. Hanumanthappa S from CWPRS Pune, if I'm correct. So I think if you have a presentation, you may please quickly start that, keeping in view of the time limits. Thank you.
Thank you, sir. Respected chair and all the delegates. It's my pleasure to present before you a presentation on long-term structural performance monitoring of gravity dams through analysis and interpretation of dam instrumentation data. So this is a case study, and before that I would like to mention that lot of things have been done about talked in so many international forums or national forums about dam instrumentation. And nowadays, because of DRAPE and because of all over in international arena, things are getting importance about monitoring. Instrumentation is being treated as a very fast and far more important aspect. But while doing so, there are certain things which are not taking care. So I will begin with my presentation as per Icold World Declaration on Dam Safety, which was recently there came out. It talks about several pillars. Among them, first one is structural integrity and routine surveillance maintenance. And third most important is about instrumentation and monitoring. So how this has been arrived or originated? Because large number of dams have been failed in the recent past, and dam failures always causes lot of loss to the life, property, and all these things. So many dam safety committees or after expertise committees, they have gone through the remedial failure patterns. And as I'm aware, most of the failures were not due to any engineering failures, or I mean to say there was no design failures. There were some design surprises, or sometimes we call them as a natural hazards, or sometimes they may be due to geological surprises. So because of this, many dams have been failed. But one among them was very common, that all the committee or they have given one suggestion. If a early warning system would have been there in place, probably these failures could have been averted, or early measures of loss of life could have been taken care. So thinking on that line, so large number of dams have been started installing instruments in all over the world. So this has taken place, I think, in the case of after 1980 and all those things, when India has also hosted some the dam safety conferences, and I could this thing. So as far as monitoring status in India is concerned, it's a very sorry state as far as in all our world is also concerned. Because in India, most of the dams, those were built long back, were not instrumented. If at all they are instrumented, either instruments are not working in, or data they are not obtaining properly periodically. In many project people, even though they are obtaining the data, but those data is filed up and kept in the cupboard. And nobody cares for analysis and what is the outcome of that instrumentation. So in this August conference or August symposium, I would like to mention also there is a time has come to set up a centralized dam monitoring cell, either in the state levels or in central government levels, where data analysis of each and every dam can be taken up. With this brief background, I would like to give an example. We in CWPRS created a analysis and interpretation part, and we developed our own methodology. That story goes back in 2003 when Indira Sagar Dam project approached with large number of data sheets to carry out analysis and say what is happening in the sea. But in fact, we were also not aware how to start, because there were so many literatures available in the journals and publications from Indian side or in other parts of the world also. The data we are getting or other interpretation results we are getting are simply graphs, and there was no hint or how whether that really cross checks have been done or not. So when we have taken up this Indira Sagar project, I am thankful to Icold publications which our CWPS is having in large numbers. So referring those things and referring to our design principles, we have set up our own methodology, or we have started carrying out analysis part. So I'm presenting before the outcome of those studies. This Indra Sagar project, as you are aware, is one of the biggest hydro project of Narmada, which is of 653 meter long and it is having height of 92 meter. It is a concrete gravity dam which is having 27 blocks. Among these, first 3 and last 3 are non-overflow sections, and middle 21 blocks are spillway sections. And it is having a capacity of 12.22 billion cubic meters and power generation of 1000 megawatt. So this is a typical instrumentation part. There is an instrumentation philosophy or instrumentation planning. If the dam is having a large, it is a major dam, you have to go for 2 difficult sections. Since it is having both the non-overflow and overflow section, Indra Sagar Authority has taken one non-overflow block, that is block number 25, and overflow block, that is block number 30. One major feature of this block number 30 selection, because it is having a shear zone below the foundation. So these are the typical instrumentations, that is foundation piezometer, uplift pressure, extensometer, pore pressure, joint meter, like that. And as per instrumentation rules, you should have go for different levels. Several instruments are installed at the foundation level, then galleries, and at a certain levels as per importance. So when we started in 2003, so apart from only having data, we were not knowing anything. So initially we went to the site. So we have collected all the data once again, and we have gone through the installation records and calibration records, which were not easily available. But after consulting so many people, though, because it was a state government project during that time, and later on it was transferred to NHDC, but some files were properly classified and they are kept in this thing. So we spent nearly 10 to 15 days to mug out the data. And after that, we came out with the data and started plotting. When we started plotting, the results were not encouraging. So afterwards, we have gone through each and every design aspects of the Indra Sagar Dam, and we have prepared a methodology. So we have started comparing one by one value. And as per our experience, the selection of initial reading and selection of calibration of data plays a very major role. In fact, data analysis should be started from the day one when the instrumentation has been installed. But this has not happened in this case. Actually, first filling, during that time, if any instrumentation measurements were done and it is analysis carried out, it will serve the most of the future dam analysis. In this case, everything was in dark, so we started in the beginning. So this is the data output I am showing from 2003 to 2000. Last updated data is 18, still 19 and 20 we are carrying out. You can see that the initial reading what we are kept in during 2003. So it is based on several observations, and this graph clearly shows the reservoir operation, and in between we have not at all changed anything, still it is continuing. Simply when we are not getting data, we are keeping it blank. This is a typical variation of uplift pressure, and we can see that uplift pressure is closely following the path of the reservoir, which is expected in this case. And it is a graph of one more uplift pressure diagram in block number 25. So I would like to take your kind attention. What is the major outcome of this project? So when we started this analysis, first plot only we got this type of result. We are all aware that as per the BISR condition codes or USBR codes, uplift pressure is to be may follow this path. So in case of block number 13, it is a measured output. It was following well within the limit. This is how we came to know that block number 13, the uplift pressure generator is well within the limit. Whereas in case of block number 25, there was a increase in the uplift pressure at the downstream side. When I showed this to our bosses or project authority, nobody was ready to accept that. Everybody, in case of every blame goes to instrumentation only. This may be the wrong reading or installation, but we have requested the project authorities to go for the confirmation this thing. So we have suggested them to go for tracer technology study, that CWPRS has carried out the tracer technology study, and finally we come out the result that there was a water percolation from the right abutment because of after several years getting enrichment of water. That water is flowing laterally to, and it is contributing the development of higher uplift pressure at the downstream side. This is a major outcome of this analysis part. And one more thing I would like to show that whenever the proper management of keeping the relief holes and foundation galleries in clean condition, that will also contribute very good result for the maintenance of the dam. This is one typical case when we visited the Indra Sagar dam first time. This is the measured uplift pressure variation. Whereas when we ask them to clean and take out the drilling the extra holes, the pressure has been released. And next, after 2 years, when we visited again and taken the readings, the measured uplift pressure is showing this much. So this clearly indicates that uplift pressure is a very major force in dam destabilization, and it can be taken care. So this is typical pore pressure variation that is also following. It is well within the limit. And this is joint movement. So typical 3 types of joint meters can be installed in dams, that is lateral, longitudinal, and along the length. So all the joint meters are showing a very good result, and means there is no much variation as per this thing. It is also following water level fall. So one more major outbreak of this project, this analysis part is temperatures. Since it is a concrete gravity dam, they were expected that there may be a much variation in temperatures, and that is why they have referred the studies to carry out the temperature control studies and to find out the future temperatures. So CWPRS project predicted in 1997 what would be the probable temperature during 2016. This dam instrumentation data we have plotted, and you can see that both these graphs, the contours are matching, and this can be very well within the limits. And on site also, there is no temperature cracks, because every year we are visiting to cross check the data and closely monitoring. We found that whatever temperature measures and site condition closely matching. So this is typical stress diagram. In this case, since we are not having we have started the analysis at later stage. So we have developed our FEM model for this and found out the theoretical stress at particular dome location. And we found that major stresses are well within the limit. So based on this, we can conclude that stresses are also within the limit. So this is typical strain variation. So strain variation is also following the water level, and whatever the strains we measured, they are all well within the limit. And if at all the strains are measured at different planes using strain spiders, so we have for a typical listing, I have taken one particular graph only. So last parameter was settlement of the foundation. Earlier, that foundation meter data is simply available, started getting from 2009, and we have started analyzing that also. In the beginning, that was very little bit very high funded settlement. It was showing like up to 0.4 mm, but afterwards it has started stabilizing, and we can see that whatever the foundation settlement we are having, it is well within the limit, and it is as per expected design parameters. So with this, we have concluded that structural behavior monitoring of dams helps to detect any early signs of or distress, and detection of uplift accumulation at downstream side and subsequent identification of cause of leakage justifies that use of dam instrumented data plays a very vital role. And it also found from the studies that proper maintenance and cleaning of weep holes and foundation galleries is also very much helps to control the pore pressure and drain holes. So as of now, simply installing instruments or taking readings is not going to help. And many existing dams need to be instrumented properly. While taking the instrumentation and going for the instrumentation for existing dam, one has to take care that analysis is also very much important. So keeping this in mind, I request all the project authorities. So the day one when we start installing the instrument, please assign the task to this analysis part. If at all you are not available, take the external help also. But analysis and interpretation is very important. The cost of analysis and interpretation is not much, if at all, and it can be at least.
Thank you very much. Thank you very much, Mr.
Thank you, sir. Thank you, sir.
And yeah, we have already overshot the time, so we have to cut short over here, and there may be some questions also. Yeah,
And
that's
the references.
okay. I think we could hurry up in these things. So any question, if somebody has a question, can put in chat box with the name and question. Is there any question? Okay, there does not seem to be any question from our listeners. So what I propose is next. Now we have actually 4 presentations and only 35 minutes have left. So I will just request everyone to just cut short few of the extra details and complete the presentation in 9 minutes, so that we can really close it at about say 3:30, 3:35 or so. Otherwise, it will be too late. So kindly, then we have a next speaker today who is going to explain an extraordinary event at Mariborskiutak Dam, which is in Slovenia on Drav River. And Dr. Pavel is there to share it. I hope that Dr. Pavel is there.
Yes, I'm here.
And I will request you to that if we can, hurry up with some of the slides and then we can conclude in 9 minutes. Thank you very much.
Okay. Ladies and gentlemen, my name is Pavel Žvanut, and I'm head of the project team for dams at the Slovenian National Building and Civil Engineering Institute, which is located in the capital of Slovenia. The title of my presentation is An Extraordinary Event at the Mariborski Otok Dam. I've divided my presentation into the following headings. Firstly, introduction. Secondly, description of the dam. Thirdly, monitoring system of the dam. Next, an extraordinary event. Then we come to the rehabilitation works, and finally to conclusions. Let's start with the introduction. There are over 40 large dams in Slovenia, both concrete and embankment dams, which are intended for water retention for different purposes, mainly electricity production, but also flood protection, irrigation, and recreation. There are also some historical dams and the dams which are used for other commercial purposes. Figure shows the locations of large dams in Slovenia. We can see 3 the most important rivers which are used for the electricity production: Soča River, Sava River, and Drava River, located in the northeastern part of Slovenia. On the Slovenian section of the Drava River, which is 133 kilometers long, 8 hydropower plants are located. 6 hydropower plants, Dravograd, Puzenica, Vuhred, Ožbalt, Fala, and Mariborski Otok, are located directly in the river stream, whereas the other 2 hydropower plants, Zlatoličje and Formin, are located in the derivation channels of the river. Between 1918 and 1978, 10 concrete gravity dams were built with structural heights between 17 and 54 meters. The discussed Mariborski Otok Dam is located close to the city of Maribor. The concrete gravity Mariborski Otok Dam was completed in 1960 and renovated between 1997 and 2000. It is part of the corresponding hydropower plant located on the Drava River. Its structural height is 33 meters and the dam crest has a length of 184 meters. The dam structure contains 3 turbine piers placed between 4 spillways as well as bank structures. The spillways, closed by 2 steel gates, have a total capacity of 5,600 cubic meters per second. The reservoir, which contains 18.7 million cubic meters of water, has a length of 15.5 kilometers and the surface area of 2.4 square kilometers, whereas the catchment area of the reservoir is 13,410 square kilometers. The Mariborsky Otok Dam is founded on sedimentary bedrock. Figure shows the bird's eye view of the Mariborsky Otok Dam. We can see 3 turbine piers placed between 4 spillways. On the next figure, which shows cross sections through a spillway, we can see the position of both steel spillway gates, lower and the upper one. Long-term manual technical monitoring of the dam behavior began in 1969 and included all necessary types of measurements and visual inspections. In 1990, the monitoring system was supplemented by 2 additional side piezometers on the right bank of the dam. Because of the need for more accurate determination of the state of the dam, automatic measurements of several parameters, mainly hydrostatic and partly hydrodynamic, began in 2002. The monitoring system includes deformation measurements, displacements and inclinations, visual inspections, geotechnical and structural, groundwater measurements, piezometric levels, uplift pressures, temperatures, electrical conductivities and outflows, and measurements of external loads on the dam, which are carried out in the reservoir, in the steering basin, and in the dam itself, in inspection gallery and on crest of the dam. Figure shows the monitoring system for deformation and groundwater measurements. We can see locations of the measuring points for determination of vertical and horizontal displacements marked with a blue color, and the locations of piezometers under the dam and at both sides of the dam, which are marked with a red color. In December 2017, the malfunction of the steering system of the upper spillway gate management of the 4th spillway caused unexpected overflowing of 230 cubic meters per second of water between steel gates, which severely damaged the upper spillway gate. In addition, the concrete beam of the crane rail on the crest of the dam was also damaged. Immediately after this event, the necessary deformation and groundwater measurements were carried out. Measurements of horizontal displacements and inclinations of the dam were performed twice in a short span of time, whereas the measurements of piezometric levels, uplift pressures, and outflows were carried out 3 times in the short time intervals. The detailed visual inspection of the dam was also performed, which involved overview of the state of the damaged part of the concrete. The results showed that, fortunately, the safety of the dam and the operation of the hydropower plant were not threatened. Figure shows some consequences of an extraordinary event. We can see damaged and inclined the upper spillway gate in the 4th spillway. Next figure shows damaged concrete beam of the crane rail on the dam's crest on the right side of the 4th spillway, whereas in this figure we can see damaged concrete beam of the crane rail on the dam's crest on the left side of the 4th spillway. Technically demanding rehabilitation works on the dam, estimated at about 2 million euros, were anticipated. Firstly, auxiliary spillway gates were inserted, which enabled, for the first time since the dam was built, the required lowering of the reservoir level by 6.5 meters. In September 2019, the second phase started, which included restoration of the damaged concrete structure and of the spillway gate, as well as the restoration of the remaining undamaged equipment of the 4th spillway for extending its service life by another 30 to 40 years. Rehabilitation works are expected to be completed by the end of March 2021. The scope of the renovation includes the repair of damage of the concrete structure, and the repair of the equipment of the spillway gate on the following sets of equipment: upper and lower spillway gate, drive mechanisms, and concrete parts. Figure shows the first phase of rehabilitation works. We can see that auxiliary spillway gates were inserted. Next figure shows the start of the second phase of rehabilitation works, after the upper spillway steel gate of the fourth spillway was disassembled. Damage rehabilitation and restoration of the spillway gate of the fourth spillway involved the following activities: disassembly and cutting of the upper spillway gate, displacement and support of the lower spillway gate, disassembly of the lower spillway gate equipment, implementation of non-destructive testing on equipment, production and supply of new upper spillway gate and other equipment, renovation, reconstruction and modification of existing equipment, corrosion protection of equipment, construction works, delivery and replacement of electrical equipment, assembly and testing of equipment, and finally trial operation. In conclusion, I would say that large dam structures represent significant safety risk, since major damage to them or even their failure can cause disastrous consequences, such as the loss of human lives, major economic losses, and severe ecological effects. A very important role in ensuring the safety of large dam structures has the regular technical observation of these structures, which is carried out with numerous measurements and visual inspections, covering the monitoring of deformations and of groundwater filtration. In the case of unfavorable behavior of the dam or major damage, immediate intervention is required, which includes appropriate investigations of the dam structure and also the necessary actions to ensure both the safety of the dam and the operation of the hydropower plant. Thank you for your attention.
Thank you, Dr. Pavel, and for a nice presentation on the case study. Do we have any question in the chat box? Yeah, okay. So I don't see any question. Do hosts see any question at any other forum?
Yes, sir, I will send you.
Is there any question there?
No, sir, no any question.
Okay, fine. So I think we can now move to the next presentation, which is performance of dam and foundation system, case study of concrete gravity dam again, and that is the Srinagar hydroelectric project, which is on Alaknanda River in Uttarakhand, and it is being presented by Group Project Manager SCC India, I think Mr. Rakesh Khali, if I'm correct. This is about 330 megawatt hydroelectric project, and the study will be presented by Mr. Rakesh. Mr. Rakesh is there? Mr. Rakesh Khali? Mr. Rakesh Khali, can you hear me? Are you there?
You are not available.
He is not available. Okay, so then we will quickly move to the next topic, which is being covered, safety inspection of dams in India. So this is being presented by, I think, was to be presented by Rajiv, and I think.
I am, sir. Raghavendra available, sir.
Pardon?
I am Raghavendra, sir. I will be presentation on behalf of Project Singer, sir.
Okay, okay. Your voice is echoing. Just keep little space between mic and yourself.
Yes,
Okay, then I think safety inspection of dam in India. I think you are going to explain certain processes of dam safety inspections. And this has been prepared by Dam Safety Organization in Central Water Commission, India. And I hope that you will finish it within 9 minutes, please. Just give the overview, highlights, and the conclusion.
Yes, sir.
Thank you.
Respected chairperson and co-speakers of the session and all other participants, very good afternoon. Today, our topic is safety inspection of dams. So in this presentation, we would like to give basic introduction and also broad view of what are the steps going to be taken in dam safety inspections and what are the steps we have taken till now from CWC. We move into our presentation. So this is the introduction already covered by other speakers and our chairperson also. In India ranks as of now third in the number of large dams. As per our national register on large dams, we have around 5,534 already constructed dams and around 411 are under construction. So out of which 75% are more than 20 years old, and average if you take, there are more than 40 years old. So you can see, so these dams need to be taken care in proper inspection. So for this, CWC has initiated for institutional strengthening. They started preparing guidelines. In 2018, CWC has already published guidelines for dam safety inspection. So if you see over dam safety inspection, generally these dams are owned by either state governments or respective developers. So these developers or dam owners, they have to do regular inspections like pre-monsoon and post-monsoon and any special inspections, and also they have to submit these reports to dam safety organization in CWC for our examination. And also there is a web portal is also available, that is Dharma. In that also the dam owners have to upload all these inspection reports. So the primary goal of this DSO is to encourage and also assist all the dam owners to the safety, and maintenance. If you see different types of inspections, there are some scheduled inspections and comprehensive evaluation inspections and special inspections and informal inspections. So this you can read it from the scheduled means there are regular. So and also comprehensive means detailed comprehensive evaluation is done. And special, whenever any specific requirement is there, then special inspections are carried out. And informal means daily by the routine regular staff, they can also have these regular informal inspections. If you go into the inspection items, see now the dams, if you classify it, there are so many different types of dams like concrete dams, earth dams. Nowadays RCC dams are also coming up. So even in the dams also there are different parts like spillways, energy dissipation arrangements, outlets, intakes, etc. So in that also each and every item, each and every part is having different structures. If you take only spillway structure includes gates of training walls also. So like that, if you take concrete dams, we have to take care about these joints, movements, drains, water passages, etc. So even we have to consider our inspection with regard to the safety and performance of the instrumentation also. Like already one speaker has talked about the importance of the instrumentation and also the reservoir. In India, recently we have seen in Uttarakhand also the shoreline like massive landslides in reservoir. So this type of regular inspections also will avoid these dam failures. And operation and maintenance protocols and proper disaster management plan and security arrangements and some basic dam facilities. So regular inspections have to be carried out to have all this. Then if you go into the documentation view of this, so there are different methods of documentation we will discuss here. So inspection checklist. So like we have already discussed, different dams are owned by different owners, so everybody will have their own different formats. So again, okay, there must we can try for a uniformity in the different checklist, and also there may be field sketches. So if you want to have a comprehensive report, inspection report form is there, and even photographs also we can include in that, and voice recorders and also in other like even using GPS and etc. If you come to the conclusion, first in India, just after the independence, we have only focused on creating the infrastructure, like only dam creations. But as we coming across, now the dam safety is also coming a big issue. Like already we have told 5,500 dams are already in place. So to take up this challenge, CWC started publishing guidelines in 1987. So recently, this dam safety bill is also coming up. So we are trying to create a uniform inspection manuals throughout the country for all the stakeholders. So that's it, sir. Thank you.
Thank you very much, Raghavendra, for your quick presentation on dam safety protocols, dam safety inspection protocols, which have been put in place in India. Do we have any question in the chat box? One can send with the name as well as question. Please open the chat box. We don't see any question over here, but I would like to ask a small question from you, Raghavendra, since Rajiv is not there, and also I think Gulshan is also not there, is the co-author. How many inspection on an average are being carried out in India? Safety inspections. Do we have some data with us? Because in DSO, I suppose that they are supposed to do that, and you told that on Dharma also we received such things. So what were the during 1819, sorry 1920 or maybe 2021? What kind of number of inspections in India we have seen?
Sir, myself Vivek Kumar Soni, Assistant Director in Dam Safety Monitoring Directorate. Sir, as such, we don't have any number, but in NCTS meetings and in various correspondence, we recommend the owner to carry out pre-monsoon, post-monsoon inspections and comprehensive dam safety evaluation of the dams. And few dam owning agencies submit their annual health status reports where they place inspection reports of their dams. So we receive a 40-50% number of dams inspection pre-monsoon, post-monsoon reports from state governments.
So 40-50%, you mean to say of all large dams, 5,000 plus, you receive 2,500 reports. Anyway, that's okay. Just a curiosity, it was there. You need not explain much. That's fine. So this is what you said, and then some of our author have actually, some of our speakers have talked about Uttarakhand tragedy and probably some protocol which we can fix up. Early warning system in place, that's fine, but sometimes the kind of here also we have said that probably inspection, if we do such inspection can help. Yes, such inspections definitely can help, but probably do you think that the kind of event it happened could have been noticed just prior with certain kind of inspection?
Sir, as of now, we cannot comment. I cannot comment, sir, on that.
Yeah, because as of the information available in open domain as well as with CWC also, it only says that probably land mass moved from bottom and then alongside glacier and then it came down tumbling. So probably and a little far off above at certain height of 5,000 meter plus, something like that.
Yes.
So anyway, so maybe, once we, that's what I was just wondering whether, what we are talking, whether we can really avoid such kind of by having certain early warning system in place or not. Anyway, that's fine. So thanks for a very crisp presentation. Then there is a last presentation today as early prediction of RCC dam body permeability during the construction. Now we are talking about permeability during the construction. This case study is on Dairava Dam in Sri Lanka, and it is being presented by Syed Roosbeh. Is he here? Sayed Roos Bey is the presenter here, or any message for recorded presentation with the host? Host, is there any message from Sayed Roos Bey? I think that Sayed Roos Bey is not present in the session. So I think host, I think we should conclude the session now and move on. Okay, so then we conclude our session today. We had a very nice, session, which was short and very informative. We had about 5 presentations which we could hear, and about 2 more were presented. They were with us, but could not be presented because of non-availability of the presenters today for some reasons. This basically, the topic was very apt, as I said in the beginning itself. Modernization, optimization, and rehabilitation of aging dams. This is one of the concern worldwide, and I think in the context of recent one article by certain persons in Canada, they have researched certain parameters and came up with the aging of the dam and concluding that this question is scary. But then probably I do not agree in totality with that report. In general, there are a number of aspects which were not there in that report, because the safety of the dam can be maintained. It's not linked to simply by the age parameter. There are a number of dams which are century old, which are maybe thousands of years old, which are still existing. Proper maintenance and other things are also the factors, or any other factors which come into the picture. Definitely, certain issues do come: operation and safety, maintenance, and all those things. We need to be taken care of. We had the first first presentation was on hydrological modeling of design flood, Icold Dam. Nice presentation by Ms. Izak from Central Water Commission, and she has nicely explained that this project will be covered in GRID 2, and they have done the hydrological studies related to this project already, and found that it has increased by about 3,000 cubics or so. And probably we might be able to take care of this by reservoir operation, or maybe any other measures during the thing. So that thank you very much. And the second presentation was on heightening of Dhanikari Dam, which is in Port Blair, which has been increased. The height has been increased, and Mr. Ramarao has presented a nice study how useful it was, and with the increase of about 5 meter, we could really get an additional storage of 70% more. And primarily, since it is being used for 70%, and I think it was mentioned in the presentation that they were taken care of future about 20 years or so needs into the picture. So that do help. There are certain cases where we have increased the height of the dams, provided the foundations and other things, design parameters are in place for doing so. In Upper Krishna project also, certain planning was done. Some 3 meter increase was there in the first between first and second phase itself, and then further heightening of the dam is also under consideration. But then all those things how could be planned, because a lot of land acquisition and rehabilitation issues do come, because in the top level, as we move, more and more volume will come into the picture, and more area is likely to be submerged. So that has to be carefully planned, probably, all these activities, what is the cost and what is the benefits and what are the losses. If everything else is balanced, then probably this can be very, very useful because there is possibility of new good sites these days are very few. But the only thing is whether if the site suitable is there, design is suitable. The third presentation was on long-term structural performance monitoring of gravity dams through analysis and interpretation. This was related to the instrumentation on the dams. This was case study by Mr. Hanuman Thapa from CWPRS Pune, and did on Indira Sagar Dam project. And definitely this is extremely important topic. In India also, instrumentation may not have been carried out in earlier past when in the beginning we came up with large number of projects during 70s or 80s. So instrumentation might not be there even, or may not be adequate as on present. And yes, he has rightly explained about the uplift pressures, core pressures, maybe swimming movements. All those things are required to be measured, and they are extremely related to the dam safety. And maybe I'm very sure that our dam safety program DRIP 1, 2, 3 has also taken care of wherever such instrumentation was not there, must have been there. And Indira Sagar is one of the very important project. And as far as my understanding by going through the presentation, probably most of the parameter had been found okay, except that uplift pressure was more at the downstream of one point. So probably that will be taken care by certain measures that will be taken by the project authorities. And definitely this is very important topic as far as we consider the dam safety protocols. And thank you very much for presenting the case studies, and will be useful to us in understanding and implementation of instrumentation in various dams wherever required. Then there was a very important presentation on extraordinary event at Maribor Kyotek Dam by Dr. Pavel. And the case studies belong to Slovenia, and he has explained that how the event has happened and certain damages occurred, and probably the measures they had to take quickly, and they have taken care of the things now. He also, in the conclusion, actually informed what kind of protocols we should follow so that such events could be avoided. Thank you very much, Dr. Pavel. And the last presentation was safety inspection of dam in India. And Raghavendra has present from Central Water Commission, DSO, Dam Safety Organization. And he has nicely explained the process of dam safety inspection, which should be followed. CWC way back has given the guidelines for safety inspection. There is a dam safety organization in Central Water Commission in India. And also a very high level committee, which is there, which meet often and review the dam safety measures being taken all over for the dams all over India. And of course, as I explained in the opening remarks, dam safety protocols are going to be strengthened once we have a legislation in place, and that will give us the comprehensive procedure, which is backed by the law, which will have to be followed by the project authority. So that is, and already we have gone we have passed through one. Lok Sabha has already passed it, and then we are waiting for its passage from the higher house. So this is all today which we had, and presenters have been very brief, and they have actually done a good job in presenting the main things and also concluded them very well. And I really appreciate the thorough preparation they have made while presenting the things with them. And then I have also gone through their some of the papers in length and some of the presentation beforehand, and I see that the quality of all those presentation is very high, and it will be useful to all of us. I think more than 100 or so our professionals have logged into these sessions, and which I have been told by my team. And I hope that this will be entirely this exchange of information of maybe India and abroad amongst each other will help us to understand and implement more and more measures in this area. With that, thank you very much to the host and to all our presenters and all our professionals who have logged into the session for increasing their knowledge in the area. Wish you all the best in your endeavors, and thank you very much.
Thank you, sir. Thank you, sir.
With that, we close the session. Host, you may please log off.
Okay, sir.
दो आपके पास है समझ रहा था सर इजी है सर तो मुश्किल नहीं है सर जैसे नॉन कन्वेंशनल फाउंडेशन यूज
Yes, sir. We are now live. Please start.
Okay, good afternoon, everybody. I am Sanjay Shrivastava. I am Chairman, Bhakla Byas Management Board. BBMB, it has a bouquet of two large dams, large storage dams, and many barrages. We have 6 power plants. So we'll start today. Today we have 6 very interesting articles, very interesting papers to be presented here, and all are from outside India. I think only Dharma is in with my sister organization, Central Water Commission, in association with French people. So to begin with, the first paper is applying early concrete compressive strength prediction in infrastructure construction. So this is a very interesting topic. We are struggling with to get the details of this concretes, how much time how much curing time it takes, what would be its likely strength, what additives we have to put. So basically, this supplementary components such as chemical, mineral, and admixtures may be added to the base concrete ingredients to enhance its properties in a hardened state. So they are working on it, developing accurate compressive strength prediction model. The prediction of compressive strength of concrete has great connotation. It offers an option to do the essential modification on the mixed proportion and help to avoid circumstance concrete does not attain the mandated design strength. It helps in more economic use of raw material and fewer construction failures, hence reducing construction cost. So prediction of compressive strength of concrete has been an active area of research. So now I would request first presenter to please present his paper. Mr. Sayyed.
Sayyed is not available, sir.
Okay, then in case he comes, then we will take at end. So now we will take second paper. Second paper is regarding long-term monitoring of subsurface changes in earth embankment dams. So this is a very majorly used dam in perhaps in all the countries. And initially the invasive, non-invasive techniques were not available. Now many techniques are available like electrical resistivity imaging, stream potential, multi-channel analysis of surface waves, streaming potential, ground penetrating radars. So the major cause of failure of earthen dams are subsidence, sliding, overtopping, erosion of upstream face, cracking due to frost action, erosion of downstream face by gully formation, erosion of downstream toe, and seepage failures. As such, monitoring of subsurface changes in earth embankment dam assumes great significance. Methods such as electrical resistivity imaging, all these what I told have to be done. So now I would request the presenter to please make the presentation.
Hello, my name is Jonathan Chambers, and I want to spend the next few minutes talking about the long-term monitoring of subsurface change in earth embankment dams. And the approach that I'll be focusing on is a novel geophysical monitoring approach that we've developed in BGS with my partners Phil Meldrum, Paul Wilkinson and David Gunn, with HR Wallingford, Craig Goff and Socotec Monitoring, as represented by Nick Slater. Now we refer to the technology as PRIME, the Proactive Infrastructure Monitoring and Evaluation System. The system is built around a really well understood geophysical imaging approach, so resistivity imaging. And for this development, we were seeking to combine resistivity imaging with data telemetry, automated processing and web portal access, really to develop and deliver low cost, low power geophysical ground imaging technology to support geotechnical asset managers, thereby enabling the remote monitoring of the internal condition of geotechnical assets, such as large earth dams. And as a research group, we're really keen to make cutting edge geophysical ground imaging technology relevant, useful and available to end users. Now, I'm assuming that many of you are not familiar with resistivity imaging as a technique, so I'm just going to spend a few moments just introducing the approach. So the property that we're interested in here is electrical resistivity, so the resistance of the ground passing an electrical current. The fundamental measurement is very simple. We need just 4 electrodes, as shown on the diagram, C1 and C2 to inject current into the ground, and then 2 potential electrodes, P1 and P2, to measure the resulting potential difference or voltage, from which we can infer a resistance and then a resistivity. Standard resistivity surveys use portable field equipment and lines of electrodes. You may be able to see in the photograph the stainless steel electrodes in the foreground, a line of those running many tens of electrodes, making up the imaging array, connected to the yellow box, which is our imaging instrument, which will automatically cycle through many hundreds and thousands of these 4-point electrical measurements. So that's the standard survey approach. So you go into the field, set up the equipment, make your measurements, and pack up and go home. Here's a little cartoon showing the measurements in progress. So lots of these 4-point measurements, and by processing, by modeling and inverting the data that we measure, we can generate our images, as shown at the bottom of the slide. Images of the subsurface. So here a 2D slice through the ground showing geological variability. Now, the reason we're interested in resistivity as a property is that it's sensitive to geological variations, and crucially, it's very sensitive to changes in groundwater saturation and quality. It's being widely used in environmental and engineering surveys for a very wide range of applications. There's a very large peer-reviewed evidence base supporting the technique, and crucially, it's a technique that we can configure for remote monitoring, and that's what I want to go on to now. And this is what we've done with PRIME. We've sought to move resistivity imaging from a manual survey technique to an automated monitoring approach. So to do this, we deploy our sensors at our field site. Here I've shown a grid of sensors on the bottom right over an embankment type structure. There are lots of different ways we can configure electrodes, as you'll see later. This is connected to the instrument that sits in the field, and then we interrogate and operate the instrument remotely using wireless communications, wireless router. So we stream data wirelessly back to our servers. We go through an automated processing scheme where we generate our resistivity images, our time-lapse resistivity images, and by applying the appropriate property translations, we can go from resistivity images to images of moisture content, for example. And then these data, this information is delivered through a web dashboard to enable geotechnical asset managers to use this information for decision support. So that's the concept. This is what we've sought to develop within BGS with our partners. Now, there are two modes of operation for this technology. First of all, the system can run to a predefined schedule. So we'll set it to make a number of measurement sets per day, for example, and these will be done and then streamed back to wirelessly. The second mode of operation is where we can attach additional sensors to our system, such as a rain gauge, or, for example, a pore pressure sensor, or even a water level sensor. And so if predefined thresholds that we set for these sensors are exceeded, two things happen. First of all, it bumps the instrument into a very high intensity data collection mode to capture, if you like, events, discrete events at the monitoring site. And then secondly, we'll generate an alert sent by an email or an SMS alert to the relevant asset manager. In terms of the instrumentation, it's been built with a modular design, so it's very easy to service in the field. It fits within a small GRP enclosure, so the instrument sits within a small GRP enclosure. You can see there on the right-hand side. The sensor arrays that the instrument addresses are deployed in the vicinity of the instrument, and these can run for many hundreds of meters within the imaging area. It is indeed a very low power system, so just 10 watts. This means it can be deployed in remote field situations where with no mains power. It can run off a modest sized solar panel. It doesn't just make geophysical measurements, resistivity measurements. We can also attach a range of SDI sensors to the system, such as pore pressure, soil moisture, rainfall data can be harvested along with the geophysical data. And then we have a web portal to set up and configure the measurements and to automatically retrieve data as shown here. So measurement scheduling, effectively calendar type function here to tell the system when to make measurements, and then results reporting and upload to retrieve data. With integrating this monitoring system with existing geotechnical information delivery dashboard, the Calyx system developed by Socotec. And this system allows engineers to have a web dashboard with all the monitoring data from their sites readily available, with alarm thresholds that can be set for the various sensors that can be seen and interrogated. It has a GIS front end, so the sites that are being monitored can be seen in the GIS. We can zoom in to one of these sites and we can see where the sensors have been deployed as the green circles there. We have webcams as well. Now, this was originally designed for standard point sensors, so tilt meters and soil moisture or pore pressure sensors. And what we've done is to integrate prime information, so volumetric time-lapse imaging data into the same interface, so we can interrogate the geophysical information alongside the conventional point sensor information. So you can see an example for an embankment here that we're monitoring. We can cut and slice, rotate, interrogate the 3D volume to see what change is occurring within it. We can set thresholds on a cell-by-cell basis, if we want to, or for clusters of cells. So when certain thresholds are exceeded, so increased moisture content, for example, these can generate alarms and flag up where change is occurring within the structure that we're monitoring. I should stress this is non-invasive imaging, so we deploy sensors across the ground surface, allowing us to see many meters non-invasively into the subsurface, much as we can achieve with sort of medical imaging of the body. We can scan the body to see what's happening inside non-invasively. Now, this technology has been deployed very widely across the UK on pilot sites, looking at engineered slopes, natural slopes, water-related problems, and for energy research. It's also been deployed internationally, looking at moisture-driven processes in natural slopes and also for agriculture. But what I want to show now, just to end, is a brief case study looking at a water-retaining structure. I should say we have deployed this technology on dams with commercial partners, but at present those pilots are still commercially in confidence, and we're not yet at the stage where we're going to release the data, though they are going very well. So I'm going to use a similar example, so a canal embankment, to show how this approach can be used for leakage monitoring and detection. So here we have our field site. It's a canal, and then the shaded region just to the north of the canal, just above the canal, is our embankment. So this canal is sitting on a hill slope, dipping down towards Grove Cottage, with the towpath on top of the embankment. There are a number of known leak locations, so we use this to, if you like, to validate the prime system where we knew leaks were occurring. So we deployed a 200-meter array along the toe of the embankment in this case to try and detect and monitor the leakage. You can see the sensors being installed here. We install them just below grass level. Just for protection, we could put the sensors on the ground surface, but the cables are likely to be disturbed if they're there for a long time. So we bury them just below grass level, and then we cover them. You can see the toe of the embankment here with the sensors having been covered back up. You can see the instrument being installed on the towpath and the solar panel to go with it. And then after installation, the only bit of the monitoring system that could be seen is the green box. Everything else is buried out of sight. Now, the reason we chose this site provided by the Canal and River Trust was that we knew that the leaks were due to be remediated. So the canal was drained and then relined. And we were able to monitor, if you like, a before and after. So looking at a leak situation going into a no leak situation. So you can see our baseline image, our scan at the top of the page there. So our 200-meter section, we're looking about 10 to 15 meters into the subsurface in terms of the vertical array. You can already see that we've detected the three main leak locations, lower resistivities, which means a higher moisture content. Okay, and what I'm going to show you next is a time series showing how the resistivity changes over time at this site. So here we go. Relative to the baseline, we're sitting in the summer here, going into the autumn. And at this point, we're entering the winter. The canal has been drained by this point. And you can see there's a lot of rain, so much of the subsurface is wetting up. You can see the blue region. This is because of the rain, wetting the surface up during the winter months. But you can see in the areas of our leaks, the ground has actually become, in relative terms, drier. And that's because the leaks have been stopped. So ground that was previously saturated is now only partially saturated. So effectively, we're seeing the drying out of the leaks, even though the ground is still pretty damp in the surrounding area. So what this confirmed to us very clearly was that the system could detect leakage from the canal. It's provided information on the location and the size of the leaks. Now, these leaks, not all of them were obvious from the ground surface. Some of them represented underground leaks. We were provided with daily information on changing leak conditions and operated remotely and without mains power. So just an
I think you
example
can
of
please
this,
conclude.
monitor leakage from a water retaining structure. So just to conclude, we have a unique monitoring system here. So in terms of the end-to-end automated remote data collection through to information delivery, this is a global first for a low power, low cost system like this. It's non-invasive technology, so faster and safer to install. Provides remote data access, so improved health and safety, reducing the amount of time people need to spend on site. very, very suitable for dams as a cost-effective means of monitoring the internal condition of those sorts of structures. And something that we feel is very appropriate for monitoring the internal condition of large dams. As I said, we have a number of pilot sites underway, including tests on large dam structures, and we're hoping to release the results of those monitoring studies very soon. But thank you very much for listening.
Sanjay sir, please announce next presenter.
Hello.
Yeah, sir. Please, next presenter.
Next presenter, please. Yes.
Good afternoon, Chairman sir, and all the participants. This is Yogesh Visa. I am the Director Central Water Commission. I am making presentation in my paper. I will just share my screen. Good afternoon. So I am making a presentation on development of software for the effective management of dam asset and health data. So this software which we have developed, it appears.
I think your voice is not clear. You have to come, I think, closer to mic.
Okay, sir. Is it audible, sir?
Now it is audible.
Okay, sir. So this software which we have developed, this is a part of the bigger challenge, that is the dam safety part. So if in sum, if you see what are the important major challenges related to India dam safety, so these have been listed here as inadequate allocation of resources, weak dam safety culture, inadequate investment in staff and training, then no centralized database, and no effective monitoring system. So this software is a part of this fourth component, that is no centralized database, which is very important to make the informed decisions about the rehabilitation of the dams. This drift, Dharma presently, the software, it is a part of the drift scheme. Drift in the sense, logistical farming, dam rehabilitation and improvement project. It is the World Bank funded project with the objective as improve the safety and operational performance of the selected dam under the supervision of the overall supervision of Central Water Commission. It has three components, that is rehabilitation, institutional strengthening, and project management. The present software is a part of the institutional strengthening component of the DRIP scheme. This scheme is being implemented for the rehabilitation of 198 dam projects in 7 states with 8 state agencies and 2 central agencies. Now, if you think of why Dharma, let me tell you the full form of the Dharma. It is the Dam Health and Rehabilitation Monitoring Application. Why Dharma is required? As I highlighted in the first slide, that there is no centralized database. So, to overcome this challenge, this Dharma is required in the sense to bring the stakeholders together to ensure the completeness of information assess the soundness of dam health, and effectively manage the asset inventory. We'll see one by one in this next slide. The first problem which I explained, why is it required to bring the stakeholders together? Because for any dam project, there are multiple stakeholders in the sense that there are operational staff, there is the dam safety organization at state level, then there are consultant, designers, contractors, and at central level there are stakeholders. So Dharma collects this information regarding stakeholder. Secondly, by needed to ensure the completeness of information. This is also one of the challenges in collecting the data, in the sense that all this data is not available in standard format, or it is not available in a uniformly with all agencies. Secondly, India is the third largest country with, in the case of a number of large dams. So with such a wide geography, such a voluminous data, this completeness of information needs to be ensured. That is by Dharma. Third is the why, because to assess the soundness of the dam health. That is, once we collect all this data related to the dam asset and its rehabilitation data, then from that data we need to process that data and we can assess the soundness of the dam health. And the fourth and the last why Dharma is because to effectively manage the asset inventory, in the sense that from this asset data what we have collected, we will be able to make informed decision out of this data. That is why we need Dharma. If I try to figure out to map Dharma with asset management tool, then in short it can be multiple levels, in the sense at dam level, then at basin level, then at state level and centralized level, with each unique functions at each level as an asset management tool. DRIP and the Dharma as a catalyst for the strong dam technical care, wherein inadequate investment in staff and training to national and international best sharing practices, and from inadequate allocation of resources to proactive asset and risk management. This is where the DRIP and the contribution of Dharma as a catalyst into this will be required. Now, what is Dharma? Now we saw why Dharma is required. Now, what is Dharma? Dharma is, if I go to define it, then it may be defined as it is a web-based asset management software to support the effective collection and management of asset and health data for all large dams in India. It is a web-based software, so it can be accessed at any time and anywhere, independent of its location, be it the plains, be it the health, be it the forest, and at any time. Data collection. Dharma is an important part of the Dharma. It collects the data at the dam level, and it is at the same time it gets available to all the state level and the central level. Then the data collection. Then the third one is the asset management. Asset management, out of this data, what we have collected, we will be able to effectively manage this data. And the asset and the data management in the sense that what we are collecting, we are not only collecting, we are processing also, we are storing it, we are securing it. That is why it is a data management. Now, what are the interface of the Dharma? There are 7 modules in Dharma. Out of these 7 modules, all these 7 modules are part of the data collection in Dharma. There are, out of 7, there are 2 modules which are static modules, kind of fixed modules or stationary modules. This data will be hardly fixed once in a lifetime and hardly changes. And all other 4 modules are the dynamic modules. We will see one by one in the next slide. The first static module, I would say, it is the project features. Project features, it has mainly 3 tabs, that is the general tab, location tab, and the financial tab. General tab tells about the dam, its purpose, location, its lifelong, its seismic zone hydrologic data, and the financial information, that is past information about the dam construction, its cost, its year, like that. Next step, static model is the project portfolio. Project portfolio, nothing but it allows the dam authorities to map this dam in tree-like structure. So there are, for this tree-like structure, there are 17 project components have been identified in this schema. Out of those 17 components, the dam authority need to map out his dam. First, I will show one example. These are the 17 components: the reservoir, dam, gallery, drains. These are all. And then last is given by the physical component in order to ensure that if any component out of these 16 is there, that is required to be given, then the project operator has possibility to add this under safety component. These are the major safety components affected. They then land projects can map with the dam in Denmark. So just to give an example, I'm showing here the one tree structure for the rapid dam. This is the dam. Below this, there is a reservoir. There is a left side. There is a rapid main dam. In the main dam, there is a left side of the dam. Left spillway, right side of the dam, right spillway.
I think you have to come closer to speaker. Yeah.
Okay, sir. So like this, this tree structure can be defined in this project portfolio model. The third static model is the engineering features. Engineering features is nothing but it gives the it captures the technical details about all the components which have been defined under the project portfolio. So, for example, if it is the dam, then for this dam, what is the storage capacity? If it is spillway, what is the discharging capacity? So, all kind of technical details about the every component defined in the project portfolio can be given. The next four modules, dynamic modules. The first one is the important one, that is the asset health module. Asset health module is nothing but the inspection, investigation, operation maintenance, emergency action plan. All these data are captured under this asset health module. Inspection, as you are aware that all this inspection data, yearly data, specialized inspection, then investigation based on any deficiency, to find out any deficiency and to decide the rehabilitation measure. So all this data, if the dam has operation maintenance manual, yes, no, when was it published, what is its reservoir root curve, emergency action plan, what are the stakeholders, all this information, this very important information is captured under this asset health module. This asset health module, then we go to asset rehabilitation module. Asset rehabilitation module captures the what are all the rehabilitation efforts have been done in the past for this particular dam. This can capture the scope of that particular work, then its contractor, then its cost. All this information is captured under this asset rehabilitation model. The next comes the stakeholders model. Very important model again. Stakeholders, all the project staff, then contractor, supplier, designer, this consultant, everything is captured in this stakeholder. Then beneficiaries, irrigation, hydropower, tourism, navigation, all important functionaries are captured under this stakeholders model. And the last one is the document library. All the, as you may be aware that there is a very big problem that documentation is very poor. So in order to overcome this difficulty, this document library tab has been provided so that all the important like the design, drawing, pictures, all such important documents can be stored under this document library tab. So next we come. So far we have collected the data under all these 7 modules, static modules and dynamic modules. Then how to use this data? It comes here, data analysis tools. So this is there. For this there are two tools. One is the dashboard and the other is the report generator. In this dashboard this module, data analysis tool. This here, just I have seen the figure. We can see for each implementing agency, be it WRD or electricity board, what is the progress of the data entered in this. In this, we can see static in the sense the progress of the first three modules, data entry. Here you can see different percentages, how much the progress against the static module. Similarly, for dynamic module, what is the progress we can see, and inspection, what is their progress in the dynamic module and the inspection module. You can see for different search criteria we can go. We can see state-wise, we can see implementing agency-wise.
Please conclude.
Yes, sir. And inspection module, we can see the deficiency and the category of deficiency identified by the dam authority, and we can see accordingly we can make decisions where we need to look at and how we can go ahead with the rehabilitation of the dam. So this is the report generator. Next, what is the present status of Dharma? More than 5,000 dams registered, active users more than 1,000, and dam assigned 1,500. Then so far we are also conducting training, 30 trainings, more than 1,000 participants, and it is being used by 18 states and 25 state agencies. And in the conclusion, I will say that Dharma is progressing well, but still we have a long way to go in its implementation in India, and there is scope for further development also. I thank you very much to Chairman Sir and this Icold for providing this opportunity to present my data. Thank you very much.
Is this software is available, commercially available?
Sir, this presently it is not commercially available. It is with the Central Water Commission, and based on the request from the implementing agency, we provide the users login ID and password to the agency level, and in turn agency level from agency actually BBMB is also registered with us, and I can show you there is a you can see this is the BBMB is also there, and there is 75% of data in case of static modules. They have been completed. There are 4 dams BBMB, 75%. So it's basically a repository with the Central Water Commission, but based on the request, we we provide login ID and password, and they can use this data.
Okay, thank you very much. Very nice presentation. So now I will request to present this 4th paper. It is improving dam surveillance and monitoring in countries with non-existent legal and regulatory dam safety framework case by Mr. Joffrey. Yes, Mr. Joffrey, please.
Dear Icold delegates, fellow delegates, I bring you greetings from Uganda, East Africa. Today, I'm presenting a paper entitled Improving Dam Surveillance and Monitoring in Countries with Non-Existent Legal and Regulatory Dam Safety Framework. And our case study is Isimba, which is in Uganda. My name is Godfrey Rakafunjo. I'm a civil engineer, and I'll be presenting on behalf of my co-authors, Wilberforce Manuel Pizarro, Dr. Mary Crute, Dr. Jotham Sempeo, and Dr. Harrison Mutikanga. We all work for the Uganda Electricity Generation Company. To summarize the presentation, we shall have introduction, we look at visual inspection, we look at functional checks, we look at instrumentation, we look at dam safety audit, and we shall conclude. Dam surveillance and monitoring is a core of operation and maintenance for any dam across the world. However, more importantly, it relies on the prevailing laws and regulatory framework of a particular country. This is where Uganda is located on the world map. Here in East Africa, we border Tanzania, Kenya, and DRC. In the green, those are the dams that are on the Nile. River Nile is the longest river in the world, and it starts from Uganda. But our focus today is not on all those dams. Our focus today is on one particular dam, which is the Simba hydropower plant. As you can see, those are the megawatts. We have one Falls Dam 380, which is 250. Our focus, which is the Simba, is 183 megawatts, and Karuma is 600 megawatts. Simba was commissioned on 21st of March 2019, and it's a 1.6 kilometer composite dam. It has a gravity dam and an embankment dam, and it costs a whopping cost of $567 million. And our reservoir is as big as 170 million cubic meters. That's the beautiful Simba. We call it the pearl on the Nile. Now, according to world statistics, the highest percentage of dam failures happen at impounding and in the first 5 years of operation. Hence, we have a critical phase for Simba since this is its second year of operation. That is according to Oregon. For Isimba, dam surveillance and monitoring was benchmarked on the Swiss Federal Safety Guidelines together with Icold guidelines. But we can never talk of surveillance and monitoring without resounding this Icold bulletin. This framework has both structural and non-structural components. These aspects have further been discussed in Icold Bulletin 158 and 118. These aspects, all of them fit into the overall safety of the dam. But for someone out there, why should we carry out? Why is monitoring and surveillance this important? I mean, why? We have built the dam, we have good engineers. Why? This is the reason. One is to identify key physical changes and detect any early abnormality or anomaly. Second is to detect the potential failure modes. We also need to conduct and analyze the trends. How are the things changing? Today you have a small crack, let's say a big crack. We also need to do improvement or repair measures. We also need to balance automation and human interaction. Now we know that there is improvement in AI, artificial intelligence in most of the dams today. We need to balance the automation and human, then data storage and defense. Therefore, improving dam surveillance and monitoring is the best strategy for risk reduction. This is according to Icold Bulletin of 2029. How is surveillance and monitoring done at Isimba as our case study? What are we doing at Isimba? Maybe you are doing better than us, or you can learn something from us. I mean, what are we doing? What is that? We are doing daily inspections. The daily inspections have daily, weekly, and periodic as per our dam surveillance manual, which I already talked about. For example, we have the spillway gates. The structures are inspected daily to look at what is happening. We had an incident where a steel pipe was stuck between the gates, and you can imagine. Two is that level 1 staff have been equipped with sufficient knowledge. Personally, I'm level 1 staff, so we've been equipped we've reviewed drawings, we've reviewed manuals, we've read Icold bulletins, and we have sufficient knowledge. We are in the process of getting level 2 and level 3 experts in progress to look at, because what I look at might not be the same as what an expert looks at. It's also part of visual inspection. We also have the third blanket, which we call the panel of experts. This is a seven-member committee that does periodic inspections at Isimba. We have also developed a tracking tool for both daily inspections and crack monitoring. Now, this tool allows us to have pictures, have photographs, you have the dates, but you also have a section for recommendation and comments. This one can be used by any other person in case maybe someone goes to another plant or another project. To cap it up, the visual inspection, a comprehensive checklist is always the greatest yardstick. When you have a good checklist, you can always see you can always focus on what to look at. When you go out in the field and you don't have a checklist, maybe you can look at things which you're not supposed to look at, but a great checklist is the best. And there are very many templates, and I'll be happy to share ours. Functional tests. Now, these functional tests are we carry them out on spillway gates, on emergency diesel generator, and the mobile hydraulic unit. But at Simba, the capacity of our gates is 5,250 cubic meters per second, and it is far, far greater than the 4,500, which is the 1 in 10,000 year probability. So that means that at Simba, we are very safe when it comes to capacity of the spillway gates. We have 5 spillway gates, and what we do every month, we open and close them, and then we record the time. How long does it take to open and close? We have 2 emergency diesel generators installed at Simba. These are for emergency because there is a national blackout, as you're all aware. Blackouts happen. We run these generators for 30 minutes every month. This is to make sure that they are working very well. We also operate the gates using a mobile hydraulic pump unit every year. This is sort of like the last resort in case the emergency generators don't work. If you all recall the Tours Dam failure of 1982, it was reported after the overtopping that the emergency generator was not available. And I believe it could have been on site, but it wasn't working. So we have a case here. Instrumentation. Every dam needs measurement with aid of instruments. Unlike other dams built in the past, Simba was able to tap into the latest technological advancement. On the far left is a kilometer for horizontal displacement of embankment. The middle is the geodetic survey level for vertical displacement. And on the far right is myself doing with the settlement gauge. That one is for vertical displacement. This is an example of points installed at one of the challenges, 1+275. You can see SP14, SP14 is a standpipe piezometer, SP14-1 is another standpipe piezometer, SP3, those are vibrating wire piezometers, and we have C10, where the magnetic tapes are installed. So with 293 monitoring points, Simba is well monitored. This is a summary with together with the frequency. We have weekly, we have like an implementer will do weekly measurements, the Vinwatch weekly, the automatic weather station is daily per hour or per hour for some parameters, the anemometers weekly. So this is the summary of the frequency that we use to Simba. We have the dam safety audit. The dam safety audit, it audits the implementation of the dam safety management system. Yes, we set up the system, but can we audit ourselves and see what we are doing? So we have an in-house audit team. We also have a level 2 review and audit. These are managers who come in, review what we have been doing, what we can improve, what we can maybe drop, what we can maybe teach other people. We also have external audits. Again, the panel of experts come here on the auditing. These are people with over 300 years of professional experience in dam engineering. An example, a picture here is one of the experts, Lydian, is a dam engineer, is a geotech and a dam engineer with over 38 experience in dams across the globe. Here we had an increased discharge at one of the weirs downstream. So together with the dam owner, gentlemen you see in white helmets, for UEGCL, the gentleman in red is for the contractor. And here we are assessing, she was assessing why and looking at it and analyzing the trends, what discharge did you have in January, March, what happened in July. And with the PO's continued interface with the client and the consultant, we have had several recommendations implemented. Some are already work in progress, others have already been implemented. So, in conclusion, countries with non-existing laws can operate hydro power plants safely while mitigating the risks of losing revenue and affecting downstream communities. By implementing the best, by customizing the best practices from countries with strong regulations, having periodic review by level 2 experts and even level 3, but also dam owners should invest resources in training and capacity building of staff and involve them in establishing this dam safety management system. However, even with a few dams, if you're out there, maybe you say my country has 2 dams, 3 dams, you need to enact these dam safety frameworks, because even if you have 1 or 2 or 3, you don't want to lose 1 dam and wash away communities. So, as per, to cap it out for this presentation, as for Isimba, are we going to be sipping coffee as we wait for this regulatory framework? Maybe no. For us at Isimba, of course, no. We said we shall continue doing the visual inspection and functional tests. We shall also continue with instrumentation. We are going to get our POE and the level 2 to review what we are doing and look at these reports and the recommendation. And also, we shall do a dam safety audit periodically, assess our progress. Thank you very much. I remain Godfrey Kafunjo, and this is Icold, Uganda Committee of Light Dams and Uganda Electricity Generation Company. Thank you, Paul.
Thank you very much. I think you are doing a commendable job, and you have the system which you have narrated is very good. I think we also have to learn from this article. So thank you very much. So now I would request next presenter, Case History and Lessons Learned, Early Warning System of Mosul Dam from Iraq, Mr. James.
Hello, my name is Jim with AECOM Technologies. This paper is titled Case History and Lessons Learned, Automated Instrumentation System, Mosul Dam, Iraq. The outline of this presentation will basically go over the background of the project, the reason for the project, the types of instruments that were automated. We'll describe the automated system itself, discuss the options that were employed to present all of this information on a web portal, project web portal, and then finally conclusions and lessons learned. Mosul Dam was built in 1980, early 80s. It's located on the Tigris River, about 50 kilometers northwest of Mosul, Iraq. The dam is a zoned earthfill embankment, 113 meters high, 3,650 meters long. There is a powerhouse located here. There's a concrete lined gated spillway over here near the left abutment. And then there is a reinforced concrete grouting gallery that extends beneath the embankment, all the way across the embankment. And the reason for that is the geology consisted of a karst bedrock foundation. It had alternating layers of limestone, soluble layers of gypsum anhydrite, and has been experiencing sinkholes on the downstream embankment area and in the left abutment area. So going back to the original design of this structure, it was intended that there would be a long-term maintenance grouting program. to counteract the solutioning of the foundation material. And that consisted, that consisted basically of a fairly significant grouting program on site, full-time, going back to the mid-'80s. It was interrupted, the grouting program was interrupted in 2014. So there was almost a 2-year period where there was no grouting taking place, and government of Iraq and U.S. Army Corps of Engineers wanted to understand exactly what the present state of that dam was. So we were contracted to come in and basically help them design a system, fabricate the various data acquisition units and so forth, and help them bring that system online. And that was in 2015. So there were basically 13 closed system piezometers that we automated in the gallery, and we installed 47 new crack meters. These were placed in sets of 3 at each of the concrete joints. This here is a cross section of the grouting gallery, and you can see that it follows the basically follows the surface of the bedrock. The instrument locations here, you can see the automated piezometers are in blue, and then the X's indicate new crack meter locations. This diagram here shows a set of instruments that were automated. In this case, we have 4 closed system piezometers. We spliced in pressure transducers in the existing standpipe with swage-like T-fittings. And we added in this case, it was a Geocon 4500 or 3500 vibrating wire pressure transducer. These are the sets of crack meters. Again, sets of 3 for XYZ deformation measurements. On the embankment, we automated 28 open standpipe piezometers. These were existing piezometers. There were also 4 existing seepage channel weirs. We automated those as well, automated those flow rates. But we also installed new instruments. These are called deformation loops. We installed those mostly over in this area here. And there's a detail here that we'll go over shortly. This is a plan view of all the instrument locations on the embankment. And the data acquisition units, these blue rectangular symbols here are RIO units. They were basically Campbell Scientific AVW 206 units, sometimes with a MUX in the same cabinet, sometimes just as a standalone 2-channel data logger. The red squares here were remote monitoring units. Those were basically enclosures that house Campbell Scientific CR6 units. We also had satellite transmitters at each of those 5 RMU locations and cameras. The open standpipes were basically retrofitted. We basically added this enclosure with the data acquisition unit inside, a battery, solar panel. These were like little kits that we fabricated so they could be quickly added to the top of the standpipe. There's air terminal here for lightning protection. And we have a down lead that basically all the electronic components, including the solar panel, are bounded to that down lead connected to this grounding rod. The radio communications here, we just used the dipole antennas, and since these were fiberglass enclosures, we installed those inside the enclosure just for additional protection. This is the deformation diagram here, deformation loop diagram that I mentioned earlier. And this consisted of 4 cables of varying lengths from 30 meters to 76 meters approximately. And then if there was a depression forming or some subsidence in that area, these are basically heavy concrete weights out here at the end. And if there was a subsidence, it would break a cable, maybe multiple cables. And depending upon how many cables broke, you could get a rough idea of how large an area that you're talking. And we did detect movement on one of these locations, so it did work. The ADAS, when we started out, we discussed key design principles. And basically, one, we knew we had to retrofit existing instruments. We had to have something that was easy to install and could be quickly installed. Everything had to work the first time. And then everything had to be solar powered, including the BGAN satellite terminals and the video cameras. Again, we don't need to go over this in detail, but you can see the locations of the cameras again. These here looked across the upstream embankment and across the crest of the dam. This one here, this set of cameras looked at the outlet works and the spillway area over here, this general area. We had a camera at the base of the spillway. We had a camera up in this location that looked out over the crest. I'm sorry, not the crest, but the downstream embankment section over towards the west. This is an architecture diagram. It shows the data being collected over on the left-hand side of the diagram at these remote units. The data then would be basically transmitted to a BGAN satellite, Inmarsat satellite constellation. And then there'd be an Earth station. We had an Earth station here in the US where the data was downloaded. And then we had it routed over a terrestrial VPN network to a hosting center where we had virtual PCs and servers to manage all of the instrumentation data and photo images coming off the dam. From there, the information was available on the internet. We had a project portal that was set up. Detailed technical charts were generated every 15 minutes to every hour. Any project stakeholder could log in and view that information. We also they could also use their phones to view the plotting and any other information that the camera views worked very well over cell phones, tablets, and desktops, of course. So anyway, that's basically the data flow here, collected by these remote monitoring units, Campbell Scientific CR6. These were robotics cameras, video cameras that we used still images and relayed those back to the project web portal every 15 minutes. And then again, the hosting center and environment, laptop connections here for people to interact with the system from any location. And the alert messages, typically those were text messages. We also sent out email to everyone on the project. This is a view of the 6 cameras. This is near the base of the spillway. This is the upstream embankment. There's the lake. This is the camera that looks out over the crest to the downstream area here. The spillway is over on this far side over here. This is the outlet works. This is a view across the lake. Well, not the lake, I'm sorry, the outflow channel here. Looking in, there's a spillway section right there. And then finally, there was a camera that was located on the east side of the embankment that viewed the downstream embankment to the west. This is the project portal. All of this information was available to anybody working on the project. And you could view all of the technical charts, time series charts, correlation plots, etc. And all the camera images were also available here as well. We had an interface with Google Earth. All the instrument locations on the embankment section were displayed in this fashion. And they were color coded for yellow or red alerts if those threshold exceedances occurred. Basically, you could see the current reading by clicking on that instrument, and you could also bring up the current time series chart for that. It's another view of the instrument locations. So this is a view of the upstream embankment. This is the gatehouse basically, and this is where the cameras were located. This is the downstream embankment looking over towards the powerhouse. So in conclusion, the automated system was very reliable. It was designed to accommodate future expansion. And currently, we started out with about 100 instruments in phase one that were automated. And then we automated about 300, a little over 300 instruments by 2018, 2019 timeframe. And now the government of Iraq has added 200 more instruments. So there's over 500 instruments now connected to the system here. And this was turned over to the Iraqi government in 2019. They continue to operate it, add to it, and are fully responsible for evaluating.
I think there is some problem. So others are listening.
Yes, sir.
I think this was very good presentation. I think we have lost the connection. So we will straight away go to this last paper of this session. So it is Koira Basa Dam Spillway Rehabilitation Emergency Stop Log Operation and Regulating Gates Instrumentation by Jose D. Mello. Please upload your presentation. Jose D. Mello, yeah. Gates Instrumentation by Jose D. Mello. Please upload your presentation. Jose D. Mello, yeah. He is in mute. Please unmute yourself. By Jose D. Mello. Jose D. Mello, please unmute yourself. By Jose D. Mello. Jose D. Mello, please unmute yourself. By Jose D. Mello.
Dear colleagues, my name is Melo. I am from Portugal. I am one of the co-authors of this study. The other colleagues are identified in the lower part of the slide. They are colleagues coming from Portugal and from Mozambique. The presentation relates with the Cahora Bassa Dam, an existing Mozambican dam with 45 years of operation. And this dam, which I have here a general overview of the dam. It's an arch dam, very high dam with 171 meters high, and a very large reservoir with capacity of 65 cubic kilometers.
Presentation is not visible. Presentation is not visible.
Sacrifices, all identical, that constitute the spillway, and also an additional crest spillway that allows passing the presentation relates with the Cahora side. They are colleagues coming
I think there is some technical problem.
Big dam with 45 years of operation. And this dam, which I have here a general overview of the dam. It's an arch dam, very high dam with 171 meters high, and a very large reservoir with capacity of 65 cubic kilometers. The dam has 8 deep orifices, all identical, that constitute the spillway, and also an additional crest spillway that allows basically some additional capacity, but mostly passing the any floating materials accumulating upstream in the reservoir. The capacity, the maximum capacity of the spillway is 13,000 cubic meters per second. And the issue that has been observed during the dam observation relates with the development of alkali aggregate reactions, which impose deformation on the dam body, and these deformations inevitably affect the spillway orifices, changing its rectangular section to some different shapes that may compromise the reliability of the spillway regulating gates. It is important to point out that the spillway orifices work under a very significant hydraulic head of 80 meters. And they also consider the possibility of isolating the orifice by, both for maintenance, which is done on a periodical basis by lowering a stop log from the dam crest along the upstream face of the dam, which in balanced pressures is rather safe. But also in the design, it was considered the possibility of lowering the stop log with the operation of the spillway taking place. This is, of course, in case of a blockage of the regulating gate, which might occur in any position. would force the operator to cut the flow by lowering the stop lock under full head and full load in order to avoid the loss of a significant impounded volume of water above the elevation of the spillway orifice. So in order to prevent or to mitigate this increase of risk of blockage of the operating of the regulating gates, the dam owner initiated a set of studies in order to minimize the consequences of such occurrence. To give you a brief idea of the dam characteristics, of the spillway main dam features, I would point out the geometrical dimensions. It is they are very short in length. The height of the orifice changes from a maximum entrance height of 15 meters to a height of 7.8 meters, so it is converging when moving downstream, and the width is constant of 6 meters. It has also this ascending longitudinal profile in order to enhance the jet reach downstream. Each orifice is also equipped with ventilators. The larger ventilators immediately downstream of the entrance in order to avoid depressions when this gate is operated, so to enable the installment of the atmospheric pressure inside the orifice, and also in the upper part of the orifice, smaller ventilation aerators are considered. To cope with the challenges posed by the alkali aggregate reactions into the operation capability of the spillway, hydraulic models were studies were carried out, namely by building a 1 to 40 physical model, which it is depicted in this picture. So we have in blue a reservoir that allow to simulate the hydraulic head upstream, where also the geometry of the approaching stretch of the flow to the orifice was reproduced, and the stop lock. Then across the dam it was reproduced in plexiglass, the spillway, in order to enable the flow visualization. The aerators are reproduced, and the regulating gate, we see it here, it was reproduced in brass. And of course the jet that forms is reproduced. It was scheduled a set of tests to verify not only the normal conditions, which you see here, the full opening of the regulating gate, and also 5 sets of scenarios in which we assume the blockage of the gate in 5 positions, 20, 40, 60, 80, and fully open. And then we lower the stop lock and observe and measure the pressures inside the orifices, the aeration conditions, and also the downpull force in the stop lock suspension chain. Another view of the model, general overall view. Here it is possible to see the reservoir, a side spillway in the reservoir that enable us to move the stop lock with constant discharging to the model. So the extra water that is coming in when closing the gate is spilled over the side, while keeping the head in the model.
I think we have lost DeMello. Anyone from Icold side? Will it resume?
Sir, I think some network issue.
It seems network problem is there. So first presenter is available. Mr. Sayyad. So have you received any questions?
No, sir, not available.
Acha, Mr. Sayyad is not there.
Not available.
Okay, so any question you received from participants? So now I think we will take question answers.
Just I'm checking, sir.
So Mr. Jonathan is there. Professor Jonathan.
No question in chat box, sir.
Okay, Mr. Professor Jonathan is available. I have a question for him. Mr. Jonathan.
No, sir, not available.
Not available. So, okay, then I will conclude. So we had a very interesting session over here. Very good papers were presented. Unique case studies were there, particularly this Mosul Dam. Mosul Dam, it was a very, must be very challenging even during construction. And or Mr. James is there online. I have a question for him. Mr. James. James. I think Mr. James is also not there. Okay, then I thank all participants and Icold for organizing such an interesting event. So we are going to benefit from this seminar very much. So we have full papers. I think all participants will go through those and make good use out of this. Thank you very much.
Thank you, sir. Thank you, Icold.